Now we're gonna switch a little bit to a different topic, which is very relevant in practice. This is the topic how you actually design the database that you want to store in a relational database management system. Now, that is a problem that keeps occurring in industry, for instance, and at a high level, we typically follow the process that is described here. Typically, you would first do something called the requirement analysis, where you essentially get some more information about the use cases in which the database is being used. You get a description of the business processes if you're considering to create a database for a company. And based on that, we first of all do the conceptual design, which essentially is a model of the data that you want to store in your database. And especially if you are talking to people who might not have that much IT background, then trying to describe the database by showing SQL queries, that is probably not a good idea. So there's a couple of graphical formalisms that have been developed in order to represent databases in a little bit more intuitive way. And those are entity relationship diagrams that we will see in the following. If you have a first design for your database, then often it is somewhat suboptimal. We will see later that it is easy to introduce lots of redundancy in your database design. And during the schema normalization step, your goal is to essentially get rid of that redundancy in order to come to a better database schema. And based on that, you typically create the database. So in the end, all of this translates into those SQL create commands that create the different tables and constraints. And then finally, in practice, what you would also do is some kind of performance tuning. For instance, we have seen indexes, and during the physical tuning phase, we would, for instance, decide which indexes to create, which sort order to use for specific tables on disk, and so on. So everything which doesn't influence the semantics, but influences the performance of processing. Now, in the following, in this and a few further lectures, we will mostly discuss about those two phases over here. We will discuss about the conceptual design and about a schema normalization. Now, in this and the following lecture, we're going to start looking at a conceptual design, and we're going to learn a graphical formalism for representing a database schemata, basically, that is called entity relationship, or short ER diagram. So that is a formalism that is heavily used in practice. I should warn you, the precise notations sometimes differ slightly if you look at different books, for instance. So if you're looking at an entity relationship diagram from a database, or if you're drawing one, make sure that you're on the same page with the author of the drawing or with other people you're collaborating with about what semantics you attach to specific symbols. But even if the precise representation sometimes differs a bit, the things that you can model, the concepts essentially stay the same. In the following, we're going to mostly see different formalisms that appear in entity relationship diagrams. So the most basic concept in entity relationship diagrams, those are entities with associated attributes. So the term entity is very generic. It can be a thing. It could also be a person, like an employee. In any case, if you have entities that play a role in your scenario, then you group them into entities of the same type, which you represent as rectangles, typically in your entity relationship diagram. Those entities typically have some kind of properties, attributes, which are represented typically as ovals in the entity relationship diagrams. And then you simply connect those ovals to your entities in order to indicate that this property belongs to that specific entity. Often you have one or multiple attributes that together uniquely identify one specific entity of a specific entity type. That is essentially like the keys in relations. And you represent that in the entity relationship diagram by underlining all the attributes that are part of the key. Also important to know, the values for those attributes are restricted, so you wouldn't use attributes to model any complex composite data types. Instead, those attributes have simple types such as integers, for instance. This is one simple example. If I want to create a database for Cornell, for instance, then I would probably have to model students, obviously, in some way. And this is how I could represent it in the first simple version. So here, the student is basically the students, the set of all students. That's an entity type, and we represent this by this rectangle here. And here I have three properties: name, GPA, and net ID. All of them are of simple types, and here the net ID is underlined, meaning that this should be a unique identifier. In order to make things more interesting, we can introduce relationships that connect different entities. And those relationships are represented as diamonds in the entity relationship diagram. We connect those diamonds to the entities using simple lines. And we often have binary relationships that connect two entities, but we can also have relationships that connect more than two entities together. Here, for instance, again, taken from the university scenario, we have, for instance, a relationship that connects entities of type lecturer to entities of type course on the left-hand side. And on the right-hand side, we have a connection between entities of type lecturer and entities of type room. So those are two binary relationships. Here we have a ternary relationship which links entities of type lecturer, courses, and rooms together. So here essentially those are relationships that always connect one entity of each type, one lecture with one room and with one course. And here intuitively it seems a little bit related to what we have seen on the last slide. So here we had those two different binary relationships, and now we have this ternary relationship. Little control difference. Semantically, what would be the difference between those two models? So here we have one ternary connection connecting all three types of entities. Here we have two binary connections connecting the same entity types. Is there, for instance, something that you could express with the ternary relationship, but you could not really express that with the binary relationships? Okay, there's a course and room. Can you elaborate a bit more? Or can anyone else suggest some situation that we could model? Yes, very good. So here the proposition is, let me quickly move the chat. Yes, you can tell which course is in which room. And I assume that refers to the binary relationship, and I totally agree with that. So here we have a connection between lecturers and rooms. So here we essentially seem to assume that lecturers are generally teaching in specific rooms. And on the left-hand side, we see that lecturers seem to be teaching specific courses. But I could not, for instance, express any connection between courses and rooms. So for instance, if specific courses are always taught in specific rooms, but perhaps by multiple lecturers, that will be difficult to express. So here, for instance, I could also describe a situation in which one lecturer teaches one course in one specific room, and the same lecturer teaches a different course in a different room. That would be essentially we couldn't describe that situation precisely using this formalism here. So this is already to prepare you a little bit. So in the following, we're going to see a couple of subtle issues around the semantics of entity relationship diagrams. In practice, it is important to be very precise about which formalisms you use in order to describe a situation, because you want to make sure that it matches exactly the information that you want to represent about a scenario in practice. All right, so very good. Yes, so this here is a more fine-grained description of the situation. It allows me to express certain things that I couldn't really express with the other one. All right. Now, I can add even more information by classifying the type of a relationship that I have. So I have multiple ways of expressing constraints on relationships. So here in particular, we will look at participation and at most one constraints. If you put a participation constraint between an entity type and a relationship type, if you put a participation constraint between them, it essentially means that each entity of the connected type must appear at least once in that relationship. So each entity must relate to at least one entity of the other types. And in the entity relationship diagram, you represent this by a particularly thick line. Then you can also express that one entity can appear at most once in a relationship, and you express that with an arrow between the entity type and the relationship. So here basically this is like a functional dependency. Once we fix the entity, then it must uniquely fix the relationship. Here are a couple of examples. So here we have taken a similar example as before. And on the left-hand side, here we have a connection between lecturer and the courses that the lecturer teaches. On the right-hand side, we have a relationship between students and the courses that they favor. So we assume that each student has a favorite course. Can anyone tell me what the semantics of those two representations is when it comes to the constraints? Anyone has a suggestion for any constraint that is represented here? Okay. Yes, very good. Okay, great points here. Okay, very good. So, all right, so I'm gonna go through some of them. Okay, so here, okay, so first of all, we have, for instance, a participation constraint between courses and teachers. And that essentially means that each course needs to be in a teachers relation, which makes sense because you need to typically at least one lecturer for each course, right? So that is the semantics of this thick line connecting course and teachers. And then we have an at most one constraint between lecturer and teachers. So here essentially it means if you fix the lecturer, then it uniquely identifies the teacher's relationship. And that essentially means that here apparently the university has some restriction where each lecturer only can teach at the most one course. And on the right-hand side, I have both constraints combined on one side of the relationship. There's like a SIG arrow connecting student to a favorite. And the participation constraint essentially means that every student needs to have at least one favorite course. And the arrow essentially means that each student can have at most one favorite course. So in taken together, that means that each student has exactly one favorite course. We don't make any restrictions on how often courses have to appear in that relationship. For instance, we don't require that each course is the favorite of at least one student, or that each course can only be the favorite of at most one student. But we do have those two constraints on the student side. Yes, very good. Okay, very good. So I think here I have the right answers from multiple students. Very good. So yes, so that is the semantics of this representation of constraints. All right. You can do more things with relationships. You can, for instance, associate them with attributes which are represented similarly to attributes of entities, and you also connect them via lines. So here, essentially, the semantics is that those attributes, they have specific values for any combination of entities that the relationship connects. So if we have this relationship between, for instance, lecturers and courses, and we add attributes to that relationship, then they refer to specific lecture and course combinations. Also, we can assign entities to roles from the perspective of a specific relationship. And that becomes important if you have relationships that connect one entity type to itself, basically. Then you need to assign roles to each of the two occurrences and label the connecting edges with those roles. So here there is an example, for instance. Here we have both of those features in one scenario. So here we have employee entities, and we want to represent that sometimes employees supervise other employees, and we can do that using this supervisors relationship, which connects the employee entity type to itself, right? So, because we do that, we want to associate the connecting lines with roles. So here we can say that one of the two entities that are being connected is the supervisor, the other one is the supervised employee. Okay. And here, one little constraint that we also add is that each employee can be supervised by at most one other employee. So you cannot have multiple direct bosses, at least. And we also associate an attribute with the relationship. We associate a start time with it. So if we have one specific supervisor's relationship between two specific employees, then here this attribute would allow us to represent the start time of that supervision. Now, one other concept that we will see next time in more detail is a subclassing, which you probably know already from object-oriented languages. Also a couple of other features. We are now approaching the end of the lecture. Here I'm gonna answer one more question. There's a question about what the arrow means in this case. And in general, the arrow always expresses an at most one constraint, which means that if you fix the entity on that side, then you fix the relationship. So in this specific scenario, it means like if you fix the employee that is being supervised, then you fix the relationship as well, which essentially means so each employee can be supervised by at most one supervisor. We don't want to make it a participation constraint because then, yeah, there might be one employee at the very top which is not supervised by anyone, but in each case, you want this supervision relationships to form some tree. So one employee cannot have like two other employees that directly supervise him or her. Does that make sense? Okay, awesome. All right, good. So that was a little introduction to entity relationship diagrams. We are gonna pick it up again here next time, and then we will start discussing about how we can normalize some initial draft of a database schema in order to reduce redundancy and get nice format properties. All right. Have a nice day, and then I see you again on Friday. All right, let's get started. And today we will continue to discuss about database design. Last time we have been discussing about the process by which databases are designed. It starts with the requirement analysis, then you do the conceptual design, afterwards a schema normalization, and finally physical tuning. So the last time we have started discussing about the conceptual design stage, and in that stage you use tools such as entity relationship diagrams in order to model at a high level of abstraction what data you want to store in the database. Now, the last time we have already started discussing about entity relationship diagrams, and we have seen a couple of visual representations for different elements, for different aspects of your database. We've started discussing about entities, which can be persons or things. It's a very generic term, and they can be associated with attributes. As a little reminder, this is how we represent them: entities as rectangles and attributes as ovals that are connected. Then we have discussed about relationships, which essentially connect multiple entities, and we represent them as diamonds in those diagrams, like you see here, for instance. So here, those are binary relationships because they connect two entities. All right. We can also have ternary relationships connecting three entities, or even relationships that connect more than three entities. There is some differences in terms of the semantics, in terms of what you can model with them, and we have quickly discussed about that last time. We have also seen that we can classify those relationships further by introducing constraints. In particular, we have seen the participation constraint, which essentially means that an entity needs to be related according to a specific relationship with at least one other entity. And the at most one constraint essentially means that one entity can be related to at most one other entity in a binary relationship, or for instance, in a ternary relationship, it can be related to at most one combination of entities. So we represent participation constraints by very thick lines in the diagram, and at most one constraints are represented as arrows in the diagram. So this is an example here. For instance, on the right-hand side of the slide, we have the example that students, they have one favorite course, and here you see the combination of a participation constraint and an at most one constraint, because here we have a thick line and an arrow, meaning that each student is linked to exactly one course that is the favorite of the student. So this is how far we got last time. And then we have started discussing about, subclasses. So maybe I should also very quickly remind those two features. So here we have also quickly discussed about the fact that we can associate relationships with attributes. And also we can associate relationships with roles that we assign to the different entities that appear within a relationship, which is required in cases where a relationship connects entities of the same type. And perhaps here, let's have a quick look at this example again. So here we have the entity of type employee, and there is a supervisor's relationships between different employees, which is associated with an attribute that's the start time of the supervisor's relationship. So starting from when was this employee managed by this other employee. And here we have a relationship that connects employees together. So we are connecting entities of the same type. And then becomes important to assign those entities to roles. And here you see those roles are modeled as labels on the lines connecting the relationship to the entity type. We have the supervisor role and we have the supervised role. There's also constraint in here, as you see, based on the arrow. So for the supervised employee, we can have at most one such relationship. So each employee can be supervised by at most one supervisor. So that is a little reminder of the things that we have seen. And on the following, we're going to see more features of entity relationship diagrams. And later, we will see how we can translate those entity relationship diagrams into actual SQL commands or into relation schemata. So one feature that entity relationship diagrams allow to model is subclasses, which is something that most of you might already be familiar with from object-oriented languages. And if you introduce subclasses in your diagram, you essentially reduce the amount of drawing that you need to do, because the subclasses automatically inherit certain things from the parent class, such as the attributes and also the relationships. So if you say that one entity type is a subclass of another entity type, then you save yourself the work of having to redraw all the attributes that are in common between a subclass and a superclass. We represent those subclasses as triangles. Those triangles, they're connected to the superclass and to the subclass, and typically still have some label inside of them. For instance, there is a label. We only support, we don't support multiple inheritance. So if you only consider those subclassing relationships between entity types, then that will form a tree. To make things more concrete, here is an example. And let's, for instance, assume that we have a university database. So we have employees, and then perhaps there's different classes of employees, such as the instructors. And here the employee already has a couple of attributes. So first of all, we have the net ID. And the net ID is a key, which you recognize because it is underlined. We also have the name attribute. And those employees are also in a supervisor's relationship with each other, which we have seen in the previous example. And now we essentially introduce a specific class of employees, which is the instructors. And we can represent that using the subclassing relationship. So here you have the is a relationship, and it connects the employee to the instructor. And the instructor is thereby classified also as an employee. So it will automatically inherit the attributes net ID and name, even though you don't see them here explicitly in the diagram. It also adds a new attribute, which is the number of courses, which only makes sense for instructors, but not for other employees. And it also adds a new relationship, which is the teacher's relationship, which connects an instructor to the courses that are taught by this person. So here we have added a relationship and a new attribute that only makes sense for this specific subclass of entities. Now, another commonly used feature in the context of entity relationship diagrams, this is weak entities. And a weak entity is generally an entity that cannot really stand all by itself. It's always dependent on another entity, and we call that other entity the owner entity. So more precisely, the weak entity will have some primary key, which essentially only becomes unique if you combine it with the primary key of the owning entity. And in order to indicate which is the owning entity, we have to connect the weak entity with a relationship to the owner entity, and it has to be a specific type of relationship. The weak entity needs to be connected by an exactly one relationship to the owning entity. And to make things more concrete, let's just look at an example. So here, for instance, assume that we have an entity type homework, which stores an attribute that is the homework number. And the homework number, all taken by itself, is not necessarily unique, because a homework could belong to different courses. So there will be a homework one from multiple lectures. So as long as you only store the homework number, it doesn't uniquely identify the entity. And this is indicated by underlining the homework number here by this dashed line. So this is different from the non-dashed line that we use for primary keys. So here the homework with the partial key homework number is connected via the belongs to relationship to the courses table, which has the course ID primary key. And now if you take both of them together, if you take the homework number and the course ID together, then you get a unique identifier for one specific homework. So that is the semantics of weak entities. They don't have a really unique key, but if you combine their key with the key of the owning entity, then you get a unique key. And here in this example, the weak entity is the homeworks. Another important concept in the context of entity relationship diagrams is aggregation. And that essentially models a relationship of a relationship. So if a relationship between entities exists, then you can add some additional information about that. We represent this by putting the first relationship into a dashed rectangle, which contains the relationship and the associated entities. And then you connect this dashed rectangle with other items. This is how it looks like. So here, for instance, we could have a situation in which we have departments associated with a department ID, which sponsor projects, and this sponsoring relationship is associated with a since attribute, meaning this is the point in time at which the sponsoring started. And then we have employees that monitor this sponsoring relationship, making sure that everything is accounted properly, for instance. So this is why we have this aggregation relationship. So we have put the first relationship, the sponsoring relationship, into a dashed rectangle. And now we connect that relationship with a corresponding employees that monitor the sponsoring relationship. Right? So here we have the monitors relationship, which is a relationship connecting employee entities to sponsoring relationships. So that is aggregation. And perhaps to clarify things, I mean, in this situation, you could also imagine that we are connecting perhaps three entities: the employees, the departments, and the projects. Does anyone have a suggestion about reasons why we would prefer the aggregation in some cases over those ternary relationships? Okay, all right. So there's the proposition that the department might be monitoring multiple projects. And we don't want to repeat the employee every time when we are drawing. So you have multiple propositions coming in. So here the monitors relationship connects one specific employee with one specific combination essentially between department and project. If you think, for instance, about the constraints that I could add here. So this all goes into the right direction already. I mean, there's many reasons, so there's multiple correct replies. And specifically thinking about a case where I want to introduce constraints on those relationships. If you imagine the same thing, if you imagine instead of this, a ternary relationship between employees, departments, and a project. Okay, yes, very good. So now, yes. So here the proposition is to look at those constraints on relationships that we have seen. Here we have the at least one relationship mentioned, and there's also the participation constraint mentioned. So here, for instance, what I could model would be something like making sure that each combination of a department and project, where the department sponsors the project, is monitored by someone. So I could express this by a participation constraint that connects the sponsor's relationship to the monitor's relationship. Now, on the other side, if you have a ternary relationship, you might be able to express that specific departments or specific projects can get monitored, but you cannot really express that the combination of a department and a project needs to get monitored. And that is only one example. So here we could have multiple constraints that we can model when having two separate relations, but we cannot model them when only having one ternary relationship. So there's a lot of subtleties about which model, which entity relationship diagram you choose in order to model a certain situation. And you have to be careful that whatever representation you choose really allows you to model all the constraints that you want to add. Okay, so very good propositions here. All right. So in general, you have a couple of design choices. Now here we have already discussed aggregation versus ternary relationships. And one thing that you also often can choose is whether you model certain things either by introducing new entities or by adding attributes to an existing entity. For instance, if you think about something like an address, let me quickly move something here. If you think, for instance, about an address, then you can either consider introducing an address entity, or you can consider this rather as an attribute of an existing entity, like of an employee. The first thing to consider is whether the entity, for instance, the employee, can be associated with multiple addresses. Now, attributes in entity relationship diagrams, they must have simple types. They must have, for instance, string or integer types. In each case, they cannot store a set of values. They can only store a single value. So if you want to model something like one employee could have multiple addresses, then you have to model this by an entity as opposed to an attribute, because those attributes, they couldn't store a set of addresses. And also, if you want to structure the address further. So often like an address is structured into multiple fields. You might have the street number, the city, and so on. If you want to represent that structure, then you also have to model it by introducing a new address entity, because then you can model those different components as attributes of the address entity. So those are some of the things to consider when choosing between entities and attributes in your model. Here we have an example. What we're modeling here is the works for relationship between employees and departments. And this works for relationship is associated with two attributes, the from and the to attribute. Can anyone tell me what might be wrong with this representation? Can you imagine a situation that you would like to model, but cannot model with this representation? So remove the question so you can see the diagram better. The question is, can anyone tell me what might be wrong with this representation? Okay, very good. And here there's exactly the point that I was looking for. Great. So the thing is this, one employee might work repeatedly for the same department. Maybe that person worked for a different department for a while and then is coming back to the first department, or even worked for a different company for a while and then is coming back to the department. And that means that I want to be able to associate one employee with multiple time periods during which the employee worked for one specific department. Now in this representation, the from and the to attributes, they have a one value for each combination of an employee and a department, right? So here the works for relationship connects one employee and one department. And here we can associate works for with from and to, but we can only pick one value for from and to for one specific combination of employment and of employee and department. So if you want to resolve that, a better model would be the one that you see here. So here we add a new entity type, the time period of the employment, and then we model the works for relationship as a ternary relationship connecting employees, departments, and time periods. And for the time period here, we can introduce again the from and to attributes. And so here, for the same combination of employee and department, we might actually have multiple time periods during which the employee worked for the department, right? So that is somewhat subtle points, but when creating a database, then those points actually matter a lot, and you have to be very careful that all the constraints that you want to represent and all the things that you want to be able to express can be expressed using the database model that you are choosing. Is there any questions on this? Okay, that's an interesting proposition. So the proposition is that we might also consider using aggregation here. So we have the employee and the department, that is the works for relationship. And now we could associate this via aggregation with the time period. I assume that's the proposition here. So a priori in this context, you could also use aggregation. I imagine that you, via aggregation, the works for relationship has a time period. So in this scenario, you could also model it via aggregation. I assume that you would connect the works for relationship to a time period entity again, perhaps, which would also be possible. I'm not sure whether it gives you additional things that you can express in that way that you cannot express in this way. So with the corresponding constraints, I think you would get something which is close to what we are modeling here. So the answer is yes, you can use aggregation. And the question is, okay, so you want to make sure that the works for relationship has a time period. So in this representation, that is actually ensured because each of those works for relationships must connect one employee, one department, and one time period. So with this representation, you essentially ensure that we mark down a time period for the employment. All right. And all right, and then there is another question. How can you make some of these relationships more explicit? What about when things aren't as clear? Say if an employee works for another employee and the department is a property of where they work. Okay, so in general, so I mean, what we ultimately want to do with those entity relationship diagrams is that we essentially want to formulate those SQL create commands for different tables in order to create a database schema into which you can insert your data. So it is true that it can sometimes be challenging to consider all possible situations in advance. Often those database schemata, they need to evolve, they need to get changed over time in order to either extend them or in order to represent changes that a company is going through, for instance, which impact the data model that they want to use. But I mean, in principle, so basically, I mean, if you want to work with a database, then you have to make a decision about which schema you want to use. You can, of course, adapt that decision over time, but you need to decide which tables to create. So entity relationship diagrams, they help you to make that decision. If your question refers to whether it can be difficult to integrate all possible situations in those entity relationship diagrams, I agree with you. That can be challenging. But for sure, if you want to work with a database, I mean, you have to decide on the schema that you want to use in your database. So even though it can be challenging, there is no alternative, basically. So, okay, all right, yeah, but great question. So, I mean, I think in many of those cases, it is difficult to come up with a good entity relationship diagram. It's also an iterative process. You make a first draft, then you realize, oh, there's a situation that I didn't consider and which I cannot represent with this entity relationship diagram. Then you refine it, and you do this a couple of times until you come to something that you like. So it is challenging, but I mean, we have to decide on some structure for the database. All right, great questions. Now let's discuss a different scenario. So here we are modeling the manager-managers project relationship. And here we have a budget. And let's say this budget is meant to represent a budget that one specific manager has in order to manage all of that person's projects. Same question as before. Can anyone tell me what is wrong with this representation? Okay, so there's some information that is not represented in this diagram. I mentioned that the VJ that is specific to one specific manager, but here it doesn't say how that VJ is partitioned across different projects. Yes, exactly. One manager could manage multiple projects. Yes. So I think, yes. So this is all aiming at the right thing. So the problem is this budget relationship. And very correct here, the point that one manager could manage multiple projects. And in that case, first of all, we are missing information. So because we don't represent how the budget is partitioned across multiple projects. And also we introduce some redundancy because I mean, here we essentially model something where we would need to store this budget for each manager project combination, right? I mean, those attributes of the relationships, they're essentially stored for each combination of the entities that are involved in the relationship. And if the VJ only depends on the manager, but not on the project, then this representation is redundant. So a better way to store that would be, for instance, this one over here. So here we represent managers as a specific type of employees that are associated with a VJ. So here the attribute is associated with the entity, not with the manager's relationship. And that is more intuitive and avoids redundancies here. Still, there would be probably, it would be good to introduce the specific budget for each project and make this an attribute of the manager's relationship. So that was a great point here. So here we have only taken care of the redundancy. So those are subtleties, but nevertheless, in practice, it would be very important to make sure that you choose the right representation. All right. Now, in order to get the hang of it a little bit, I wanted to make a little exercise to give you a couple of minutes. Try to draw an entity relationship diagram which describes the following situation. So we are modeling customers that have a unique ID in the name. We have orders that are associated with customers, and each order consists of at least one item. Where those items, they have also an ID, which is unique, a name, and a price. So I give you a little bit of time to draw one of those entity relationship diagrams for this situation. So just take a sheet of paper perhaps and try to model that. If there's any more questions about entity relationship diagrams, I'm happy to answer them here. No questions on entity relationship diagrams. Give you one more minute, then I'm gonna show you the solution. All right, let's quickly have a look. So here we introduce an entity type for the customers with the associated attributes, which is ID and name. ID is marked as a key by underlining it. Then we have a connection between customers and orders. And we also have an association between orders and the items. Items have the attributes that are mentioned in the description. And here the orders are connected to the items via a participation constraint. You have the SIG line over there, which means that each order must consist of at least one item, otherwise it is not a proper order. And since the part of a relationship connects specific orders and items, we might also have multiple items of the same type. And in order to model that situation, we introduce the number attribute. Also between order and customer, logically an order needs to belong to one customer, exactly one customer. And this is what the constraint here with the SIG line and the arrow is expressing. And here there's a question. Is there a way to do this with order being a relationship instead of an entity? Why not? So maybe one high level remark. So in general, there's always many possibilities to describe the same situation with entity relationship diagrams. So if there is a different solution from this one, it does not at all mean that that solution cannot be correct. So like when writing SQL queries, there's always many different ways to express the same query, or here express the same situation, and all of them can be correct. So modeling order as a relationship, I assume that would be a relationship connecting the customer with items. Okay. And then, yeah, I think you can also make that work. So you would have to express that each item needs to be associated with an order. Yeah, so, okay, I can see that. It depends on the specifics, but I believe that there's also ways to model this when connecting customers and items with an order relationship. And number, that is an attribute of the part of a relationship. So here, those relationships essentially can contain information about each order and item combination at most once. So if you want to model the case that we have multiple instances of an item in the same order, then the way to model that is to introduce an attribute which captures the number of items for each order item combination. And so this is what the diagram is essentially doing. So that is essentially the number of times that each item appears in an order. All right. So now we have learned the formalism to represent the database structure at the high level of abstraction, those entity relationship diagrams. Ultimately, our goal is to translate them into SQL commands for creating the associated tables. So in the following, we're going to see how we can translate those entity relationship diagrams into actual relations. And then for those relations, it is relatively natural to formulate corresponding SQL commands for creating those relations. So in order to represent those entity types, which appear as rectangles in the diagrams, we introduce a relation such that one entity corresponds to one row in that relation. And different properties of an entity are represented as columns of that relation. The underlined attributes, they become the primary key. For relationships, we can also introduce relations which essentially contain one row for each combination of connected entities. So the columns of that relation representing the relationship, the diamond in the entity relationship diagram, would essentially contain the primary keys of all the entities that the relationship connects. And then one row would represent the relationship between specific entities. If the relationship is associated with additional attributes, then those attributes become additional columns in that relation. Let's make things a little bit more concrete by an example. So here we have a relationship between students and courses. We are expressing that each student has exactly one favorite course. We have the net ID and the student name as attributes of the student, and we have the course ID and the course name as attributes of the course. And also this favorite relationship is associated with one attribute since. So for a specific combination of a student in a course, this attribute gives us the time starting from which the course became the favorite of the student. And now we can chat, and now we can express, we can translate this entity relationship diagram into relations as you see here in red. So the student entities, they get translated into a relation student, which has columns for the net ID and the student name. And the net ID is the key column, which when representing relations, we always represent that as well by underlining the corresponding column. On the other side, we have a relation, a course, which stores the courses, and again has course ID as a key column. And then the relationship between the students and the courses is expressed by this favorite relation, which has the net ID and the course ID as a primary key columns. So here this is essentially the combination of the primary keys of all involved entities. And also it has this additional column in order to store the since attribute. So here that is one generic way in which we can model relationships, so how we can translate them into actual relations. Here we can just add one corresponding relation, and the primary key columns of that relation just collect the primary key columns from all the involved entities. So we can store something about each possible combination of students and courses here. And then after I have those relations, it is relatively natural to formulate corresponding create table statements in SQL in order to actually get the database that this diagram is describing. Now, in the following, we're gonna discuss about how we can translate some of the other features of entity relationship diagrams, starting with subclasses. As a little reminder, subclasses essentially means that one entity type is a specialization of another entity type. So it may add additional attributes, it may have specific relationships, and it adds all of these on top of the attributes and relationships of the parent class. So in order to translate those subclasses and superclasses into a relation schema, there is multiple ways. For instance, I could just store entities of the subclass and entities of the superclass in separate relations. Also, I could introduce multiple relations for each of the specific attributes. Some of those attributes are specific to the subclass. Other attributes, they also appear in the parent class. So I could introduce separate tables for those attributes, and then I would insert rows only for entities of the class to which the attribute belongs to. Another possibility would be that I just say I introduce one single relation in order to store entities of the superclass and of the subclass. And if I'm dealing with entities of the superclass, they will not have all attributes for which the relation has columns, but that is maybe not such a bad thing. I can just set those corresponding entries to SQL null values in the end. Now, we will see an example on this in a minute. I believe there's a question. Okay, all right, great. So we're gonna see an example, I think, that will clarify things, but otherwise, please let me know, then we can discuss about that more. All right, so here we have a one entity relationship diagram with a subclassing relationship. We have managers, which are a subclass of employees in general. And the managers, they additionally have a budget that they can spend for their projects. So that is one additional attribute that is specific to the manager class. So we can represent this by introducing two separate relations. As you see here, we can introduce the employee relation, which stores the employee ID and the job title, and the manager relation, which stores employee ID, job title, and also the budget. So here you see the manager entity does not explicitly represent the emp ID and job title attributes, but they are implicitly included because we have the subclassing relationship represented by this yellow triangle with the is a label. So that here is a first possibility. We just store different entities in different tables based on their class. Another possibility is what you see here. So there is the job title attribute, which is common to all of those entities. And then there is the budget attribute, which is specific to entities of type manager. So what we could do is that we introduce one table to include all of the common attributes. Here that is the job title, and of course we always need to include the employee ID. And then we could introduce a second relation which only stores the manager specific attributes, which in this case is the budget. So that would be an alternative way to represent this subclassing relationship. And now for the last possibility, that is that we essentially only introduce one single table to store entities of both types. Now, the only challenge here is that if we are dealing with employee entities which are not manager entities, then we will not have any value for the budget. But what we can do in this case in our database is that we simply set the corresponding fields to SQL null. This represents that we don't have the corresponding value. All right. So I think it makes one table per class. So that I believe refers to the first possibility here. Okay, I see that was the answer to the other question. Okay, all right. So yes, so those are three different possibilities, either introducing one table per class or introducing tables for specific attributes which link the entity key, in this case employee ID, to the corresponding value for the attribute, or just one big table in which we collect everything. Then we will have a couple of holes, so to speak, in that table, which means fields that we set to null because those attributes do not belong to an entity of the corresponding class. So those are a couple of ways in which we can translate entity relationship diagrams with subclassing relationships into a relational schema. Is there any questions on this? All right. Then let's discuss a little bit about how we can translate weak entities. And as a reminder, weak entity is generally an entity which cannot stand for itself, but it belongs to another entity. An example that we have seen was, for instance, assuming that you have entities of type homework that have a homework number, but as long as you don't consider the course that those homeworks belong to, the homework number is not a unique key. So for a weak entity, it means that in order to obtain a unique key, we have to combine the partial key of the weak entity with the key of the owning entity, which in the homework example would be the course. So the way in which we represent weak entities in our relation schemata is that we introduce a new relation for storing those weak entities. And they have essentially a column that represents a foreign key reference to the key of the owning entity. If you implement that in SQL, then you also want to set specific constraints on those weak entity tables. In particular, if the owning entity should ever be deleted, then you also want to delete all associated weak entities. So if for some reason in your university database you have homeworks and courses and you delete the corresponding course, then all the associated homeworks should also be deleted because their foreign key references now point into the void. All right. And here there's a little bit more detailed example. It is exactly the one that I mentioned. We have homeworks which belong to courses. The homework itself has a homework number, but that is not a complete key. It becomes a complete key if you combine the homework number with the course ID. And here on the bottom of the slide, let me quickly rearrange something. On the bottom of the slide, you see the corresponding relation. It has a homework number and course ID, and both together form the primary key of that relation. We also have a grade mean for that homework. And if you want to represent that as SQL commands, then this is how you can do it. Here we are creating the table homeworks with the corresponding columns. We identify the homework number and the course ID as the primary key. And we specify that the course ID refers to another table storing the courses. And we have this little addition on delete cascade, which means that if somebody deletes the course that the homework belongs to, then implicitly the homework should also be deleted. Because otherwise, without the owning entity, those weak entities cannot really stand by themselves. So we should remove them in case the owner entity gets deleted. All right. So this is how we can translate some of the features of entity relationship diagrams into relation schemata for which we can find corresponding SQL commands for creating those tables. In practice, you might not always do this by hand. I mean, if you work on a serious project, then you use tools for those translations and also for drawing the entity relationship diagrams. So if you want to have a list of corresponding tools for Postgres, here you have a web address where you can find a relatively large list of tools. And the number of available tools already tells you that this is something which is done very frequently when it comes to databases. Some of those tools automatically translate your entity relationship into SQL statements. So if this is something that you want to do, I recommend you to pay attention to that, to ideally get a tool which does the translation automatically, but now you know a little bit what is going on in the background. One little caveat, the representation used for entity relationship diagrams, it differs a little bit across different books, across different courses. So be careful and make sure that you understand well what the semantics is of the elements. The representation might slightly differ from the one that we have seen here, while the concepts will most likely be the same. So those are tools that you can check out for Postgres, but there's also tools for other database systems, of course. Here, perhaps finally, one simplified entity relationship diagram of a popular database which stores information on music. And as you see here, so those are already significantly more complex than what we have seen in our examples. Also, the representation is a tiny little bit different, but the concepts are still similar. So this is just for showing you a little bit how that can look like in practice. And let me tell you that this is still a very simple database on the global scale of databases. So for other databases, it would be essentially impossible to parse the entire entity relationship diagram by one person. All right. So next, we will switch to talking about how we can optimize database schemata. So we will go away a little bit from entity relationship diagrams. Before doing that, I wanted to verify whether there's any questions on entity relationship diagrams. All right. So we're gonna continue talking about a database schema design. Now we are gonna talk about how we can optimize an initial draft of a database schema. We have seen this entire database design process where we discuss mostly about those 2 points in the middle, the conceptual design, which is drawing entity relationship diagrams, and the schema normalization, which we are about to discuss in more detail. So the goal of schema normalization is always to bring your initial schema into a more optimized form. And in the following, we are going to discuss in detail what we mean by optimized form. So this is what we are going to talk about, schema normalization, just the process of bringing it into an optimized form. The corresponding chapter in the Ramakrishnan and Gerke book, that is chapter 15. All right, so with entity relationship diagrams, you model what information you want to store in your database based on some use case analysis with whatever company or entity in general you are doing the database for. And then in the next step, you want to optimize the initial draft of the database schema. Typically, the first draft of the schema introduces a lot of data redundancy. And as we will see in more detail in the following, this data redundancy can lead to various problems. So the goal of schema normalization is to get rid of that redundancy up to a certain extent. So in the following, we're going to discuss about normalization. We will not finish that in this lecture, but this will extend to the next lecture. This is the high-level roadmap of what we will discuss about. In the first step, we will talk about functional dependencies. And functional dependencies are important because they are a way to indicate a redundancy in your data. And that is what we want to get rid of in normalization. So functional dependencies are important for that reason. Then we will discuss about normal forms. And a normal schema is in a normal form if it has certain desirable formal properties with regards to data redundancy. So we will see a couple of different types of normal forms which come with different trade-offs in terms of how much redundancy they still allow and which other properties they have. And finally, we will see principled algorithms that allow you to bring any initial database schema into one of those normal forms. So that is the high-level roadmap. We start by discussing about functional dependencies. Now, As already discussed, functional dependency allows you to detect redundancies, which is what you typically want to remove during normalization. A functional dependency always applies to one specific table, and it essentially states that the values in some columns uniquely decide the values in other columns. So if you use this notation over here, x, right arrow, y, it means that the values in x, where x is just a set of table columns, they decide the values in y, which is also a set of table columns. To be precise, I should probably say that functional dependencies, they can apply across different tables in principle, but for the purpose of normalization, we will care most about the functional dependencies that apply to one single table, meaning that x and y, those are sets of columns that are taken from the same table. All right. Let's make a little example here. So let's say we have again this university scenario, and we have a list of a table with TAs, and for each TA we have the name, the hours worked, simply distinguishing full-time or part-time, and the salary per, let's say, per week. So those numbers are not realistic, but let's use it as an example. So here we have one functional dependency at the bottom of the screen. It states essentially that the hours, the value in the hours column should imply the value in the salary column, which somewhat makes sense because when people work the same amount of time in the same job, then they should get the same salary. All right, so that at the bottom is a functional dependency where the two column sets that are referenced, they only contain one single column. In general, it could be multiple columns on both sides. Now, here we store information in the table, and we have a functional dependency which connects the hours column to the salary column. Can anyone tell me why that might be a problem? Representing the data in this way, having this functional dependency which links two columns in the same table. If you think about when you're working with the data, okay, there's some proposition. Yes, very good. Okay, very good. So here, the first suggestion is if we store things in this way, then we are wasting space, because here the number of hours already implies the salary. So as long as I know which salary correlates with what hours, I don't need to store the salary in each of those rows. Yeah, wasting space, that is a great point. Okay, very good. And here there's another proposition. What happens if we suddenly decide to be generous and change the salary of the TAs and give them 5% more, for instance? I mean, in this case, I would have to go through the entire table and change it everywhere, right? Yes, yes, also. I mean, if we update the hours that a TA works, for instance, somebody who initially only wanted to work part-time and then decides to work full-time. So here we would not only have to change the hours, but also the associated salary. Yes, so those are very good points. All of this is correct. So we covered most of the problems that I see in the scenario. Right. All right, and here that is a list of the problems that we could have, plus a space consumption. That's not even mentioned here. But the three anomalies that we typically associate with the scenario that is update anomalies, insertion anomalies, and deletion anomalies. And as you know from concurrency control, those anomalies are typically a bad thing. And here we have details what could happen. So here, for instance, if we update data, then if I only update the payment, for instance, for one TA, I could violate those integrity constraints. I could like get inconsistent data according to this functional dependency. Moment. Also, when inserting a new TA into the database, for instance, let's assume that all my TAs so far, they work part-time. And now I have a first TA who wants to work full-time. In that case, I would need some external knowledge source in order to know which hours to insert, which salary to associate with this TA based on the hours. Because in this table, I can only store salary for TAs that I currently have working. On the other side, it might be good to store somewhere outside the link between the number of hours and the salary. If I only have this single table, I cannot store any information about salary for job hours if I don't have a corresponding TA currently stored in the database. And related to that, there's the deletion anomaly. I mean, let's say I currently have TAs, some of them are working part-time, some of them are working full-time. And for those TAs, I therefore store the number of hours worked and the associated salary. And now I delete all the TAs which are working part-time, for instance. In that case, the information, which salary I was paying for part-time work would get lost. So I want to delete the information about TAs, but I don't want to delete information about the link between the hours and the salary. So those are a couple of problems that are linked to redundancy. The solution to that is the following. I simply put this information in two separate tables. Now here I have one table specifically for associating the number of hours worked with a salary, and I have a different table associating TAs with the number of hours worked. And as you can see here, this representation is better for multiple reasons. First of all, we have less space consumption. Second, if I now delete all the TAs which are working full-time, for instance, then it doesn't mean that I'm losing information which salary is associated with full-time work, because I still have it in the other table. And also if I insert a new TA which works here I have a part-time and full-time. If I only had full-time TAs and now I would insert a part-time TA, then I could look into the other table in order to get the salary which is associated with that number of hours worked. And of course, also, if I want to change the salary of the TAs working full-time, for instance, I can just change it once in this table on the right-hand side of the screen, and then I avoid any data inconsistencies because all the other TAs will automatically be associated with the higher salary. So this is how we resolve the redundancy. We decompose a table into different tables. All those normal forms that we see in the following, in the end, they come down to trying to be smart about how we decompose your initial tables in a way to reduce redundancy. This is the analysis of the example. We have already mentioned most of those things. The anomalies cannot really happen anymore. And here, what happened is that we still have the function dependency, but it doesn't connect columns in the same table anymore, but now it connects columns in different tables. So it becomes essentially harmless. One important point to keep in mind when decomposing tables is that you want, of course, to avoid data loss. What you need to be able to do is that if you essentially join those tables again, you need to be able to obtain the original table before the decomposition. Now here in this case, we have that because the function dependency states that the number of hours worked uniquely implies the salary. And then going back to the example here, that means that if we would join those two tables together via a natural join, meaning that we want the same values in columns that have the same name, which in this case is only the hours column. So if we join them together this way, then since the hours implies the salary, it means that for each row in the table on the left-hand side, I will find one single row in the table of the right-hand side that matches, that satisfies the join condition. So this is what we call a lossless decomposition, which is good because it means we're not losing any data. We can recompose the table in order to get the original data. But for storage, we decompose the two, which has all the advantages that we have discussed. All right. One little drawback about decomposition, we will also talk a little bit more about that later, is that in order to verify integrity constraints, or for some other operations, you might require more joins. So there's a little bit of a trade-off here. Joins are an expensive operation. We have seen all the different algorithms that people have proposed for them because they are typically the most expensive operation in practice. And if you decompose things further, it means you will potentially need additional joins at runtime. But nevertheless, the advantages are huge. This is why people often go for those normal forms. All right. Now, let's discuss a little bit more about a functional dependency. So now we have seen how we can do this in one specific example. In the following, we're going to see a more generic process to do that. All right. So in general, function dependency always states that the values in some column set X imply the value in some column set Y. As we have discussed, we have a redundancy if we have those functional dependencies that apply to the columns in one table. And here we store things multiple times that we essentially only would have to store once. So that is the thinking. This is why we have separated out the content, the columns that belong to the function dependency in the previous example. During normalization, we typically want to avoid function dependencies that apply to columns on the same table, and we achieve that by decomposition. So in general, for most of the normal forms that we see, we will try to avoid having functional dependencies that apply to columns in the same table. There's already at least one exception to that. Can anyone guess in which case it is acceptable to have functional dependencies that only link columns in the same table? In which case does it not indicate redundancy? In principle, there's multiple cases, but let's see if someone has a proposition. Okay, and this is actually, okay, that's a great remark. So, okay, very good points here, very good points here. Let me address already those. Okay, so here, one proposition is that if our function dependency, for instance, links hours to a salary, and let's say, for instance, I currently only store one TA in my database for full-time and one TA for part-time. Then we could say at this point in time, we don't really have redundancy in our table because values are only stored once. So that is a great point. In fact, the function dependencies may not always be associated with a redundancy. Now, the thing is that when designing the database schema, I typically don't actually know the content yet. So I try to design the database schema in a way such that I can guarantee that redundancy is avoided independently of which data I'm inserting in the future. So even if at some point in time the database would actually not contain redundancy, if I leave those columns that belong to a functional dependency together, I could have redundancy sometime in the future once people start inserting data. So that's one important point. We are going to discuss more about this. I fully agree that we might not always have a redundancy with functional dependencies. But when designing the schema, it's really about making sure that no redundancy can happen at some point in the future. So it abstracts away from the current database state. Nevertheless, I agree with that point. So there would be points in time where we actually don't have a redundancy depending on the content. Okay, and here another proposition, primary keys. Now that is a great point because functional dependency, basically a key constraint is a special case of a functional dependency. Because a key essentially says that if we have this set of columns here, then it will uniquely determine the the values in the other columns. So that is also a way of like one special case of a functional dependency. The key always means that if you fix values for the key columns, then you narrow it down to one single row in your data. And that is a special case of a functional dependency because here essentially fixing the values for the key columns immediately implies values for all the other columns in the same table. And so for key constraints, we cannot really have redundancy. Here there's some other. Okay, this is a very good point. So the amount of space that I'm saving, it would depend on like how many entries I have for each of the columns on the left-hand side of a functional dependency. Yeah, so that is true. But essentially, it also depends on which data I insert at runtime. When I'm designing the schema before runtime, then I might not necessarily know like how many entries I have for each value combination. But it is true, in the end, how much space you waste, it would depend on the specific content of the database. Absolutely correct. And here, when designing a database schema, we would nevertheless try to avoid redundancy as much as possible up to a certain extent in order to essentially make certain guarantees independently of what people later insert into the database. But I agree with that point, yes. Okay, very good, yes. So keys, primary keys, those are acceptable functional dependencies. Also, I mean, of course, if you think about trivial functional dependencies, for instance, like the TA name and the number of hours together imply the TA name. So that is a trivial functional dependency because here the set of columns on the right-hand side is a subset of the set of columns on the left-hand side. So that is always true. And there's no way to avoid those functional dependencies from holding within the same table. So that is also okay. We will see, we will classify those functional dependencies into some that are okay and some that are not okay in more detail later when we discuss about normal forms. But I already wanted to show you a little bit that not all functional dependencies are the same, and we might be more willing to accept some to hold in the same table compared to others. Now, functional dependencies allow us to detect redundancy in some cases, and we can try to decompose tables accordingly. But first of all, we have to find them. So one common mistake is to try finding functional dependencies by looking at the current database state if there is already a first version. Now, the thing is that functional dependencies, they must be guaranteed to hold for all possible data base states. Now, the data that you see at some point in time, it reflects the current state, but just because a functional dependency holds for the current data, it does not mean that it will hold after updating the data or after inserting more data or deleting some data. So you cannot really tell just from looking at the data. There's essentially two sources for getting functional dependencies that are valid. The first one is domain knowledge. If we design a database for the university and we know that the university has a policy that TAs get paid the same salary if they work the same number of hours, then I can integrate, I can translate this domain knowledge into a corresponding functional dependency for my schema. Also, after having some initial set of functional dependencies, I can use algorithms in order to infer more functional dependencies. So those are the two sources. There's like some seed functional dependencies derived from your domain knowledge, and then there's those automated processes which can derive more functional dependencies. How can we infer more functional dependencies? So this is what we mean by the notation on the left upper side of this slide. If you have a set of functional dependencies F1, then it might imply a set of functional dependencies F2, and we denote this as you see here. And what that means is essentially that any relation which satisfies the functional dependencies F1 must also satisfy the functional dependencies F2. There's a method to infer all possible functional dependencies. We can prove, even though we are not going to do that here, that with this method you find all functional dependencies, and all functional dependencies that you derive, they are actually implied by the seed functional dependencies. This method uses 3 axioms called Armstrong's axiom. And if you keep applying those 3 axioms, then eventually you will get all the functional dependencies that are implied by a certain set. Yes, first of all, reflexivity. I mean, that is that refers back to those trivial functional dependencies that I quickly mentioned. And here basically it just says that X implies Y. That's a valid functional dependency whenever Y is a subset of X. Example again from before, the TA name together with the hours implies the TA name. That's not very useful, but clearly satisfied a functional dependency. Then I have augmentation, and that essentially means that if X implies Y, then X and Z also implies Y and Z. For instance, we could say, now we know that the hours implies the salary from the previous example. So why not? We can also say that the hours and the TA name imply the TA name and the salary. Again, I mean, that doesn't seem very useful, but it is certainly true. And then we have transitivity, and that essentially means that if X implies Y and Y implies Z, then X will also imply Z. So if the TA name implies the number of hours, and if the number of hours implies the salary, then the TA name also implies the salary. Right, so those 3 relatively simple axioms actually allow you to infer all possible functional dependencies. The closure of a set of functional dependencies, those are exactly all the functional dependencies that you can infer, and this is what you would get when infinitely applying Armstrong's axioms. We also sometimes compare different sets of functional dependencies on the same database, and we say that one is a cover for the other one. If essentially the set of functional dependencies that you can infer from them is essentially the same. So saying that one set of functional dependencies is a cover for another set of functional dependencies is essentially saying that both of those functional dependency sets are essentially equivalent because it can infer exactly the same set of functional dependencies. The problem with those closures, with the set of functional dependencies that you can infer, is in practice they're extremely large. So it is quite impractical to deal with them. So we will see a method to narrow down the set of functional dependencies that we are interested in at any point in time a little bit later. Now, first of all, let's make a little example where we infer more functional dependencies from an initial set of functional dependencies. So here we have a set of 3 functional dependencies given. This is a set F. We know that the course implies the lecturer. The course implies the department, and the lecturer together with the department implies the office. Maybe the lecturer alone isn't yet sufficient because people could have the same name in different departments, but a lecturer and department, that should imply the office. Now, a couple of things that we can, for instance, infer here. For instance, we have the constraint course implies a department. Via augmentation, we can just add the same attributes to both sides of that functional dependency. If we add department on both sides, then we would get course and department implies department. Now, those 2 sides of the functional dependency, they have set semantics. So here, if I add department to the set which already contains department, it will just remain department. Now then we have a course and a lecturer implies department and lecturer. So here we have essentially added a lecturer to both sides of the second functional dependency in F. And we have course implies office. Now this one might be a little bit harder to see. So we're going to go a little bit more into detail there, how we can infer this one based on Armstrong's axioms. So here we have given those 3 functional dependencies marked up in blue. And now we infer the ones given in green. And at the very end, you see we infer the functional dependency that we are interested in, which was the one course implies office. So we will see how we can get there in multiple steps. So here we have a course implies lecturer on the, like that is the given one, number 1. And now we add course on both sides, which doesn't change anything on the left-hand side, but to the right-hand side, it adds course. So that is the augmentation axiom. Number 5. So now we have course implies course lecture. Okay. All right. So for number 5, we can use a number 2, which is course implies department. And here again, we can use augmentation and add lecturer to both sides of the functional dependencies. Then we get number 5, which is course and lecturer together imply lecturer and department. And now if you consider number 4 and number 5, then we can apply transitivity, because in 4, course implies course and lecturer, and course and lecturer implies lecture and department based on 5. So also course implies directly lecture and department via transitivity. And now we get a 6, and if you combine 6 with a 3 and apply transitivity again, then we also get the one that we were looking for, which is course implies office. So this is how one example how we can infer new functional dependencies using Armstrong's axioms. Any questions on this? All right. Now, we are at the end of our time slot. I already mentioned that functional dependency closures can be extremely large, so they're impractical to handle in practice. This is why next time we will start by introducing attribute closures, which narrow down the functional dependencies that we are trying to infer. In general, next time we will discuss in more detail about how we can exploit those functional dependencies in order to come to better database schemata with less redundancy. Have a nice day, and then I see you again on Wednesday. All right. Hello, everyone. Let's get started here. One little remark before we get started with the course material. I saw some questions about a previous material in the chat. I will answer such questions for a few minutes at the end of the lecture, but I wanted to get through with the material first. Otherwise, please always feel free to ask on Piazza. All right. So we have been discussing about a database design, and more specifically, we have been looking into how we can optimize an initial database design via normalization. And normalization is in particular about getting rid of redundancy. And there is multiple techniques that bring some unoptimized database schema into an optimized form. And we have been discussing a lot about functional dependencies last time, because functional dependencies indicate a redundancy that you want to get rid of by normalization. Later, we will discuss about normal forms, which are schemata that have certain nice formal properties. So this is something that we want to achieve. And then we will see normalization algorithms, which is essentially the technique by which we get to a normal form schema. All right. So we have been discussing about functional dependencies, and as a little reminder, functional dependency just means that the values in some set of columns imply the values in some other set of columns. So you write them, X implies Y, where X and Y are sets of attributes, and the semantics is that if you know the values in X, then you also implicitly know the values in Y. And if you have those functional dependencies within one single table, it means that you could store redundant information like here, and that has various disadvantages. The solution is to decompose tables such that functional dependencies do not hold within the same table anymore. And here we essentially resolve the redundancy problem. All right. So we have discussed about functional dependencies, and we have discussed that they indicate redundancy in most cases. One exception is if the functional dependency essentially states that knowing the value in key columns implies the values in other columns. In this case, you cannot have redundancy because in your database, you can only store one row with the same values in the key columns. All right. So at the end of the last lecture, we have started discussing about how we can find functional dependencies for a given database schema. What does not work is to try to look at the current data, because that only represents the current state. And even if it looks as if you have a functional dependency there, it might not generalize. So valid sources for functional dependencies is first of all domain knowledge. If you just know from your use case analysis that this functional dependency must hold, and based on some initial functional dependencies derived based on domain knowledge, you can infer more functional dependencies via algorithmic methods. Now, the last time we have in particular discussed about Armstrong's axioms, which are a couple of rules that allow you to infer new functional dependencies from given ones. And if you apply Armstrong's axioms often enough, then in the end, you end up with the closure for a given set of functional dependencies, which is essentially all the functional dependencies that can somehow be inferred from the original ones. Now, the problem with those closures is that they are extremely large, so it is typically impractical to try to calculate one of those closures. So now in the following, we're going to discuss how we can narrow down our scope a little bit and not try to infer all functional dependencies, but rather only infer functional dependencies that are based on the same attributes on the left-hand side, basically. So this is one way of narrowing down the scope. That leads to attribute closures. An attribute closure essentially tells you what are the attributes for which I can infer the values if I know values for this set of attributes. So we typically denote that with the plus sign. So if you have some set of attributes x, then x plus is the attribute closure for x, which means those are all the attributes for which you can infer values based on the values in x using the function dependencies that you have. Now, this essentially gives us some subset of function dependencies from the closure. For instance, we often want to check whether function dependencies which have specific attributes on the left-hand side, whether they can be inferred from given function dependencies. And the way to check on that is by using the attribute closure. Now, how can we calculate the attribute closure for a given set of functional dependencies? The algorithm is fortunately relatively natural. You see it here. And we essentially start with the attributes in x, because if I have given values for the attributes in x, then most certainly I can infer the values for the attributes in x from that. Then I keep iterating and I keep adding more attributes whose value I can infer based on the given attribute values. So the way we do this is that we iterate over all function dependencies, which are of the form A implies B. And if my current closure, meaning the set of attributes for which I can infer the value, is a subset of if it includes the left-hand side of the functional dependency, then I add the right-hand side of the functional dependency into my closure. So this subset sign should actually be the other way around. So if the left-hand side of the functional dependency is included within the current closure, then we add the right-hand side to the set of attributes whose values we can infer. Let's make a little example in order to make things more concrete. We have given the functional dependencies in F here on the top of the slide. And here we want to calculate the attribute closure of the attribute set A and E. All right, so this is represented as AE plus. And in the first iteration, we just start with exactly this set of attributes A and E. So after we iterate over the function dependencies, we will expand that set by adding attributes C and D. So let's see how that happens precisely. So during this iteration, we assume that we have given values for attributes A and E. So if we look through the function dependencies, already looking at the first function dependency, here we state essentially, if you know the value for attribute A, you can infer the value for attribute D. And since we know the value for attributes A and E, we know the value for A, and we can therefore infer the value for D. Now going further through the functional dependencies here, we see the last one, which essentially states that if you know the value for attribute E, you can infer the value for attribute C. And this is why, since we have given E, we also want to add C to our set of attributes that we can infer. So after this iteration, we know that we can infer the attributes A, C, D, and E, given values for attributes A and E. Now we're gonna iterate over the functional dependencies again, because we have just added attributes into our closure, and that might mean that now more function dependencies become applicable. So if we go through the functional dependencies again, this time considering that we are given attribute values for attributes A, C, D, and E, we can see that here we have the function dependency CD implies I. So if you know a value for attribute C and the value for attribute D, then you can infer the value in attribute I for the corresponding row. So because of that, we are adding I into the closure as well. All right. And so here we have expanded the attribute closure to A, C, D, E, I. Now, when going again through the function dependencies here, A, B implies E, but unfortunately we don't know B. BI implies E, but we have already E and we don't have B anyway. CD implies I, all right, already have that. And E implies C, we have that as well. So here, nothing really changes anymore by the next iteration. And this is how we know that we have converged. And now further iterations would not expand the attribute closure any further. This is why we can stop the algorithm. And now we have calculated the attribute closure. I believe there might have been a question. So exactly, yes, very good. So the question is whether this means that knowing values for the attributes A and E, we can infer values for attributes A, C, D, E, and I. That is correct. And here there's also the representation of the functional dependency. That is correct. So the attribute closure essentially gives you additional functional dependencies that can be inferred from the original functional dependencies. Yes. So based on what we see here in the attribute closure, we know that we have the functional dependency A and E implies A, C, D, E, and I, or any subset of that. So the attribute closure generally gives you a subset of the total closure with a specific attributes on the left-hand side. So yes, you are correct. Is there any more questions about the attribute closure at this point? All right, then let's continue. All right, before we go further, first of all, I want to show you that this is actually a pretty efficient algorithm. So here we have the algorithm again, and now we analyze the complexity. Here, for instance, the innermost command nested in those loops here, that one should have a complexity that is proportional at most to the number of attributes, because B is a set of attributes, a subset of all possible attributes, and adding those attributes to the closure should take a time that is proportional to the number of attributes, and also checking for one specific function dependency, whether its left-hand side is included in the closure. That also is proportional at most to the number of attributes. So this is relatively cheap, but let's see how often we execute that. Here we iterate over all function dependencies. So clearly the complexity is proportional to the number of function dependencies. And here finally, we have a loop that keeps iterating until convergence. But we know that for each function dependency in my function dependency set, it will only change the closure once, because if it has been triggered, meaning if the left-hand side of the function dependency is known, then we add the right-hand side of the function dependency into our closure. But that can only happen once for each functional dependency. And if we don't have any changes to the closure anymore, then we terminate our iterations. So because of that, I know that the number of iterations is limited by the number of functional dependencies as well. And taking everything together, I know that this algorithm is proportional to the number of attributes and quadratic in the number of functional dependencies at most. And so this is already reasonably cheap. And so just that you know there's also other algorithms that are even a little bit more efficient than that. So the attribute closure can be calculated quite efficiently. One way in which we can exploit the attribute closure is for calculating all keys of a relation. And when discussing about redundancy, we have discussed that function dependencies, they can be good or bad depending on whether they have a key on the left-hand side. So finding keys is generally important in order to assess redundancy. And this is an algorithm that essentially finds all keys for a given relation. So if we simply iterate over all attribute sets of that relation, we can check if it is a key by calculating the attribute closure for that attribute set. And we have a key if the attribute closure includes all attributes in the entire relation, because a key is essentially a special case of functional dependency where the left-hand side implies all the attributes in the entire table. And this is what we can check using the attribute closure. So this is one possibility to calculate all keys. As you see, the algorithm is, of course, more expensive, even though calculating the attribute closure is quite cheap. Here, this one iterates over all attribute sets, and their number is in general exponential in the number of attributes per table. So that is, on the other side, quite an expensive algorithm. All right. So, and just saying, typically, if you are trying to get to a normal form, which we will do in a couple of slides, you don't have to calculate all the keys in the relation via this method. Typically, there's ways in which you can more easily recognize which function dependencies are okay or not. But in principle, you could apply this one in order to get the full set of all possible keys, and that allows you to check whether function dependencies are okay or not okay. All right, so now we have discussed the functional dependencies. We have discussed a couple of corresponding algorithms which allow you to infer functional dependencies. And next up is our discussion of normal forms. And we say that a schema is in a normal form if in general it had certain desirable properties with regards to redundancy. And we will see some of the most common normal forms, but just so you know, there is more normal forms that are also used in practice. So here we are only going to cover the most important ones. One of those is the Boycott normal form, short BCNF. And in order to verify whether a given schema is in Boycott normal form, we have to do the following. So here in the following, I assume that you have an overview of which function dependencies hold for that schema, either because of the main knowledge or because they can be inferred from initial functional dependencies, and also assume that you can assess whether a function dependency refers to a key or not. All right, so we decide whether a schema is in Boycott normal form by going for each table over all the function dependencies which hold within that table. And for each of those functional dependencies, one of two cases must apply. And those cases is what you have here. A function dependency does not indicate a redundancy. First of all, it is a trivial function dependency. And a trivial function dependency is something like saying that knowing a value, knowing the name of the customer, and knowing the age of the customer implies the name of the customer. Or just saying that knowing the name of the customer implies knowing the name of the customer. So those are trivial functional dependencies. They always hold, and they don't specifically mean that there's any redundancy. So that is definitely okay. On the other side, function dependencies are okay if they represent a key constraint, meaning that the left-hand side implies all the attributes in the entire table. Key constraints are okay because for the same values in the key columns, I cannot store any two rows. So because of that, I know that there won't be any redundancy. And if for each functional dependency on a table, one of those two constraints applies, and if that holds for all the tables in the database, then the corresponding schema is said to be in Boyce-Codd normal form. So this is very strict about avoiding any redundancy. Okay, and here there's a question I see, whether a B is a set or a single value. Okay, great point. So in this case, we assume that we have normalized the functional dependencies and put a single value on the right-hand side. You can show that if you guarantee this for those functional dependencies, then it will hold in general. Okay, so very good point picking up on that. Yes, so here we essentially assume that we have a single attribute on the right-hand side. Let's make a little example to make things more concrete. We have a schema given on the lower side of the slide, and I have given you the short version of the definition of the Boyce-Codd normal form on the upper half of the slide. Here we have 3 tables in the schema, which have different subsets of attributes, and we are given the functional dependencies that you see here on the bottom of the slide. Does anyone want to tell me whether we might have a Boyce-Codd normal form here? So let's go through the different tables together. So let's start with table number 1, which has the functional, which has the attributes A and B. Does anyone want to make a guess about whether this table satisfies the conditions for Boyce-Codd normal form? Yes, very good. So A implies B is okay because A is a key for this table. So we have one of the 2 cases that we want. Very good. Okay. Let's maybe treat the third table before the second table because the third table has less attributes. It has only attributes as C and D. I believe there's a follow-up question in the chat. How do we know if something is a key in this example? Well, the definition of a key is that essentially by knowing the values for those columns, you can infer the values for all columns in the same table. And in this case, for table 1, we only have 2 attributes, which is A and B. And we are given a function dependency which says A implies B. And because of that, I mean, this is a function dependency that holds on the attributes of table 1. So we have to decide whether it represents any redundancy or not. But since here A is a key, it means that this functional dependency is okay. So this is implied by the functional dependency A implies B. And a key that always relates to one single table. So in order to be a key, it only has to imply the attributes that are in the same table. Great question. All right. Anyone has any suggestions about table 3? So for table 3, it's actually also, it's quite non-dangerous in a way, because here we only have 2 attributes. So if there's a functional dependency that is non-trivial, then it essentially must be of the type that knowing the value in one of those attributes implies the value in the other attribute. Because we only have 2 attributes, it means that in that case, it would have to be a key as well. So here, there is no specific functional dependencies. Quickly moving this. So there's no specific functional dependencies with C here. On the other side, D implies A and E, and A implies a C, so D implicitly implies a C as well, but here that makes it a key, and therefore we don't violate the constraints of Boyce-Codd normal form. And here, that was exactly the comment I see here. Yes, exactly. Yes, you're absolutely correct. D is a key here in table 3 because it implies C. Very good. Okay, so that table is also okay. Now, let's finally look at table 2. It has attributes A, D, and E. So anyone, any suggestions about that? Can anyone spot a key for this table? Okay, D applies A and E, yes, very good. Absolutely, so D is definitely a key. Is there any other keys? Very good, yes, exactly. So over a couple of corners, A also implies all the other attributes. You see here, A implies a B, and A implies a C, and BC implies D. So A implies a key, which means that it also becomes a key via transitivity. Yes, so A is also a key here, right? So also all function dependencies that have A on the left-hand side should be fine. All function dependencies that have D on the left-hand side should be fine. And here finally E. There's no real function dependencies which have E on the left-hand side. So here it seems that all the function dependencies are okay, and therefore this should be in a Boyce-Codd normal form. All right. Yes, exactly. So essentially, we are checking for all the functional dependencies that can be inferred from the original functional dependencies. Question was whether a Boyce Codd normal form considers the entire closure of functional dependencies, and yes, that is the case. All right. Now, the second or the third normal form here, but the second one that I'm discussing in this lecture here, that is the one that you see here. And that is another very commonly used normal form in practice. It is a little bit more permissive compared to Boyce Codd normal form, because here, for each of the functional dependencies, we require not 1 out of 2, but only 1 out of 3 conditions to be satisfied. And the first 2 conditions are exactly the ones that we have seen for the Boyce Codd normal form. So when going over all the functional dependencies that hold for a specific table, we say that they're okay if they're either trivial, or if the left-hand side contains a key, or if the right-hand side is part of some minimum key for the relation. And the minimal key is generally, it's a set of columns which forms a key. But if you take away any of those columns, then you won't have a key anymore. So this is essentially a key without any redundant columns added to it. All right. So again, the process to determine whether a given schema is in third normal form is to go over all tables. For each table, to collect the function dependencies, initial or inferred, doesn't matter, all the function dependencies which apply to the attributes of that table, and then to check for each of them whether at least one of those conditions applies. And if that applies for all function dependencies and for all tables, only then is the corresponding schema in a third normal form. All right. And a minimal key is generally a key which stops being a key if you take away any columns. So you have a set of columns which imply values for all the other columns in the same table. But if you take away any of those columns, then you cannot do that anymore. A key without any superfluous, without any redundant columns. All right. So this third condition is new compared to Boyce Codd normal form, and it allows a certain type of redundancy. So this is a very specific condition here. Of course, so one might wonder why people allow specifically this type of redundancy. And before we go into this, I'm going to tell you a little bit more about that on the next slide. But let's already make a little example for verifying whether something is in the third normal form. And here we have the same example again. So can anyone tell me whether that is in third normal form? Yes, exactly. Very good. So here the insight is that Boyce Codd normal form is essentially a restriction of third normal form. So if something is in Boyce Codd normal form, it also must be in third normal form, because if you compare the conditions, can quickly do that again. If you compare the 3 conditions of third normal form and the 2 conditions of Boyce Codd normal form, the first 2 are essentially identical. So third normal form is really just a little bit more permissive compared to Boyce Codd normal form. All right. So if we compare those normal forms, then, I mean, at first one could think that Boyce Codd normal form must be better because it allows less redundancy. And we have seen that redundancy has quite a few disadvantages. So that is the advantage of Boyce Codd normal form, that we don't have a redundancy anymore. On the other side, it also has a disadvantage because we have to break up our dependencies. And that means essentially the following. If you have functional dependencies, then you often want to verify that freshly inserted data satisfies those functional dependencies. For instance, in our original example, we had a functional dependency linking the number of hours worked by TAs to their salary. And if I would now try to insert a new TA into the database with a salary that is inconsistent with the number of hours worked, then I probably want to reject that update. And in order to verify whether that update is okay or not, in some cases, I might actually have to look at multiple tables, and I might have to join them in order to verify whether a certain functional dependency is satisfied. And the drawback of Boy's Codd normal form is essentially that I might have to decompose tables so far that in order to verify some relevant functional dependencies, whether they hold for new data, I might have to actually join multiple tables together. And as we know, the joins are expensive, and therefore we might want to allow a little bit of redundancy if it helps us to avoid additional joins. And this is exactly what the third normal form has been designed for, so to speak. It allows us to always preserve dependencies, meaning that I can verify functional dependencies without having to do any joins. And this slight extension of Boy's Codd normal form, you can prove, even if we are not going to do it here in the lecture, but you can prove that this allows you to preserve all dependencies. If you're interested in this, then please have a look into the book, into chapter 15. But this is the reason why we want to slightly relax the requirements of Boy's Codd normal form. All right, so those were already the normal forms that I wanted to introduce here, because those are two of the perhaps most popular normal forms used in practice. Now we're going to start discussing a little bit about transformation methods, and towards the end I can also take a few questions on some of the prior material. So the algorithms that we discuss here, their goal is essentially to bring some initial database schema into one of those normal forms. And the way to get to some of those normal forms, that is generally decomposition, and which is what we have already applied in our very first example, where we first had the TA name, the number of hours worked, and the salary in the same table, which caused problems. So we decomposed it into one table about TAs and the number of hours worked, and a different table which keeps track of the relationship between the number of hours worked and the associated salary. So the way to reduce redundancy is by decomposing those tables. One very important requirement here is that we want to decompose tables in a way that allows us to reconstruct the original data. We want to avoid redundancy, but of course we don't want to lose any data. And the condition in order for this to hold is the one that you see here. So let's assume I have some relation R, where R is essentially just the set of attributes that the relation has. And now I'm decomposing the set of attributes R into X and Y, and introduce essentially tables for storing those attributes in X and another table for storing the attributes in Y. Now X and Y, they might overlap, and if I take the union of them, then I need to go back to R. And I know that my decomposition is okay if I know that intersecting X and Y either implies all the attributes in X or all the attributes in Y. Now what that means essentially is that if I join together the two tables after decomposition again, and I require that the values are equal for those columns which appear in both of the decomposed tables. Then if one of those conditions here holds, it means that I can match each row in the table associated with X to exactly one row in the table associated with Y, or the other way around. So essentially, when intersecting those two column sets, then you need to obtain a key for one or the other of the two decomposed tables. In that case, if I do a natural join between the two decomposed tables, I will get back my original relation, which means that the decomposition is lossless. Now let's see a little example here. So here we have a slightly extended example from the one that we have originally seen. So here we have also added the office of the TAs. And again, I have this constraint that hours implies the salary. So here, if I have decomposed my table into those two tables that you see here, you see that there is some overlap between the columns of those two decomposed tables. The hours column appears in both of them. And if I do a natural join between them, what I will get back is this original table that you see over here, because the hours implies the salary. And that means that for each row on the left-hand side, I find exactly one matching row on the right-hand side. So if I do a natural join between them, then I get back my original table. Now on the other side, if I decompose like this, I store the TA name and the number of hours in one table, and in the other table, I store the hours, the salary, and the office of a corresponding TA. Now here, that is a bad decomposition because I cannot really uniquely link rows from those two decomposed relations together again. Because about each TA, I will only know how many hours that a TA works, but the connection between the name of a TA and the office is unfortunately lost. And if I would do a natural join between those two decomposed tables, then I would not get back the table that you have seen on the previous slide, but instead I would actually get back a larger table, which has lots of spurious rows. I'm essentially combining one TA with the office of another TA, which is working the same hours. So here I would essentially get back this table over here. Now, the name can sometimes be confusing. I'm calling it, or in general, it is called a lossy decomposition, but it actually means that if you would try to recompose things again, you would not get back less, but actually more than what you want. But that also means that information about which TA belongs to which office has been lost, and this is why we cannot get back our original data, which is bad. So this is how we want to decompose our tables. We want to make sure that we don't lose any data. Now, the next time we're gonna see in more detail how we can use this decomposition method in order to get to one of those normal forms with a principled method. Now, we have very few minutes left, so I can take a few questions on some older material. I think I had one at the very beginning. It was about when we release the logs of a transaction and how that relates to the commit time. So here the important point is that after you release the logs and before you commit, you cannot allow any other transactions to grab logs on those objects on which you have just released the logs if you want to be strict. Because the nice property of a strict two-phase logging is that we avoid those cascading aborts, which can happen if a transaction releases the log on an object early, then another transaction comes along and grabs a log on that object and reads the current value. Then the first transaction decides to abort. At that point, it would also cause the second transaction to abort. So in order to avoid that, you want to make sure that between the transaction releases the lock and commits or aborts. You cannot have any other transactions snatching the lock in between. So you want to get those two close together. Yes, exactly. And for snapshot isolation, you abort if there is a conflicting writes on the same objects. Exactly. And for the reading, all the transactions start from a certain snapshot, which doesn't change during the execution of the transaction. Sure. Any other questions on today's material, or also allowing some questions on previous material? Any questions on lossy versus non-lossy recomposition? Okay, seems that most questions were answered. All right, then the next time we're gonna see how we can get to some of those normal forms that we have outlined by using decomposition. We're also gonna make an end-to-end example for a database design, and then we are gonna start with new topics where we essentially look at systems that go away from those very traditional relational database management systems that we have so far been discussing. Have a nice day, and then I see you again on Friday. All right, let's get started here. And for the moment, we are still discussing about how to optimize an initial database schema. The last time we have been introducing normal forms, and the normal form essentially just means if a schema is in a normal form, it means that it has certain desirable formal properties. For instance, in particular, it avoids redundancy. And the last time we have been discussing about two of the most popular normal forms that are used heavily in practice. One of them is the boycott normal form, which you see here. We essentially test whether a schema is in boycott normal form by considering all functional dependencies, which means the ones that are initially given, as well as new functional dependencies that we can infer from them. And for each functional dependency that holds on a single table, we test and make sure that one of those two conditions here is satisfied. Either the functional dependency is trivial, meaning that the right-hand side is included in the left-hand side, or the functional dependency is a key constraint, which means that the left-hand side implies all attributes in the entire table. Because if any of those two conditions is satisfied, it means that we don't have any problems related to redundancy. So this is the boycott normal form. It is quite restrictive. If none of those two conditions is satisfied for at least one functional dependency for at least one table, then boycott normal form does not hold. We have seen a slightly more permissive normal form, which is the third normal form. And it is slightly more permissive compared to boycott normal form because here we allow one additional case, which is the third one in this slide. We also consider functional dependency as okay if the right-hand side is part of some minimal key of that relation. And the minimum key, it is essentially a set of attributes which imply all attributes in that table. But if you remove any of those attributes, then you do not have a key anymore. That is why the key is minimal. So the third normal form is a little bit more permissive. And the reason why we want to be a little bit more permissive is that the third normal form can always be achieved by preserving dependencies. Dependencies, those are essentially those functional dependencies. And if I want to verify that those functional dependencies are satisfied as integrity constraints, if I have a dependency preserving normal form, it means that in order to verify all relevant dependencies, I only have to consider single tables, but I don't have to start joining tables in order to verify anything, because that would be expensive. So those are two different trade-offs between how much redundancy we are willing to accept and how efficient checking constraints can be, and whether it requires joins or not. So those are the two normal forms that we have seen, and we have also quickly started to discuss about how we can get to any of those normal forms last time. The key technique in order to get to one of those normal forms, that is decomposition, because those normal forms, they only require that conditions are satisfied for function dependencies that hold within the same table. So if we keep decomposing those tables, then we have to worry about less and less functional dependencies. We want to be careful when decomposing those tables, because we want to decompose them in a way such that we can still reconstruct the original data. This is what we call a lossless decomposition. And here we have essentially the condition for lossless decomposition. If I have a relation R, which is at the same time like a set of attributes, and now I decompose R into two relations X and Y, where X and Y are essentially the attribute sets of the new relations. And in order for this decomposition to be lossless, I must guarantee that if I do a natural join between X and Y, then I get back the original content of the relation R. And that is the case if one of the two conditions on the bottom of the slide is satisfied. If when intersecting X and Y, I get something that implies X, then I'm okay. Or if by intersecting X and Y, I get something that implies Y, then I'm also okay. What this means essentially is that if you only take the join columns of the natural join, then you get a key for one of the two decomposed relations, X or Y. And that means that one row on one side matches with exactly one row on the other side. And in that case, you know that you will get the original relation back if you join those two decomposed relations by a natural join. So I'm going over this relatively quickly. It's a reminder. Those are things that we have discussed in a little bit more detail last time. Now, we have also made a little example for a lossless decomposition. I'm not going to go into it in too much detail, but I encourage you to have another look at this example. So here we have decomposed the things in a way that we can reconstruct the original relation by a natural join like this. And here we have decomposed things in a different way, which does not allow us to reconstruct the original relation. Here, if we do the join, and we get something which is actually larger than the original relation because it contains more rows. And that means that we have lost information about which TA in this case is associated with what office. So we can use decomposition in order to come to a normal form. This is how we get to the Boycott a normal form. The algorithm is relatively short. Essentially what we do is that we keep decomposing tables until we get to Boycott normal form. Whenever we want to check whether something is in Boycott normal form, then we iterate over functional dependencies and check whether they hold for specific tables. And if we find one functional dependency of the form A implies B, where A is an attribute set and B is a single attribute, and if we find this to violate the rules of Boycott normal form, then we decompose the corresponding relation R, as you see here. We decompose it into two new relations. The first one has essentially the same attributes as R, just that we take out B. And the second relation that we achieve by the decomposition, it includes the attributes in A and additionally B. So this is the rule for a decomposition. And we know, first of all, that this decomposition will be lossless, because if you do the math, if you intersect those two relations after decomposition, if you intersect R minus B and AB, then in the end we get A. And as we know, that implies B. Therefore, by intersecting the two decomposed relations, you obtain a key for the second relation, which is AB. So here we know if we apply this rule, then the decomposition must be lossless. So that is the first desired property of the algorithm. Now we could wonder whether this algorithm will ever terminate. It will, because whenever you decompose a table, it gets smaller. At some point, you must end up with atomic tables, basically. And also, since we decompose whenever a function dependency violates Boy's code normal form, and after this decomposition, you see that the function dependency that caused the problem does not apply to any of the decomposed tables anymore. So this decomposition essentially fixes the problem. And once we terminate and do not decompose anymore, we therefore know that we must be in Boy's code normal form. Otherwise, we would continue decomposing. One remark about this, the end result might actually depend on the order in which you consider your function dependencies. So in the following, if we make examples about how we get into Boy's code normal form, for instance, please keep in mind that multiple solutions to those examples are generally valid. It depends on how you order the function dependencies. In the end, all that matters is that we are in Boy's code normal form. So for a given start schema, we could have multiple equivalent schemata that are in Boy's code normal form. All right, so this is the algorithm for Boy's code normal form. We essentially just keep decomposing using this rule until finally no function dependencies violate the rules of Boy's code normal form anymore. Is there any questions on this? All right, good. So then let's make a little example. You can also find this example in the book. Here we have given a schema simply as a collection of attributes. We assume that we have one relation which includes columns called C, S, J, D, P, Q, V. So I'm not gonna go into detail with regards to the semantics of those columns. For the example, it doesn't matter. If you're curious, in the book, you'll find more details. This essentially refers to a scenario where we store information about a project. For the example, you only need to know which attributes are contained in the relation. You have given that attribute C is a key for this relation, so it implies all the other attributes in this relation, and the attributes J and P together imply C, attributes S, D together imply P, and J implies S. So as a little exercise, I invite you to try bringing this into Boy's code normal form. I give you a few minutes. Use the decomposition method that we have just seen. And while you are looking into this, I'm going to have a look into the chat because there might be some questions. Okay, very good question and reply. The question was where we get the initial functional dependencies from, whether it's the full closure or whether it is some kind of attribute closure. So in general, you need to consider the full set of functional dependencies, and that includes the ones that you can infer from the original functional dependencies. So typically, it is not necessary to think about all possible functional dependencies, but in a given scenario, when looking at the tables and trying to decide whether you need to decompose them further, then you can sometimes apply actually attribute closure in order to find out whether specific functional dependencies are relevant to you. But conceptually, you have to consider all functional dependencies that can be inferred from the original ones. So if you're given a set of functional dependencies, it's not the full set of functional dependencies that holds, but you might also have to infer new functional dependencies from them. Right, I give you another minute. So even if that might not be enough time to fully finish the example, at least have a look and think about how you would get started with this. Any more questions on the material that we have covered so far? All right, let's have a look at the solution here. So we have given this schema and, and we have given constraints. So first of all, looking at those function dependencies that are even immediately given, you already see that some of them violate the boycott normal form constraints here. So a first function dependency is SD implies P. And so first of all, this is not a trivial function dependency because the right-hand side is not simply a subset of the left-hand side. Also, SD does not seem to be a key. We can infer P from it, but after that, it doesn't propagate further. So here we have something which is neither a trivial function dependency, nor is it a key. And this is why it violates the constraints of boycott normal form, and we have to decompose. So here we decompose into two relations. So first of all, we have to take out the left-hand side of the function dependency from the original relation. Then we get one of the two relations after decomposition, or precisely we get the attributes that must be included into that relation. And also we have a second relation which simply combines all the attributes from the function dependency, S, and P. So here you see the two resulting relations after the decomposition. So in the original schema, we had one relation. Now we have decomposed it. And so we have replaced it by two relations. And yes, very good question. So the next functional, so one functional dependency that we don't have to worry about, for instance, that is JP implies a C, because C is a key, and that means via transitivity, JP is also a key. So yes, going through all of those functional dependencies, we have given that C is a key, so that is nothing to worry about. We have that JP implies a C, so JP is also a key, so nothing to worry about. We have just taken care of SD implies P, and then we also have a J implies a S, and that one would also be problematic. So after the decomposition, we essentially go through all of the functional dependencies again, and now we have taken care of the first few, but the last one, J implies S, this one is still not okay. This is why we decompose things further. So in one resulting table, we have simply the attributes from the function dependency causing problems, which is J and S. And in the other part of the relation, we have the attributes from the relation that we are decomposing minus the left-hand side. So here, after the first decomposition, we end up with two relations, SDP and CSJDQV. And here, when comparing against the functional dependencies, maybe I make that in a little bit more detail. So when comparing, when analyzing SDP, that relation, then there is only one functional dependency that has its attributes only from that relation, and that is SD implies a P, but this one is a key for this relation. For the right functional dependencies, we have that C must still be a key. JP implies a C. That one does not have the attributes only in the second relation. And J implies S. That one still has all attributes in that second relation, and it is not a key, and therefore we need to decompose the second relation further. And this is what we are doing here in this step. We are decomposing it into the two relations JS and chat and CJDQV. And after that, we have obtained three relations by two decompositions. And if we compare them against the functional dependencies, we find that all of them are either a key or they don't apply to attributes of one single relation. And this is why the resulting schema is in Boyce-Codd normal form. All right, so this is a relatively small example. Also note that we could have gotten to a different Boyce-Codd normal form if we had started initially by considering the function dependencies. J implies S, but in the end, all that matters is that we get to some Boyce-Codd normal form, and if we keep decomposing, then that will happen. All right. Good. Any questions on this? All right. Good. So one thing that the Boyce-Codd normal form cannot guarantee is that we preserve all dependencies. So dependency preservation, I've already quickly mentioned what it is intuitively. So here you have a little bit more details. So in general, assume that we decompose a relation R into relations X and Y, where those letters essentially designate the attributes of the corresponding relations. And now assume that we verify functional dependencies only on the relations X and Y separately. So we enforce all functional dependencies that can only be checked by using attributes from X, and we check all functional dependencies that can be verified using only attributes from Y. And if by enforcing those functional dependencies on a separate relations, we have implicitly enforced all functional dependencies that held initially, then we say that the decomposition was a dependency preserving. I believe there might have been a question. Okay, yes, very good question. So in a way, the point is to break up dependencies that violate constraints, that don't comply with the constraints of Boy's code normal form. And you are absolutely correct that dependency preservation is somehow at odds with trying to decompose things as much as necessary in order to avoid any redundancy. So that is totally the right insight here. And that is exactly the reason why people are willing to relax the constraints of Boy's code normal form, because it is indeed sometimes at odds with dependency preservation. So a third normal form is kind of a compromise where you decompose as much as possible without running into dependency preservation problems. So dependency preservation still allows you to break up some inferred functional dependencies, as long as you can still verify enough functional dependencies on the two resulting relations. But you're absolutely correct that it is at odds with trying to decompose as much as necessary to avoid redundancy. That is the compromise. Boy's code normal form does not guarantee dependency preservation. The third normal form that you have seen does. And in the following, we're going to see an algorithm which allows you to get into third normal form by preserving dependencies. Yes, so that is totally the right insight here. All right, and here a little summary which connects to what I was just saying. So we have seen two properties for decompositions. We have them lossless, and we can have them dependency preserving. Those two properties, by the way, are independent from each other, so none of them implies the other one. Boy's code normal form may lose dependency preservation, while it, on the other side, removes any redundancy. The third normal form preserves dependency preservation. It preserves dependencies, and under that constraint, it tries to get rid of as much redundancy as possible, basically. And all of those normal forms, they only use lossless decomposition, so you can achieve them using only lossless decompositions. So in the end, you're not losing any data. But that is the compromise of third normal form. It might still allow some redundancy, but in exchange, it allows you to preserve dependencies. This is how we get into a third normal form. So here we essentially do something quite similar to the process for Boy's code normal form. The only difference is that in order to preserve dependencies, we might actually choose to add new relations. So whenever we have a dependency of type A implies B, which is broken by the decomposition, then we simply add a relation A implies B into our database schema. In order to make this work well, it is important that we use the right set of functional dependencies for our analysis. We have to use something called a minimal cover of functional dependencies, which essentially means that on the right-hand side of each functional dependency, we only have a single attribute. And if we delete any functional dependency from our set, it changes the closure, meaning the set of functional dependencies that can be inferred. Also, if deleting any attribute from any functional dependencies left-hand side, it will also change the closure. So this is essentially a set of functional dependencies where every functional dependency and every attribute is necessary. And if we have computed that, then we can use it in order to decide which relations we want to add during the decomposition. So we are not going to go into detail in terms of how we calculate, for instance, the minimum cover. This is, if you're curious, there's an algorithm given in the database book. But on a high level, this is how we achieve a third normal form. So the only difference to Boy's code normal form is that we might decide to add, so to speak, not really redundant, but we might decide to add additional relations that contain attributes that also appear in other relations. And after we have added them, they allow us to check certain functional dependencies without breaking them. So here we simply add new relations which allow us to verify functional dependencies without having to do any joins. So this essentially concludes the chapter on a database design. We have seen how to draw entity relationship diagrams, how to translate them into schemata, and how to normalize the resulting schemata. The next time we will start discussing about database systems which expand traditional database systems in one way or the other, starting with distributed database management systems. I wish you a nice weekend, and then I see you next week. So, hello everyone, welcome back. I hope you had a nice Thanksgiving break. So we will continue discussing about database systems, but now we are looking at different data types for a change in this and in the following lectures. So far, we have been mostly discussing about tabular relational data because that's a very common data format used in practice. But there's a couple of other data formats for which people have developed specific specialized systems, and we are going to discuss about some of them. In particular, we're going to discuss about graph data. Today, we are going to discuss about data streams, and we are going to discuss about spatial data and about systems that have been designed specifically for those types of data. Now, today we're going to start with graph data. And here is a reading list that connects to some of the things that we will discuss, so that is not necessarily covered by the course book anymore, but here you can find more details on the topics that we are about to discuss. So a graph is generally a collection of nodes and edges connecting those nodes. So often those nodes will represent things or persons, and those edges will represent relationships between them. Those nodes and edges can often be associated with labels. Often that corresponds to something like a node type or a relationship type. And additionally, you can often associate them with properties which give you additional information about the entities or about the relationships. This is a simple example graph over here. In blue, the circles are the nodes, and here with the column are I'm representing labels. So here we have two nodes labeled as students, then a course node and a university node. And in green, you have those additional properties for the nodes. So here we have two students, Mark and Maria, which are apparently enrolled in the CS4320 course. And on the right-hand side, we have the Cornell University node, which offers the CS4320 course. So that is a very simple example. You have nodes, edges, and properties and labels. Now, this is a little toy example, but in reality, we have nowadays a lot of data sets that are natural to represent as large graphs. If you think, for instance, of social networks, of a knowledge graphs like the Google knowledge graph, of communication graphs, of road networks, and so on and so forth, in many cases, it is quite natural to think of that data as a graph. Here, for instance, we have a representation of a communication graph here. Nodes represent servers on the internet, and the edges represent connections between them. Or here we have a representation of the Facebook graph. So here nodes correspond to people, to profiles, and edges correspond to connections between those profiles, and you can represent it as you see here. Or here, slightly less mesmerizing, but very practical, we have a graph representing the NYC metro network. So in this case, we would have nodes representing metro stations here in Manhattan primarily, and the edges correspond to direct connections between those metro stations. So now I have marked up two locations on that map that I will use as an example here. We've marked up the Port Authority bus terminal. This is what we would arrive to when coming by bus from Ithaca, for instance. And here I have marked up also NYU, New York University. And maybe at some point when things open up again, then I might want to visit a colleague there at NYU, and then I might want to find out how many paths connect the bus terminal to the metro station at NYU. And in the following, first of all, let's think about how we could solve this problem, like showing all the possible connections with a relational database. The first thing we need to do in order to use a relational database is that we represent that graph as a relational database. Does anyone have a suggestion about how we could represent this graph, or perhaps graphs in general, inside of a relational database system? Yes, very good. Mm-hmm. Yes, very good. So here, yes, yes, very good. Okay, so thanks, that is correct. So here I have multiple correct versions. So we probably want to introduce a table to store the nodes and another table to store the edges, which has perhaps some foreign key references to the nodes. So in this case, that could be one table with stations. Here the station ID is the primary key, and then each station has a name. And then a table connected, so those are the edges. This table references two nodes from the stations table via foreign key references, and the primary keys, then the combination of the two connected stations. So in this way, I could represent this graph relatively conveniently in a relational database. Now, what I want to do is to find all possible connections between those two specific nodes in my graph, having stored the data in my relational database system. Can anyone suggest a query by which I can calculate those connections using the SQL features that we have seen so far? have this table with the stations. We have this table with the connections between stations. Maybe if you think about how you can find paths of a specific length, for instance. In the end, we are interested in paths between two specific nodes. So we somehow might have to combine multiple rows from the connections table. Well, if I, for instance, want to find out from one specific node which are the other nodes that I can directly reach in one step, then I have that information directly in the connections table. Now, if I want to expand that and find out all the nodes that I could reach in 2 steps from some initial node, any suggestions about how we could proceed? Okay, very good. All right, here that is the, yes, that is correct. And here the perfect keyword in there, that is a self-join. That's what I probably want to do. So I need to use the connections table multiple times because it will be searching for paths that have multiple steps to them. So this query here gives you the template. So I have those self-joins between the connected table where I'm always making sure that I connect the second station in the last instance of the connected table to the first of the 2 stations in the next instance of the connected table. So this whole thing forms essentially a chain of joined tables. And then finally, I just have to make sure that I'm starting from the port authority node by putting the corresponding restriction into the where clause. And the final node that I want is NYU. I can also put that as restriction into the where clause. So, and if I join this connected table a fixed number of times, then I get paths of a fixed length, and maybe initially I don't know how long the path can be, so I could just iterate and take the union over this query with a different number of connected tables, right? So this is what I could do. Is there any questions about that representation here? All right. So as you see, okay, very good. So if you really want to use a relational database system, in this case, then yes, we could use something like a loop with a stored procedure or with some surrounding software which issues multiple queries. There's also a couple of more advanced SQL features which would resolve this more elegantly. But this is mostly to show to you that maybe using traditional relational interface, using the SQL features that we have seen so far in this scenario might not be the most elegant way to go about it, right? Because here already I have they have a lot of joins here that I would have to symbolize, and I might have to repeat that with a different number of joins in order to get paths of a different length. So it's not ideal, let's say. So the intermediate conclusion here is that we can generally represent graphs in a relational database management system, but using the SQL commands that we have seen so far, it's not exactly convenient to ask queries like the one that I have shown before. And that means that there's potential for specialized query interfaces that are targeted at graph data. And also, we will probably discuss about that more in the following lecture. Perhaps there's a couple of ways in which I can change the design of my system in order to make it more efficient to process graphs in particular. So there's a couple of motivations why we might want to look at systems that are specialized to graph data. And there have been quite a few systems proposed. Here you see logos of some of those systems, but that's only a subset. Now, those systems use a slightly different query languages, and they have slightly different functionalities, but all of them are targeted at graph data. And in the following, we're going to look at one of those systems in more detail. That is the Neo4j system. It's one of the most popular systems, but that's not to say that those other systems aren't great as well. So this Neo4j system, first of all, has a specialized query language specifically for graphs. And in the following, we're going to discuss more about that language. So the name of this language is Cypher. And this language allows you to do things such as creating or updating nodes and relations in your graph, to search for specific patterns in your graph, doing things like aggregation, filtering, that supports subqueries, and so on. So in many ways, this language is somewhat inspired by SQL. You will see some common points, but it is specialized to graph data. So in the following, I'm gonna show you a couple of examples for how you can use this language. Later, we will also see a little demo with the Neo4j system. So the first thing that you probably want to do when working with that system is that you want to create a graph that you can work with. And here you see some commands for creating nodes in that graph. So in the most simple version, you can create one anonymous node with the create command, and nodes are always represented between those round parentheses here. So the first command here just creates an anonymous node without any labels or properties. The second command here specifically creates a node labeled as a student. That's always marked with this colon symbol followed by the label, and that typically represents something like the node type. The final version is more expressive and additionally adds a property to the node, which we have between those special brackets. And here we essentially attach the property name with the value mark to this student. So that creates a node probably representing a student called Mark. Now, in the following, I'm going to show you how we can add edges, relationships to your graph. Before we can do that, we have to learn how to identify specific nodes in our graph so that we can tell the system between which nodes we want to add an edge. So if you are searching for a specific node, you can do it, for instance, with the command that you see here. Here, I'm asking the system to match nodes of label student and having a property name with value mark. And I'm asking the system to match such nodes to the variable m. So m is what you have here before the colon symbol. And if we use the match command, we ask the system to match this pattern here to the variable m, and then I can use variable m in the remainder of the query. So here, for instance, I want to create a relationship, an edge between the student node Mark and the CS4320 course node. So what I do here is, first of all, I match variable a to a node of label student with property name set to mark, and variable b to a node of label course with a name property set to CS4320. And then following that, we have the create command. So here we create a relationship between those two nodes. We have A, the variable from before, and B, the other variable from before. And now I'm creating a directed edge from A to B. So this notation is relatively intuitive. You see that the edge is represented by essentially a little arrow in ASCII representation. Also, we have given a label to that edge, which you have between the square brackets. Those edges can also have labels. Here, we label the edge as enrolled, and the semester property is set to fall semester 20. So this matches the two nodes that I want to connect, and then it creates indeed a connection between those nodes. If you have any questions about this, then please don't hesitate to ask them in the chat. All right. If you have created nodes, then you can also change them later. Of course, you can update nodes. So for instance, here, first of all, you're telling the system which are the nodes that we want to update. Here, I want to update the node labeled as student with name property set to mark again. And here I can, for instance, change the label of that node. Perhaps a student finished the studies, and then I can set the label to alumnus rather than a student. That's what the first command is doing here. Also, maybe there was a name change, or I got the name wrong the first time, so I might want to adapt the name property. So the second command searches again for that same student and now sets the name property, which you write with the variable name dot and then the name of the property. And here we set that to Marcus instead of Mark. So I can also update relationships. Before we can update the relationships, we first have to find the corresponding relationships. Okay, and here's some interesting questions. So you can batch updates to nodes. In any case, if you write a matching expression, then the update will refer to all nodes that satisfy this matching expression, right? And generally, nodes can have multiple labels, but if we reset the label, then it will override the old labels. Okay, very good. So the difference between a label and a property is the question. So a property always gives you essentially, it has two types of information. I mean, you have the name of the property, and then you have the associated value of the property. A label consists only of the label name, basically. So the way it is typically used is that the label indicates something like a type of a node, and the property gives you some additional information. So here, for instance, in order to express that some node represents a student, it is natural to use a label because we don't need any additional information beyond that. But in order to assign a student to a specific name, we probably want to use a property, as we can also assign a value in this case. So yeah, typically labels used for expressing types and properties used for expressing additional information about a node or about a relationship. And if we reset the label, we will not delete the existing properties? Great questions. All right, good. So please feel free to add more questions in the chat here. All right, so the next thing that I will discuss here is how we can update relationships and edges. And the first thing we need to do is to find the relationships that we are interested in. And I can also do this with the match expression. So here I'm searching for relationships that connect this node of type student with a name property equal to mark to a node of type course with name property CS4320. And I want them to be connected by a relationship of type enrolled with the semester property set to fall semester 20. So we are talking about the current semester. As you see, I can also assign a variable to one of those edges, here E, and then I can use that variable to refer to it later. So here in this matching expression, I'm asking the system to assign 3 variables for me. The first representing student mark, the second representing course CS4320, and the third one representing the connection of type enrollment between the student and the course. All right. And now in the following, I'm gonna use this matching pattern to find those edges. And now I can, for instance, update the semester because now time has passed perhaps. So I can update the semester to fall semester 21 instead, for instance. And I'm also gonna do this with the set command. I think there's one more question in the chat. All right, how does Cypher deal with nodes with the same properties if there is 2 students named Mark? That is totally possible. And with the syntax that I have shown you so far, it would essentially mean that a variable is assigned to a list of possible matches. And if you do something with those matches, if you, for instance, update them, or if you delete them, or if you just want to show them, then that would happen to all matches. So if there's multiple students with the same name, then you would match all of them. Okay, and here a very, very good question. The question is about the nature of the relationships, because indeed we have seen a slightly different syntax, very good observation. So in a graph, you typically have directed and undirected edges. So in Neo4j, the database needs to contain directed edges between nodes. So if you have, for instance, created the relationship here, as you see here, we have made a little arrow between node A and node B. Here at the end of the command, on the right-hand side of the line, you see this arrow representation. So this is specifically an edge that points from node A to node B. Now, on the other side, when we were searching for edges, and that's a very good observation, here we didn't use any arrow in this expression. And that essentially means that here we are not making any restrictions as to in which direction the 2 nodes are connected. We could do this if we want to, but here in this case, we probably only have connections in one direction. So this representation, this notation without the final arrow tip, it means that we are looking for connections into both directions. Good observation. Yes. But if you're creating edges, then you always have to indicate the specific direction. If you're searching for relationships, then you can leave out the direction, and then you will find connections in both directions. But when creating them, you have to say which direction it should be. Good. All right. So here, the last thing that we have seen is how we can update a relationship. We can also delete things, of course. So here, for instance, we're asking the system to match variable A to all students in the database with name Mark. So that could be multiple students indeed. And for each student matching this expression, I want to delete the student, right? And I can do so in a similar way for edges. Now, in order to make this more concrete, I'm going to show you a little demo for how using the system looks in reality. Let me quickly share the other window. Okay, and here one more question, whether it's possible to only match a node using an edge but not specifying the property. Yes, absolutely. You don't have to specify any properties during the matching. You can just match nodes based on their connections, for instance. So yes, having properties in the matching expression, that is optional. All right. Good. So here I'm on the website, and if you want to try that with the examples that we have in the slides, then you would go to get started here. There's an online sandbox that we can use here, so you don't necessarily have to install anything. And here we have, for instance, a blank sandbox, which allows us to play starting from an empty data set. Now it's loading the interface. All right. And here we are. So now we can enter those commands that we have seen before into this little query box over here. So perhaps let's first of all create a couple of nodes. Here, this is the simplest version of it, which creates just one anonymous node without label and without properties. All right, and here I'm getting some feedback. It has succeeded. Now let's maybe replicate some of the examples that we have seen. So here we are creating a student called Mark, for instance. Right now I've created that. And perhaps another student. We are, and now I can create. I can create a course, for instance. So I'm pretty much following the example that we had in the slides to see how that works when actually entering it. Right, and now perhaps I want to create a relationship between the student and between the course. So we first have to match that. I ask the system to match students. Let's actually say all the students to variable s. And here I'm matching to variable c nodes of type course with name equal to CS4320, which would not be necessary here because we don't have any other courses in the database currently. Now we are enrolling everyone into CS4320. Right. Okay, here you have a little warning. Right, that is fine. Right, and now here we have created two relationships which has essentially assigned both of the students to the corresponding course. And we're gonna see a little bit more commands in the following, but here you see a little bit how the interface would work. And now perhaps let's clean up again, and we can delete the students again. And we had before the question, what happens if my matching expression matches multiple elements in the database? That is the case here, for instance, because I'm not fixing the name. We also had the question about whether we need to fix properties in the matching expression, but we don't need to do that. And here I'm simply matching all students, all nodes labeled as student in the database to the variable s, and I'm going through them and delete them. Now, if I execute this command here, it actually will not work because those students are currently in a relationship. And if I want to delete the nodes, I would have to delete the relationship first. So this should not work. If I try it, I get this error over here. So the first thing I would need to do here is to delete the corresponding relationships. So here maybe I'm matching relationship E to connections between students and courses. And now I'm deleting those relationships here. Right, and now I have deleted those two relationships which correspond to connections for the two students to the one course in the database. And after I have done this, now I can rerun the previous command because now I shouldn't have any relationships anymore between the students. All right, now I have deleted those two students again. Yes, so this is a simple example. Towards the end of the current slide deck, we will have another quick look at a more interesting example, but I already wanted to show you a little bit how to use this interface. All right. All right. So now that we have seen a little bit how to create simple graphs as a little exercise, I wanted to ask you to create a graph representing the following situation. Here, we have a couple of different types of nodes. Let's say that we have Ithaca and Binghamton, which are cities which are located in New York. Cornell University is located in Ithaca, and it offers a course with name CS4320. So I give you just a little bit of time to think about how you would represent this as a graph and create the graph in the database system. You can do it on paper, or you can try with this interface that I have just shown. And while you're doing that, I'm happy to answer any other questions that might pop up. I'm gonna give you 1-2 minutes, and then we're gonna see a few more commands. No questions currently. That's a good question, but it's a poor style to not be as specific as possible when matching. Frankly, I would say if you are not specific enough during matching, then there's a risk that you might match some nodes that you did not expect. So as a tendency, I would recommend to be as specific as possible in matching. Yeah, I think it's good practice. Yeah. Okay, and the website, if you just Google for Neo4j, the name of the system, then you will find it as first match. Yeah, so I would recommend to be as specific as possible in the matching. Of course, there's some limit. I mean, at some point you might have a database which has lots of properties for the same node, and then you might not want to specify all of them. So yeah, but in case of doubt, I would recommend to be more specific. All right. Okay, let's quickly solve this little example. All right, so here we asked about creating nodes to represent the cities, Binghamton and Ithaca, and those cities should be located in New York State. Let's perhaps first of all create a node which represents the state. And by the way, I'm gonna do it in one way, but different possibilities would be valid here. So let's create this node. And here, let's create this node, for instance, and Binghamton. And now we are connecting those city nodes to New York State. And admittedly not very specific in this matching expression. Actually, so here we're going to match city nodes to state nodes. And here we're going to add an edge that's pointing from the city to the state, and we can label it as located in. Okay. Right now we have created those relationships, and we also wanted to represent Cornell University. So let's create a university node with a name, Cornell, and just making sure I'm typically using the property name, but you could use a very different properties as well. Let's maybe just call this university name to show that properties can have different names. Okay, and actually I want to create that node. Right, and now I'm adding connections between Cornell let's be specific and add the university name here. We assign it to variable U, and we assign the city Ithaca to variable C here. And here we are creating the connection between you and the CTC. Okay, right. And now we still wanted to introduce a course node. So let's do that. We're creating the course, and now finally we're creating the connection. Or maybe other way around. Here we're creating the connection between the university, which in this case, there's only one university in my database, but I might want to specify the name anyway. Now here we are creating offers relationship in order to express that the university offers this course. Okay. All right. And duplicates of the same node. So there's a question about how we prevent duplicates of the same node. So it depends on what you mean by duplicates. I mean, every node that gets created here gets assigned some unique ID, but you might, for instance, have two nodes that are both labeled as students and both have the same name properties, for instance. That might happen. You might have, so basically, yeah, if you detect any duplicates, then you could delete them by referring to the ID. So yes, typically you would not want this kind of duplicate, and then you could delete one of them. There's a question about how we visualize relationships that we created. So I wanted to show more search queries next time, where we visualize the outcome, but let me maybe make one quick example here. So for instance, we have the relationship between the cities and the state. So here, for instance, I'm searching for all connections between city and state, maybe of type located in, and then I could return all of that, and the representation that it would give me here would indeed take the form of a little graph here. Okay, so here we have the different nodes represented in this mini graph. Over here, we have Binghamton and Ithaca both pointing to New York. We can shift that around a little bit, and here maybe make sure that we can see the labels of those edges. So this gives you also a graph representation of your query results. And the edges here, so there's a question about whether the direction of the edges has any significance here. So in general, you need to decide on a direction for the edges, and then it is a matter of a preference, whether you, for instance, whether want to represent an edge going from the university to the course with the label offers, or an edge from the course to the university with a label offered by. So there is some room for preferences, what you find most natural as a representation. You have to choose a direction when creating it in the database, but when querying, for instance, in the matching here, I haven't specified any direction, so this is why I didn't have any arrowhead in my queries. All right. So that was a little example as an intro to how to create graphs in a graph database. The next time we're going to look into how we can query those graphs, and we're going to look a little bit behind the scenes of how those graph queries are processed internally. I see you again. We're at the end of the time, so I see you again on Wednesday. Have a nice day. All right, let's get started. And currently we are discussing about graph database systems, which are systems that are specialized for processing graphs data, which is represented as nodes and connection between those nodes. The last time we have been discussing about one specific representative, which is the Neo4j system. We have looked a little bit at the Cypher query language, which allows you to create and query graphs. This is one of the last things that we have seen last time. I asked you to create a little graph which represents the situation that is described here. In the following, we're gonna see a couple of more features of that query language and a few more examples. And afterwards, we're gonna start discussing about a distributed graph processing. All right, so we have seen last time how we can represent this example as a graph. After creating a graph, of course, we also want to query it and find interesting patterns and subgraphs within it. So the way you query those graphs, you typically use some kind of a matching expression, and then you use the return clause in order to indicate to the system which parts of the pattern that you are matching it should return as the query result. So here in this example, we are looking for a student named Mark, which has a friends with connection to another student assigned to the variable s. And ultimately, we're interested in s, so we are returning this as query result. So this query essentially looks for the friends of student Mark. You can vary that. For instance, here, if we use this little asterisk there in the relation, it means that we can essentially chain those relations. So in this query, we are looking for friends of Mark, for friends of their friends, for friends of their friends, and so on. So we are essentially looking for pairs in that graph. You can also limit the number of steps that you are willing to make, for instance, with this notation. Anyone has an idea what this probably means? Mm-hmm. Okay, one proposition is a student friends at 3 edges away from Mark. Yeah, that would be a possibility. So so here definitely we are accepting multiple friend relationships in between the nodes that we are interested in. And here basically we are willing to accept between 0 and 2 connections. So that means this would include Mark himself, because of we are accepting 0 connections too, and everyone who is friends with Marks and all the friends of the friends of Mark. So you can tune how many steps you're willing to make in that graph. We can also do aggregation. For instance, we can look for the number of occurrences of a pattern using the count clause, and this syntax is similar to SQL, as you see. And you can, of course, look for more complex patterns by combining the things that we have seen. So here we are looking, for instance, for there's a student S1, which has to be friends with a student S2. S1 should be enrolled in a course C. S2 should also be enrolled in course C. And we have some restrictions on the name of the first student and on the name of the course. The syntax here again is very close to SQL. Again, you have a where clause in which you can specify conditions for filtering those patterns. And here we have the student name must be in the list Mark or Maria. And the course name should not be equal to CS4320. So altogether here, we're looking for students who are friends of Mark and Maria and have one course in common that they're both enrolled in, but that course cannot be CS4320. And in the end, we are returning S2, so we are interested in the other student. All right. So, and there's one little question for the path length of 0 to 2. So here we essentially, between the first node and the second node, we can have between 0 and 2 edges. So if it is 0 edges, then that's the node itself. If it is 1 edge, then basically you have 1 connecting edge. You can have 2 connecting edges, and those are the possibilities that we want to consider in this query. So from the start student, all the students that can be reached with at most 2 steps. And how many students are in the result of the query, that depends on the content of the graph. And if you want a specific path length, then you can just make the lower bound equal to the upper bound. We have seen this notation. We have the lower bound dot dot and then the upper bound. And if both of them are the same, then you're looking for a path with one specific length. Does it make sense? Awesome. Okay, great questions. And please always feel free to ask questions. Now I have a little exercise for you in which I want you to retrieve courses taken by at least one student who also takes CS4320. So think a little bit about how you would formulate this using the Cypher query language. And then in a minute, we're gonna see a solution. And if there's any questions about the query language, please don't hesitate to ask them. right, so let's see how we can actually do that. The question was to retrieve courses that are taken by at least one student who is also taking CS43 at 20. So in this query, we have multiple entities appearing. First of all, we have the course that we are looking for. Then we have the student who is taking the course. And then we have CS4320, which is another course, and it has to be taken by the same student. So here we somehow have connections between three nodes in the graph. So we want to formulate a matching expression where we have, first of all, the CS43 20 course, which should be of type course, and the name should be CS4320. Then we want this connected via the enrollment relationship to the student taking it. And that student should also be in an enrolled relationship with the other course that we are interested in. And finally, we're interested in this other course. So, right. Yeah. So here currently I don't have any content in the graph, but this is one way of solving, of translating this description on the slide into a Cypher query. All right. Okay, there's another question about an alternative representation. Mm-hmm. Okay. Mm-hmm. Mm-hmm. All right. Yeah, so here basically we can also put some of the conditions that are now merged into the node references. We can also put them into the where clause, for instance. We also have some directed edges here in the query, while I used undirected edges in my query, but that should be fine as long as you know into which direction the edges point to. And otherwise, yeah, the structure seems to be the same in this query. Yes, there's one slight syntax typo, but yes, the structure, yes, that is also a possibility. Okay, and here's the question, how we know when to use match and when to use where for a given condition. And frankly, for many conditions, you can either put it into the match clause or you can put it into the where clause. It's like with SQL queries, there's typically many ways of writing the same query, and ultimately it's a matter of personal preferences, which one of them you prefer. So there's no principled reason to put certain things rather into the match or into the where clause. Ultimately, it depends on your preferences. All right. Good. We're going to see a few more examples towards the end of the lecture. Now, I'm quickly going to tell you a little bit more about the internals of the system. And by the way, now we have solved some more complex problems. Initially, we started with an example graph representing the metro of New York City, and we wanted to find a path between two specific stations. And now with the features that we have seen, this would become a relatively short query. We are simply looking for paths from the first station to the second station. And if we use this asterisk in the connection, then we are automatically looking for paths of arbitrary length, which was not as convenient to represent in SQL. Now, the Neo4j system uses a specialized data layout, which makes it particularly efficient to traverse graphs. So to be precise, it has one data layout that is used for storing data on hard disk and one that is used to store data in main memory. And here I'm describing the in-memory layout where we are storing for each node the labels and properties and also a list of the outgoing edges. Also, we store the edges separately with the labels and properties and with references to the nodes that are involved in those edges. We might also have indexes that allow us to very quickly identify nodes with specific properties or with specific labels. If a query comes in, then it is translated into a query plan, which is composed of standard operators. Many of them are essentially known from SQL processing. You have operators for filtering, for projection, and so on. You have also a few graph-specific operators. For instance, if you want to find shortest paths between certain points in your graph, then there is some specialized algorithms available. And in order to find the best query plan for your input query, like the relational database management systems that we have seen here, we also use cost-based optimization. We can also process transactions. By default, Neo4j supports read-committed isolation, but you can get higher isolation levels if you manually acquire logs. There's commands for doing that. And also we have mechanisms to allow recovery by writing log entries to persistent storage. So all things considered, you can have ACID transaction processing with this system. So this is a very high-level overview of the system. Now, let's make a few more examples, perhaps this time for a different database. And read-committed isolation, that's one of those isolation levels that we also use for SQL. And essentially means you can only see those things which have been, those values which have been written by committed transactions. But there's some other anomalies that it still allows. For instance, you might not have repeatable reads if you repeatedly reading values in the same transaction that somewhere in between are changed by a different transaction that commits. All right, so now a few more examples with a little bit more complex database, which contains a graph representing movies and the people who directed them or played within them. So for instance, here, if I want to find out persons who have played in specific movies, I can do this with a match expression. Perhaps here, I first want to specify a specific movie. I could, for instance, use The Matrix, a science fiction movie from a while ago. And now I want to find people who acted in that movie. And now I want to return both the movie and the person. I have to, huh? And that explains why I'm not seeing any results here. I used a property named name, but I should have used a property named a title. And now I think it should work. All right, now I'm getting a list of the people who played in the matrix as a graph representation. I can also expand on that. Perhaps I'm interested in people who have played in the matrix, but also in the follow-up movie, which I believe was called The Matrix Reloaded. So let's extend the query here. And now we have another movie with title The Matrix Reloaded. Now here we are seeing the set of actors who have played in both movies together with the connections between the actors and the movies, all of them represented as nodes in this graph over here. Perhaps one more example, not specific to this movie. Perhaps I'm interested in cases where a director at the same time played in his or her own movie. I can also represent that as a query here. So I'm looking for somebody, for some person who has directed a specific movie. And at the same time, we want that person to have played, to have acted in this movie. So here I'm using the same variable name P twice, which means that they have to be assigned to the same node in the graph. And I have one connection between the person and the movie of type directed, and another connection of type acted in. So here I'm looking for the people who have played in their own movies, basically. And here I want to return everything, so I can just use this asterisk here. All right, and here I'm getting a couple of matches. There seems to be one movie by Clint Eastwood, for instance, and another one by Tom Hanks and Danny DeVito. In all of those cases, I have this pattern that I was looking for, which essentially contains two nodes, the movie and the person, and two connections between them, the directed and the acted in connection. All right. And what I can also do, I told you a little bit about the internals of the system. If you ever want to find out how a database management system processes queries, then a good guess is to just prefix your query with the explain command that works in Postgres, that also works here. So if I prefix that with the explain command, then it should give me a description of the query plan. So the query plan is also represented as a little graph here. So we read it from top to the bottom. I'm gonna make that a little bit larger here. And as you see, the plan starts by a node by label scan. So here I'm essentially using an index which gives me nodes for one specific label, which in this case is the movie. So here the system decided to first search for the corresponding movie nodes. Then after finding the movies, I'm trying to connect them to a person by the directed relationship. So here in the expand operation, I'm going along edges pointing from the movie to a person. And here I'm gonna essentially look for persons that have directed the movie. For the moment, P is just a variable, so I'm looking for directed relationships pointing to any kind of node. In the next step in the filter operation, I'm narrowing it down to persons, even though in this case, that might not necessary because it's typically persons who direct movies, but nevertheless here, we are filtering it down to nodes with the label person. Then we make sure that there also exists a connection of type acted in between that same person and movie that we're currently analyzing. And finally, we produce the result set. You also see that there's a couple of estimates over here. For each step, the system tries to estimate how many rows we are getting, and that is very similar to what relational database management systems do. We also try to estimate what is the output size for each operation, which is helpful in order to identify the cheapest query plan. And here you see we have those estimates. They are close, but not entirely precise. In the end, we got actually 3 matches here. The number of estimated matches is only 2. So as in relational database management systems, those are just the estimates, and every once in a while, they are off the true values. All right. I'm quickly looking whether there is a question. Okay, that is a great question. How does it come that the diagram shows directed arrows while I was using undirected arrows in my query? Let me quickly illustrate this in more detail. That is a great point. So here in this query over here, we can see directed arrows between the movies and the person. But the query that I used here, you can see the query again. I used undirected edges in my query. So those undirected edges essentially mean that I'm interested in directions into both directions. Internally in Neo4j, there are no undirected edges, but they always have one direction. So if I search for undirected edges, it essentially means that I'm interested in edges in both directions. So that is essentially a more general than if I had specified a specific direction for the connection. So here, the directed edges, they match my query because they essentially specialize the undirected edges that I'm referencing in the query. But that is a very good observation. Yes. All right. Any more questions on those examples before we switch to distributed graph processing? Okay, and here's a question about why the cost estimates are in rows if the data is stored as nodes. Well, I mean, in a way, what each row symbolizes here is essentially one connection, one match for the patterns that we're currently considering. So you could also call this a graph fragment, for instance. Neo4j actually gives you the possibility to also represent the results as tables. So I guess that might be one of the reasons why they chose this, this term. But I could also imagine choosing different terms for that. The semantics is essentially that we have one of those graph fragments that matches some part of the pattern that we specified here. All right. So if there's no questions for the moment, then I'm going to continue with the next subtopic, which is about distributed graph processing. So we are still discussing about graphs, but now we are discussing about particularly large graphs. The reading list includes those two papers you see here. One paper from 2010 introducing a system called Prego that we will discuss about in the following. That was by Google members. And then one later paper by Facebook employees in 2015 about a system that was significantly inspired by Prego. Now, the motivation for those systems are particularly large graphs, where we would typically not be able to store them and process them on one single machine. For instance, Google is interested in mining the entire web, and you can represent the web as one big graph. Facebook is interested in mining their social network data, which also is natural to represent as a graph. And in those cases, you typically want to do the processing in a cluster of machines. Now, one famous example of an algorithm that must run on a large graph, it's the PageRank algorithm. That is used by Google in order to rank your search results. So this algorithm that we will see in a little bit more detail in the following operates on a graph representation of the web. Here, nodes represent websites and edges represent links between those websites. And the goal of this algorithm is essentially to associate the nodes to a PageRank value, where higher PageRank value means that this page probably should be ranked higher in your search results. The PageRank algorithm is based on the random surfer model. And here we're talking about a randomized web surfer, which essentially starts from some random website and then randomly clicks on any link leading away from the current page. And it selects among the outgoing links with a uniform random distribution. If the surfer ends up in a dead end, meaning a website which has no outgoing links, then it selects a site to jump to randomly among all sites on the entire web. Optionally, as an extension, we can also allow the random surfer to not follow outgoing links, even if there are some, but instead with a certain probability alpha to select again some random page on the entire web. And when following this model, then the random surfer will come by websites every once in a while. And the idea is that perhaps the important websites that more links are leading to, they are visited more frequently. So the PageRank is essentially proportional to the probability to be at one specific site at any specific instant in time. So essentially, it's the percentage of your time that you will spend on that site when following the random surfer model. Now, this is a little example over here to illustrate the PageRank algorithm. So here we have websites represented as nodes, those blue circles, and we have links represented as those arrows between the circles. And in those circles, you see the PageRank value here scaled to a total value of 100 if you add up all of that. And as you see here, PageRank is not evenly distributed, but those nodes on the top of the slide, they have most of the PageRank, and that is because they have many links pointing toward them. And also the node on the top of the slide and on the right-hand side might not have that many links pointing into it, but it has a link, an incoming link from the node in the middle with 38.4 PageRank. So that's a very central node, and having a link from a node like that, that is particularly useful. All right, so this is a little example. I told you before that optionally we can allow the random surfer to jump to a random page with a certain probability alpha. When looking at this graph, can anyone tell me whether we have used this option in this case? In order to generate the page rank values here, did we allow the random surfer to jump to randomly selected pages with a certain probability? Does anyone see an indication which version we were using here? Very good, very good. Yes, exactly. So here, as your colleague is pointing out, we have nodes without any incoming links, for instance, at the bottom of the slide, to the left and also to the right. And those nodes, they nevertheless have a non-zero page rank, which means that the only way to reach them is by random jumps. So since that was possible, we must have enabled the option to do random jumps. Okay, very good. And the way to calculate the page rank, there's multiple ways, but you can use an iterative algorithm where you initially assign a page rank of 1 divided by the number of nodes, meaning the number of websites, to each of the websites. So this is because the random surfer initially selects the start website with a uniform random distribution. And then in each iteration, we redistribute the page rank. The page rank is essentially flowing along the outgoing links from a page, and each page partitions the page rank equally among all outgoing links. And then in the next iteration, the new page rank of a website is the sum of the page rank packages distributed over all incoming links. And we can iterate that a couple of times until it finally converges, and the result of the convergence that represents the probability that the random surfer spends time on a specific site. Now, this is an illustration for how we update the page rank values for each node in this iterative algorithm. So here we see page rank values at iteration I and at iteration I plus 1. And here we have 2 nodes, one with current page rank 90 in iteration I and one with current page rank 10. And they distribute their page rank equally across all of the outgoing edges. And for instance, the node on the bottom on the left has a page rank value of 10, and it has 2 outgoing links. So it will distribute a value of 5 over each of those outgoing links. And the node on the left on top of the slide has a current page rank value of 90 and 3 outgoing links. So it will distribute a page rank value of 30 across each of those outgoing links. And now in the next iteration, the node on top gets 30 from the first node and a 5 from the second node. So by summing that up, we get a new page rank value of 35. And the node on the bottom only receives page rank from the node on top on the left. So we have a new page rank value of 30 in iteration I plus 1. So this is the principle how I continuously update the page rank values of the nodes in each iteration. Now, Prego is a system which can do computations like that on very large graphs that are processed by large clusters of machines. It was described in 2010 by a paper by Google, and PageRank was one of the use cases for that paper. So we generally partition our graph into smaller parts that are managed by specific worker machines, and then they can do iterative processing on those partitions in parallel. Now, the Prego computation model works as described here. So the computation is divided into multiple iterations, which are also called super steps in this system. In each iteration, we invoke the compute function for each node in our graph. So we do some node-specific computation, and the way you specialize this system to solve one specific problem is by overriding the implementation of the compute function. So that's a little bit of a more low-level interface than some of the other systems that we have seen so far. The compute function takes as input messages sent to one specific vertex, aka node, in the previous iteration, triggered when processing the compute function for other nodes in the graph. And also, by processing the compute function, a node might generate outgoing messages that will be delivered in the next iteration. The entire computation ends once all the nodes vote to halt, meaning that they don't have any more work to do. And in that case, the system returns the final result. Now, this is an illustration of how the computation works from the perspective of one specific node here in the middle. And the node in iteration I will process messages sent to it in iteration I-1 from other nodes. And it will also produce outgoing messages for other nodes that will be delivered in the next iteration. And beyond the receiving and sending messages, we also have this flag indicating whether the node wants to hold the computation, which it does if all the nodes have voted to hold. For instance, here we have had the example of the web graph. This is, of course, a small graph. In reality, it would be way too large to represent. We would divide this graph into partitions, where each partition is defined by a subset of nodes. You can try to optimize the partitioning of the graph in order to have nodes that have lots of interactions with each other together in the same partition. And then each worker machine is assigned one or multiple partitions by the coordinator node, which tries to optimize the assignment from workers to partitions. The system also has some support for fault tolerance, which is extremely important if you have a large cluster of many machines. If you have that and let them compute for a while, then it is almost guaranteed that at least some of those workers will fail, and then you have to be able to deal with it, ideally without restarting the whole computation from scratch. The Prager system achieves that by a checkpointing, which means that worker nodes, they persist their inputs and their internal state at the start of each iteration. The coordinator node detects worker failures by pinging them regularly. And if failed workers are detected, then we start a recovery, which means that we might have to rewind a couple of super steps, and we repartition the partitions of the graph that had been assigned to those failed workers. So here we have to redo perhaps a couple of iterations depending on what checkpoints are available. They also describe a more refined recovery mechanism in the paper, which they call confined recovery. Here the idea is basically that the workers log even more data, and that allows us to restrict the recovery efforts only to those parts of the graph that were assigned to workers that failed. So here we log a little bit more, and therefore we would have to do less work at a recovery time. The way you would represent PageRank in Prager, at least a simplified version, is what you see here. We essentially have to implement the compute function that will be invoked for each node and each iteration. Here, the incoming messages correspond to packages of a PageRank value. This is the variable marked in blue here, received PageRank. And in the first step in the computation, we want to calculate our new PageRank value by summing up all the received PageRank values. Then, in the next step, we iterate over all the outgoing links, and we are sending an equal share of our new PageRank value to those outgoing links. And in the next iteration, those messages will be received by the target nodes, and they will calculate the new PageRank values based on that. So this code is a little bit simplified because we don't explicitly consider random jumps or how we handle dead ends, meaning websites from which we have no outgoing links, but this is the principle. There's a couple of optimizations that you can do. For instance, you might feel that now we are actually sending a lot of values around in each iteration. Pregel has some mechanisms to reduce that. There's, for instance, a mechanism called combiners, which allow you to define functions to combine multiple messages together into one. And that can significantly speed up the process. I believe in the paper, they mentioned speed ups of up to factor 4. All right, so this is one example for a system that does graph processing at an extremely large scale. So now we have seen two systems, Neo4j and Pregel, both for processing graphs. We are currently generally looking at different types of data beyond relational data. So in the next lecture, we're going to start with a new type of data, which is data streams. All right, so I think we won't start with the new topic anymore. If there's any more questions, then please feel free to ask them in the chat now. And gonna give it a few seconds to see whether there's more questions. All right, I believe there's no more questions on graph data processing. All right, in that case, have a nice day, and then I see you again on Friday. All right, hello everyone. Let's get started. So currently we are generally discussing about different data formats beyond relational data. Last time we have been discussing about graph databases. Now this time, and probably also in the next lecture, we are going to discuss about data streams. So this is one of the 3 types of data that we are discussing currently. And here you have a reading list introducing some of the systems that I'm going to discuss in the following, and some of the specialized data structures, which we will see later, and which are optimized in order to deal with large volume streams with many insertions. All right. So a data stream is generally something which constantly generates data. Examples are, for instance, a stock market ticker. You get new updates all the time, or for instance, in network monitoring, you get new measurements all the time, or you might have sensors which also generate data all the time. So in all of those cases, your data is not really static, but there is a never-ending stream of data coming towards you. And often in those cases, you don't only want to store or to observe all that data, you want to actually react to certain patterns in the data in real time. For instance, you might want to watch updates related to credit card transactions in order to detect frauds. That's something that might already have happened to some of you. If there was some suspicious transaction, then you very quickly get a message, and that should not happen sometime in the next weeks, but it should happen pretty much immediately. And there's other applications where reacting in real time is very critical. If you think, for instance, about medical sensors, but also if you think about financial data, if there's some quick changes in stock prices, then maybe you want to update your portfolio and sell or buy certain shares. So in all of those cases, you have a stream of data, and you're interested in detecting patterns in it and reacting to it in real time. Now, traditionally, the way databases have dealt with changing data is via the extract, transform, load, or short ETL mechanism. And that essentially means we have some data sources that generate new data. So regularly, like for instance, nightly, we would take that data, we would extract it from the source, transform it into a suitable format, and then load it into a data warehouse where we can analyze that data by asking, for instance, SQL queries. Right? So, I mean, that is the most traditional process. The problem with it is that we cannot really act in real time because it takes a while until the data arrives in our database where we can query it. So you might be able to react to what happened yesterday, but in many of those application scenarios, that is by far not fast enough. So if we are dealing with data streams, then this traditional ETL process might not be suitable. It essentially assumes that it is sufficient to ask your queries on data snapshots, and the problem is that the delay between those snapshots is often too high. Those data streams that we were thinking about in those examples that I mentioned at the beginning, they generate new data with a very high frequency. That means, in particular, if you have a given query, then actually the result of that query is not fixed, but I mean the result of that query keeps changing if the data it refers to includes data streams that keep generating new data. So if you're dealing with data streams, then you essentially might want to keep your queries running and see how the result of those queries changes over time, which is a bit of a different model of thinking about your data. And there is a class of systems that is specialized to those use cases with data streams, which are often called stream data management systems. And this comparison is simplifying, but in order to give you some first intuition for what the differences are if we compare stream data management systems to database management systems that we have been discussing about for most of the course, then first of all, database management systems, they assume a relatively static data set. On the other side, for stream data management systems, you assume that your data, your streams are very dynamic and keep generating new data. On the other side, for the queries in a database management system, we would assume that those queries keep changing very dynamically because users ask new queries. Once the query has executed, the result is known, and then this query becomes non-interesting, so we want to ask the next query. That's different for stream data management systems. Here we assume that queries are much more static because the result of those queries keeps changing as the underlying streams that the query refers to keep changing. So it is actually interesting to keep a query running for a while and to observe how its output changes. So that query could, for instance, look for patterns that indicate some likely fraud in the credit card transactions, for instance. And that is not a query you ask once. That's something that you keep running, maybe even over days or weeks or months until you have a new version of the query that you want to submit. So that is some high-level difference between the two. Database management systems assume the data is quite static while the queries are quite dynamic. Stream data management systems assume rather that the data is quite dynamic while the queries are rather static. So in the following, we're going to see two systems that belong to this broad category. There's the Stanford Stream Data Management System, already a little bit less than 20 years old, which introduced many of the concepts and techniques in the area of stream data management. And then we are also going to see and see a little demo of a more recent system, KSQL-DB, which does distributed stream processing in order to scale up to large number of streams or streams with a very high update frequency. All right, we start by discussing the first of those systems, the Stanford system from around 2003, 2004. In the reading list, you also have the corresponding paper. Now, first of all, let's look at the data types that this system supports. I mean, traditionally in a database system, you would have those relations, which we assume to be static and to only change if we insert data or change data explicitly with the corresponding SQL commands. In a data stream management system, we first of all have a new data type, which are streams. And streams, they keep generating new tuples without any user involvement. So they are more dynamic than relations, and they produce those tuples together with timestamps indicating when they were inserted. And relations might actually be derived from streams, and since the streams keep changing, the relations might also keep changing in the stream data management context. So we model relation rather, instead of something static, we model them as something that varies over time, here represented by this parameter t. So we have relations and we have streams. Streams are specific to the stream data management context. And the types of operations that the system supports, they generally can be classified based on what input type they have and what output type they have. So in the paper, the authors distinguish between those cases that you see here. We have operators that take relations as input and produce relations as output. Then we have operators that take streams as input and produce relations as output. And we have it the other way around. Operators that take relations as input and produce as streams as output. Now, in order to support that and to make it easy for the user to invoke those operations, we need a language that can describe what we want to do with our streams and relations. And in order to enable that, the authors have extended SQL. So in the following, we're going to see how we can describe those different types of operations with the extended SQL version. First of all, when we are talking about relation to relation operators, in that case, nothing much changes. We have already seen that in SQL, so we can just use what we already know there. You might also be wondering, because maybe one possibility is missing, stream to stream, but here the authors claim that you can simply translate a stream to a relation, and then you can transfer that relation to a stream again. So indirectly, that case is also supported. Now let's discuss a little bit about those operators that transfer a stream into a relation, or the other way around, here starting with stream to relation. And if you want to get a relation from a stream, then we do that typically by extracting tuples from the stream within a certain window. And there's multiple ways of defining that window. So typically, we are always interested in the more recent entries when defining those windows. So we can define the most recent tuples based on either the number of tuples or based on timestamps. So here we support both possibilities. For instance, in the query language, if you write the name of a stream and then within square brackets rows n, where n is some integer, then it means you want to extract a window from the stream that contains the n most recent tuples, the n tuples with the highest timestamps in the stream. Alternatively, we can define the window based on time. So if you write a stream name and then within square brackets, range, and then some time interval, like 30 seconds, for instance, it means that you want to get everything up to 30 seconds before the current timestamp. So here, the number of tuples that you get in that window might vary, but the time frame that it covers, the length of the time interval it covers, will always be the same. In some cases, you might not want to get one single window, but you might want to get different windows for different keys, which is a little bit similar to a group by query that we have seen in SQL. Here, what we can do is that we specify one or multiple attributes according to which we partition the data. And then we can, for instance, use the rows command in order to keep the most recent entries for each of those key value combinations. So this is a query creating multiple windows for different value combinations in the key columns. Now, on the other side, I might also transfer relations to streams. And if I want to extract streams from relations, I can, for instance, look at how the relation is changing over time. Because we have seen that in the context of stream data management, a relation is actually not static, but dynamic. So we can use the operator iStream of a relation in order to get only the inserted tuples into this relation. So at each time step, the iStream operator will contain those tuples that have been freshly inserted into the relation R in this instant. And similarly, we have a dstream, which stands for delete stream. And here we retrieve in each time step those tuples that have been deleted from the relation in that time step. And then finally, we have rstream, which essentially just extracts the entire relation in all time instants. So this one generates a lot of data and keeps showing the current state of the relation. I think there might have been a question. Okay, very good question. So here there's, we will see a couple of examples in one of the next slides, but let me already give you a little example for the partitioned window query. Let's quickly go back to the corresponding slide. So here you see the general syntax at the bottom of the slide. And for instance, I want to extract stock prices, for instance. Maybe I want to extract stock prices for each share. So I want to show the 5 most recent sales prices for all the different stocks. And I could realize that with this partition by query. And for the partition by, I would probably write the name of basically the column that contains the names of the stocks, partition by stock name, and then rows 5, which would always retain and continuously update the 5 most recent sales prices for each specific share. If you don't use the partition by clause here, then you could, for instance, get the 5 most recent sales in general, but that would not cover all the stocks. And if, for instance, one stock is sold more often than others, then you wouldn't see much from the other stocks during a certain time period. Does that make sense? Okay, great question. Yeah, so that would be one concrete example in which we could apply it. All right, here are the operators for translating relations to streams. And here are now a couple of more complex example queries. Maybe does anyone have some suspicions, suggestions about the semantics of those different queries here? any of them. Anyone wants to propose what the semantics could be, just to get the hang of it a little bit? For instance, if you look at the first one, can anyone summarize what that one is doing? Now we have fully expanded the queries into SQL plus the extensions for stream management. Okay, yes, very good. So here the first one is looking at the AAPL, it's the Apple stock. And we have the rows 10 construct. So from the stock price stream, we are extracting the 10 most recent rows. And specifically, we are looking for rows where the stock name is set to AAPL. And then what we do is that we calculate the average price of the remaining tuples. What about the second query? Can anyone make an assumption about what we are doing there? And the result of the first one is one number because we're building the average. But the average will keep changing over time as new tuples arrive in the stream. Okay, very good. Yeah, customers and their orders within the last 2 minutes. Very good. Yes, very good. Yeah, so here apparently orders might be a stream here. We are extracting a time window like the tuples within the last 2 minutes from the orders. And then we are joining the orders with the customers. So customers is probably a table here which contains the current customer set. And here the query will keep showing the customers and orders, basically the orders in the last 2 minutes and the associated customers. So this is a join, and we use the customer key in order to join the relation extracted from the order stream with the relation that contains the customers. What about the last one? Any suggestions for the last one? Doesn't have to describe the entire query semantics, maybe just some first lead about the direction. I can move the chat window so I can see the full replies. All right. Okay, great. Okay, get the tuples and insertion timestamp from the clicks in the last 30 seconds and which advertisers click. Okay, very good. So yes, so what we are doing here is that we have a click stream, which probably based on the name describes what the customers clicked on. And from that one, we are taking the last 30 seconds. Then we are joining that with the advertisers, which again might be a relation containing the current advertisers. As join condition, we want to make sure that the advertiser key is the same. So here we are combining the clicks that we get with the advertisers who posted the corresponding ad that the user has clicked upon. And then finally, this is probably not necessary in this context, but I wanted to include that operation anyway. So here we are essentially getting the insertions of the inner query. So the inner query results in a time-dependent result relation, which combines the clicks with the advertisers. And in the iStream, we essentially always get the updates, the newly inserted tuples into this query result relation. So like in SQL, I can combine those operators into more complex queries and have subqueries and so on and so forth. So that is the query language. They call it the continuous query language because those queries, they're meant to run continuously over certain periods of time, which here remains interesting if the query depends on some stream that keeps generating updates. So the query result keeps changing. That is one of the differences between stream data management and database management. All right. So this is the query language. Now, in order to support the corresponding queries, they proceed a bit similarly to database systems in general. They first of all compile the input query into a query plan. And this query plan is composed from standard operators. Now, we are going to discuss about those standard operators in more detail in the following. But what is in common to all of them is that in this query plan, the different operators, they essentially exchange information about what changes in your data. So each of those operators is essentially informing other operators by exchanging addition and deletion messages with timestamps. If we are looking at streams, then those streams, they only produce additions because I keep adding to those streams. I don't revise prior content. If we are looking at relations, they might also depend on time. But in addition to insertions and updates, they might also generate deletions because the content of the relation can keep changing. So all the operators communicate by exchanging messages about additions and deletions. The one that refer to streams only consider additions, the one that consider relations consider additions as well as deletions. Now, this is the basic model that those operators follow. They have one or multiple input queues with those addition and deletion messages, and they have output queues which also contain addition or deletion messages. What is important is that the system assumes that those input and output queues, they produce tuples sorted by timestamp order, which might require a little bit of work to guarantee that. If you only have those components, it is sufficient for certain simple operators, for instance, like filtering. The filtering operator doesn't need any state. It just looks at which tuples arrive in the input queue, and then it passes on those tuples to the output queue if they satisfy the associated filtering condition. Now, some of the other more complicated operators, like joins, for instance, they need a little bit more. They need some so-called query synopsis that maintains an intermediate state of the operators, which could, for instance, be a hash table or something like that. For instance, for the join operator, we would have two input queues which represent the two inputs that are being joined. And then in order to do the join as synopsis, we might want to maintain hash tables for the two input relations that are hashed using the join column as a key. And that will allow me to very quickly identify the tuples in one relation that match incoming tuples in the other relation. So in more detail, how would the join algorithm work in this scenario? So this is a simplified version of the algorithm. So let's, for instance, assume that for the join, we have an addition in the first input queue, then the first thing we would do is that we extract the join key from the added tuple. And then we use that join key in order to probe the hash table in our synopsis, which hashes the values from the second input queue by their join column value. And that essentially, for an equality join condition, which we assume here, it allows us to very quickly identify the matching tuples in the other table. And based on that, we can add the corresponding join result tuples to the output queue. And we might also have to update our synopsis, because now we might want to update the hash table storing the entries from input queue number 1. And of course, if it is the other way around and we have a tuple arriving in input 2 queue, then we do it the other way around. And for deletions, we proceed pretty much in the same way, just that here for the output queue, we're not adding the addition, but we are adding the deletion message. Okay, and here there is a question about whether this is for streams or relations. So before doing the join, as we have seen in the previous queries, we use the window operator in order to extract some kind of a window of the relation, at least in a general case, since those streams are essentially unbounded. If you would ask the system to join a tuple with an entire stream, it might in principle generate output of unbounded size. So we try to restrict the input to the join operator. That is a great question. So here for the join, in order to keep things bounded, we essentially want to work with relations that we have extracted from those input streams. In the examples before, we used, for instance, a time-based windows. I think we also used a row-based windows. So that means that we don't have to join any tuples with an unbounded number of tuples in the other input, which would be a stream. But that would exceed our capabilities. All right, so this is how the join algorithm works, and this is an example, a query plan. Okay, there's one more question. What we mean by adding, deleting, resulting join tuples. So all operators, including the join operator, communicate by exchanging messages about additions or deletions. So if you have, for instance, defined a window over a stream for the last 50 tuples, for instance, and that makes up one of the two input relations of the join, then you will have tuples being inserted into that window, but you will also have tuples deleted from that window once they become outdated because they're replaced by one of the newer tuples. So in this case, the join result would also change. If we add tuples in the join inputs, then we would add tuples in the join output. But if we delete tuples from the join input, we would thereby implicitly delete tuples from the join output. So the join operator also adds messages to its output queue that either represent the addition or the deletion of a tuple, and you need both typically. The way in which those additions and deletions are handled is nearly equivalent, just that in the end you need to specify whether you mean that this tuple now is being added or deleted. Does it make sense? Awesome, yes. Good questions. Okay. So this is a little bit more of a complex example here where we have not a single operator, but an entire query plan. At the bottom of the slide, you see the associated query. So here we are selecting everything from the join between two windows taken from two streams, S1 and S2. From S1, we take the last 1,000 rows, and from S2, we are taking, let me move that chat window, we're taking the last 2 minutes. We have one join condition, and we have one unary predicate that refers only to S1. And one way of treating that would be to apply the row windows on S1 and the time window in S2. Then we can put those two inputs into the join. And then after the join, we can apply the unary predicate on S1 in order to do the filtering. Now, I was thinking back to when we talked about query plans and query optimization. Can anyone perhaps see how we could perhaps optimize this query plan over here? Very good. And in general, in query planning, we have this instinct that we want to push down predicates as much as possible in order to reduce data sizes as quickly as possible. And very good, your colleague here points out that we could actually do the filtering on S1 earlier. This is a unary predicate, which are great for reducing the data size. It's very easy to do the filtering with little overhead, and it might reduce the data size significantly. So here we could just move this filter on stream 1 down far below to come before the join operation, and thereby it would minimize the total amount of data that we are processing. Very good. Now, in this case, the optimization was relatively easy, but of course, often it is more difficult to figure out how we can optimize a certain query plan. And in the case of stream data management, it might even actually change over time, because those streams, they keep generating data. And in some cases, the properties, the distribution of the data they're generating, it could change over time. For instance, we have a stock ticker stream, and then suddenly there's a lot of sales with one specific stock. Then maybe you want to process that data differently. So this is why the stream system considers adaptive re-optimization, which means we start with one query plan, but as time progresses, we might actually revise our optimization decisions and change the query plan. So here they outline 3 components that are involved in this process. We have the executor, the profiler, and the re-optimizer. The executor is essentially the execution engine which executes those plans that we come up with. The re-optimizer continuously revises those query plans. It might change them. And the profiler is a component that generates statistics, up-to-date statistics that are used by the re-optimizer for planning. And the re-optimizer also has the possibility to request specific statistics from the profiler. So they revise planning decisions over time based on the current data properties that we are observing. What they might adapt over time, for instance, is first of all the join order. We have seen that in traditional query planning, and also here the join order is one of the most important decisions made by the optimizer. Caching, so we can tell the executor which things to cache if we believe that those things can get reused. And that is specific. The re-optimizer might also essentially configure the executor to take into account certain constraints, which, for instance, concerns the arrival times of related data items in different streams. And often those constraints can be exploited in order to make execution significantly more efficient. So those are the three components. Sometimes two of them also combined, the executor and the profiler, because I mean, in the end, the profiler needs to process data to generate statistics. The executor is processing data in general. So we can, instead of having a separate profiling step, we can combine that in some cases with a query execution, and the authors propose to do that. One thing that is extremely important in the context of stream data management is space consumption, because those streams, they can essentially be of unbounded size. So you need to make sure that you don't have to store too much data. And since memory is so important, the authors propose a couple of ways in which memory consumption can be reduced. They talk about synopsis sharing, about how to exploit constraints in order to prune out unnecessary data early, and about how to optimize the scheduling of the operators, meaning the points in time at which we process steps in different operators within the same query plan. And all of those things can have a significant impact on the sizes of the intermediate results that you need to keep around. So first of all, synopsis sharing. As a reminder, the synopsis is the state that has to be maintained by different operators in your query plans. Could, for instance, be for a join operator, the hash tables that allow you to quickly find matching tuples in the opposite input if a new tuple arrives. Within the same query plan, or even across multiple query plans on the same set of streams, you might have a lot of overlap between the synopsis of different operators. For instance, if you have multiple filtering and windowing and joins operations on the same stream, then multiple of those operators might have to maintain the same tuples in their synopsis, which is inefficient because we are storing data redundantly. And so they propose to instead maintain one global store of those tuples, and then the synopsis essentially refer to tuples in that global store. And so we avoid redundant storage within the same query plan and across different query plans. Also, we might often have constraints that help us to reduce the amount of data that we need to keep around. I mean, for instance, here, if we are joining again the orders with the fulfillment on the order ID, and now let's assume that the orders and fulfillments, we are using windows of unbounded size, then without any further information, I would essentially have to maintain an infinite synopsis for both of those inputs, which is something that, of course, we want to avoid. But now let's assume we know the following two things. We, first of all, know that the orders arrive before the fulfillments. And then we assume that the fulfillments are even clustered by the order ID in their arrival. So first of all, I mean, if you compare to the default situation, which is that we essentially would have to maintain unbounded hash table sizes for both of those inputs, which of course we cannot really do. What would change if we know that the orders arrive before the fulfillments? How could I exploit that information in order to drop at least one of those unbounded hash tables or reduce the size somehow? Does anyone have a proposition? Okay, very good. So here the proposition is that when an order arrives, we can delete the fulfillments that refer to previous orders, right? So I mean here, if, so here we know that the orders will arrive before the fulfillments. So, okay, all right, okay, that's another, okay, so those are, all of this goes in the right direction, and here, this is a great point. So we could only store the orders table, not the fulfillments. So because we know this, if a fulfillment arrives, then the associated order has already arrived before. So that means that if an order arrives, I will not find the associated fulfillments in the fulfillment stream because the order arrives first. But if a fulfillment arrives, then I know that the corresponding order has already arrived. And those operators assume that tuples are handled in timestamp order. So here, I now essentially, as your colleague suggests, that we do not really need to store the fulfillments, because in order to generate join result, the process would always be a fulfillment arrives and I probe the order table with the order ID from the fulfillment entry, because the orders arrive first. Very good. And how about the second constraint? Can I simplify things even more if the second constraint holds? Okay, very good. Yes, exactly. So we know that fulfillments are clustered by order ID. So that means as soon as we see a different order ID in the fulfillments, we will never see the current order ID again. And that means that we can discard all associated entries in the orders window, because we will never see corresponding fulfillments again. And both together is pretty powerful. The first constraint essentially allows you not to maintain any synopsis for the fulfillment table because you don't really need it. The second constraint allows you to prune entries in the orders window, because you know that once the order ID in the fulfillments changes, you will never get fulfillments for the same order again. So you don't need this anymore in your synopsis. So this is the types of constraint that can help you to significantly reduce the amount of data that you need to keep around, and the streams system tries to exploit that. They consider three general types of constraints: the referential integrity K constraint, for instance, which refers to a key foreign key type joins. And that is what we have already seen in the example. We essentially assume that there is a delay of at most K between matching tuples arriving in the two join inputs. I can use that in order to limit the size of the join synopsis that I need to keep around. There's the ordered arrival K constraint, which essentially means that your data is nearly sorted within certain bounds. So if you compare K elements, like two elements in the stream that are at least K tuples apart, then those are sorted. If you compare elements that are closer together, you might not necessarily get that, but if you compare, if you allow for a little bit of slack, then your stream is basically sorted. And what we have also seen in the example is the clustered arrival K constraint, which means that elements with the same key can only be a certain number of tuples apart. So that also means that if you allow for a little bit of slack, then your input stream is basically clustered. And all of those constraints can be exploited in certain situations in order to drop tuples from your intermediate results. So this is the how we can exploit constraints in order to reduce sizes. I'm gonna quickly say a few words about the scheduling policy. The next time we are gonna continue there with an example. But the idea here is generally that you have some flexibility about the order in which you process certain operations in your plan. You know that in your query plan, the different operators are connected via queues. So we have some slack. We can let one operator execute a couple of times in order to accumulate output before we invoke the next operator. We can more evenly balance the number of times that we invoke those different operators. And as we will see in more detail next time, this can actually influence the amount of data that you need to keep in your system at the same time. So we're gonna pick up from there next time. I wish you a nice weekend, and then I see you again on Monday, where we continue talking about stream data management. So, all right, let's get started. So currently we are discussing about data streams. And the last time we have discussed about a couple of examples. For instance, if you have a stock ticker stream, or if you have sensor data that keeps being generated, then often you want to model this as data stream, and there is specialized systems for processing those streams. The last time we have started discussing about one of those systems. It's already one of the more classical ones from Stanford. And this system has several interesting features. One of them is how it tries to minimize the amount of data that it has to store in the system, because those data streams, they are essentially unbounded. So it is very important to throw away data when we don't need it anymore. Now, we have discussed about a couple of ways in which the system tries to minimize the amount of data to store. For instance, if you have multiple operators in the system and they have to store tuples, sometimes they have to store the same tuple, so you want to overlap that. This is what I mean by synopsis sharing. Also, we have seen that there is constraints, for instance, on when certain tuples can arrive in certain streams. And if we exploit those constraints, then we can also often reduce the amount of data that we need to keep around. And then finally, I've mentioned that we can also shrink intermediate results by smart scheduling. And in the following, we're going to see a little bit more how that works. So we are going to discuss about scheduling policies. And as a little reminder, so in this stream data management system, the different operators in a query plan communicate via queues. Each operator has an input queue and an output queue. And in those queues, you have information about what changed in the data, about the tuples that were inserted, and about the tuples that were deleted somewhere. And since I have those queues between the different operators, I have a little bit of freedom about when I invoke certain operators in order to process their input queue or part of their input queue. And there's multiple different scheduling strategies. The simplest one is the FIFO, first in, first out policy. Here, essentially, whenever we have one new input batch in the system, then we will process those tuples completely before we look at the next input. So here, if your operators form a chain and you have a new batch of tuples arriving at the beginning of that chain, then you will consecutively call all the operators in that chain in order to completely process the input tuples. That's one possibility. There's also the greedy policy, which essentially means that we don't necessarily call operators in a fixed order, but instead of that, we will always call the operator that can probably get rid of most tuples in the system. So here we greedily try to get rid of tuples as quickly as possible. And then they also propose some mixed strategies. For instance, you can group your operators in the system and then use a greedy strategy in order to decide which group to invoke next. But within the operators in the same group, we use the simpler FIFO strategy. So there's a couple of ways of mixing that. In the following, I'm going to illustrate the differences between FIFO and greedy scheduling by a little example. So here we have a chain of 2 operators only. We essentially get the input, then operator 1 seems to be a filtering operator. It has a selectivity of 20%, which means that for each input batch of tuples, approximately 20% of them pass the filter. And then we have a second operator. The precise type of that operator does not matter. In each case, I have 2 queues in the system that I care about. That's the input queue, input to the first operator, and this intermediate result queue, which is the output of the first operator and the input to the second operator. I don't care anymore about the final output of the system because that doesn't have to be stored in the system. Perhaps it is directly forwarded to the user or to a different system. So I care mostly about minimizing the sizes of the input and of the intermediate result queue. Now at the beginning, those queues are empty, and now the following, I assume that we have 1 new tuple batch in each time step arriving in this input queue. Now in the following, I'm going to illustrate a FIFO scheduling first. So let's assume that the first batch of tuples arrives in the input queue. And since we do first in, first out scheduling, it means that we have to invoke the first operator next. So this is why it is marked in red. And after we invoke that operator, about 20% of the input tuples will remain and be inserted into the intermediate result queue. At the same time, 1 new batch of input tuples arrives. This is why the input queue does not become empty, but fills up immediately again. So here I assume that we have 1 fresh input tuple batch in each time step. In the table below, you see that I'm inserting the total size of all queues combined in the system, which now is 1.2 in time step number 1. So here in the next step, I would invoke operator 2 because it's the simple FIFO scheduling strategy. And the result of that is that, first of all, we are getting rid of the intermediate results. On the other side, we have this current input batch in the first queue, and 1 more batch will be added in the next timestamp. So this is how the queue sizes evolve. And now, as you see, we already have a combined queue size of 2 in the entire system. So now we have completely processed the initial input batch. So now we're gonna invoke the first operator again to process 1 more batch of tuples, which produces intermediate results of 0.2 batches. And it eliminates 1 of the 2 input batches, but in the next timestamp, we will get 1 more input batch. So this is why the input queue size does not decrease. So this is what happens here. And in total, now we have a combined size of 2.2. So as you see, the total number of tuples in the system keeps growing relatively quickly. And now if I continue, I would first invoke the second operator again, which removes the tuples from the intermediate result queue, but at the same time, we allow that the input queue fills up further. So here, now we have already 3 batches of tuples stored in the entire system. And as you can imagine, that continues. So here I'm fast forwarding and filling in the last two fields in the table below. And yes, so here every 2 timestamps, we increase the total number of batches stored by 1. Now, let's see whether we can do better with greedy scheduling. So the same situation as before, I assume the same arrival rate, just that now I vary the order in which I invoke certain operators. So now here, one input batch arrives again. And the goal of greedy scheduling is that I always invoke the operator which can reduce the number of tuples the most. So here that is clearly operator 1. So I again select this one, and the result is the same as before. I have a 0.2 batches in the intermediate result, and I have eliminated one input batch, but a new input batch got immediately sent. So now I again have one batch in my input queue. And now the FIFO strategy would invoke operator number 2. But in the greedy case here, we will see that by invoking operator 2 here, we would only get rid of 0.2 batches. That's the content of the intermediate result queue. While by invoking operator 1, we will actually get rid of one entire batch. So that is clearly more desirable. So with greedy scheduling, I'm invoking operator 1 again. And after that, the intermediate result will grow by 0.2, and the input, current input batch will vanish, but a new one will get inserted immediately. So I remain at 1, and the intermediate result slightly grows to 0.4. So in total, I have 1.4 batches stored in the system. And if you compare in the table at the same point in time with the FIFO strategy, now we would already be significantly above that. And if we continue here, now it's the same thing. Operator 1 allows us to get rid of more tuples. So this is why I would prefer invoking this operator in the next time step. And now the intermediate result grows by 0.2 again. And the input doesn't change because one gets deleted, one gets inserted, nothing changes. So now in total, we're at 1.6. And again, this is a lower number of batches than I had stored with the FIFO strategy. So here, selecting greedily pays off. And if I continue this and fast forward and fill in the remaining fields in the table below, then you see this development. I keep increasing the number of tuples by 0.2. So this little example shows already that the scheduling policy can make a difference, and in the system, they exploit that fact. There's a couple of other methods that they use in order to reduce the number of tuples that you need to keep around. Now, the previous strategies, they don't essentially lose anything, so you always want to apply them. Now, there's also a couple of strategies which do lose precision, or they do lose tuples, but if you otherwise run out of memory, then you cannot do anything else. So they consider in general load shedding, which means that we don't process a certain tuples in order to save overheads. And if you have, for instance, a query in the system that calculates aggregates, then even if you don't process some of the input tuples, at least you can still get some kind of sample for the aggregate input, and you can calculate things like confidence bounds, for instance. So you can estimate what would be the aggregation value, for instance. If you calculate an average over some input stream, and then we are dropping half of the input stream, you can still get a pretty reasonable estimate for what the average is gonna be. And if you have multiple queries in your system, then they try to balance out the impact between multiple queries and make sure that no query suffers too much. And in general, those operators, they often have a so-called synopsis. If you remember, for instance, for the join operator, the synopsis would correspond to a hash table pretty much, which allows you to quickly find the joining tuples in the second input if a new tuple arrives for the first input stream, for instance. If we reduce the synopsis size, then we save a little bit more, then we save memory for the current operator. And in many cases, like for joins, for instance, reducing the synopsis size means that less results get generated. So implicitly, we also might save for the following operators, because now they have to process less data. There's a couple of exceptions to that. Can maybe anyone think of an exception? So when can it happen that by reducing the synopsis size, I might actually increase the amount of data that needs to be processed by following operators? If you have a suggestion, please put it into the chat. Let's see the first message. How could it reduce the output size? Okay, great question. So, I mean, for instance, we have a join operator and the synopsis is one of the hash tables. So if one tuple arrives in the first input, then I use this hash table in order to quickly find the matching tuples in the second input. And now I just forget half of that hash table, which means that for each tuple arriving on the first input, I will now find less matching tuples in the second table. And because of that, the size of my output is decreased. We can also have another look at the join operator, or does it make sense like this? Okay, awesome. Maybe I anyway show quickly again the join operator that we have quickly discussed the last time. So this is the join algorithm here. This is the graphical representation of the join algorithm. You see that here on the bottom of the slide, we have a synopsis, which essentially corresponds to hash tables for the two inputs using the join column as hash key. So here we assume a join with an equality join condition, and the algorithm works as it is described here. So whenever a tuple gets added or deleted in the first input queue, we extract the join key from the added tuple, then we probe the hash table, the synopsis that is associated with the other input using the key. And for the matching tuples, we add them to our join result and also potentially update the synopsis. And here, if my hash table is smaller, it will find less matches, so it will generate less output. And now the question is, if we do that, then in many cases, like for joins, I would expect that by generating less output, the following operators will also generate or process less data. There's a couple of exceptions. Can anyone think of an exception to that rule? Can you think of any SQL operations where the output size actually increases if one of the inputs decreases in size? Okay, so here you're thinking about like if we decrease the number of entries in the where clause, then we might filter less and then the output size increases. Okay, that is correct. Okay, that's a good point. And that would be a reduction of the query. So if we drop operations, okay, very good. And if you think about a case where the data basically decreases on one input and then the output increases, what kind of operations might we be talking about? Filtering is a good direction, yes. Mm-hmm. Anyone has any suggestions? If you think about, okay, self joins, might depend. So I mean, if the input to the join decreases, then often the join result also decreases. If you think about the set operations that we have seen, okay, I mean, for a union, if one of the inputs increases in size, then probably the output won't decrease either. It's the same for an intersection. If you think of other set operations, is there maybe something that comes to mind? In a way, yes. Yes, okay, very good. Here, there's the keyword. Yes, very good. So if we look at the set difference, basically you have one set and then you're taking out elements from a second set. Then if that second set decreases in size, then the total output of the operation actually increases. So that is one example where decreasing the size of one of the inputs might actually increase the size of the output. And in this system, the authors, they pay attention to those kinds of effects and will be considerate about where they reduce the size of the synopsis, because in some cases it might actually increase the size of the data processed by follow-up operations. All right, so now we have discussed this first stream data management system from already around 2003. It's a pretty classical system, but it has introduced a lot of the important concepts in the context of stream data management. This is why we have discussed it in a little bit more detail. Is there any questions about this first system before we start discussing about the next one? All right, I believe there is no immediate questions. Then we are gonna discuss now about another system, a recent one called KSQL-DB, which is a system for distributed stream processing. And often, if you deal with really large amounts of data or queries, then we probably want to do a distributed processing. So KSQL-DB uses several components that it is based upon. So we're going to discuss about those components too. KSQL-DB in particular is based on Apache Kafka. And first of all, we're going to discuss a little bit more about Kafka. So Kafka is a Java-based stream processing engine. Now, you have a data which is partitioned into different topics. Then producers can add records to specific topics and consumers can subscribe to specific topics. Then they will get updates for those topics. Kafka already supports certain simple stream processing operations with the Kafka Streams API for filtering, grouping, and so on. This is a pretty popular system. For instance, if you have already used Uber, then know that the passenger-driver matching is internally done via Kafka. So this is a popular system. It is a little bit more low level because it only supports simple operators. A KSQLDB, which we will discuss in more detail later, essentially adds an SQL interface on top of that. Those Kafka topics that I mentioned correspond essentially to an ordered, to a log that contains ordered records. Each record essentially corresponds to a key value pair. Producers can append to this log, so we don't go back and update or delete previous entries, but we just append entries to that log. And the consumers, they receive updates for the topics they subscribe to. There's a couple of different types of topics. Regular topics, they essentially delete tuples only if certain space or time constraints are met. So if you're running out of space, you have to delete the tuples, or if the tuples become stale after a certain timeout, you might also delete them because now they are not interesting anymore. So also compacted topics, which essentially mean that new tuples, they override the old entries for the same key. Each record has a key and a value. And if you have a new record that refers to a key for which you already have entries, then the new value overrides the old value. So this is how those topics are structured, and they are processed in a distributed manner. Each of those topics is divided into partitions and at the same time replicated across multiple servers, which as usual gives us a fault tolerance, because if one of the servers fails, then we can recover the corresponding partition from others. And it also allows us to scale to more consumers. And here, okay, this is actually a great question. The definition of the compacted topic, whether it doesn't mean that we can actually update a tuple as opposed to just appending to the topic. Yes, that is a very good point. In a way, it does, yes. So for the compacted topic, you can update the old values essentially by appending new tuples. Yes, that is a very good point. So when processing those partitions, then we always have one dedicated leader server, which accepts new updates for the corresponding partition, and it propagates those updates to the followers. This is an illustration for how that looks like. So here we have 3 servers, and we have 2 topics. The first topic with 2 partitions, the second topic with only 1 partition. For each of those partitions, a different server is the leader, so it accepts updates from outside, and it synchronizes, it forwards those updates to the other servers which are storing the same replica of the same partition. So this is how distributed stream processing works in Kafka at a high level of abstraction. Now, in order to make this efficient, we have to deal with insertions at a very high frequency. At the same time, we still want to be reasonably good at reading data. So Kafka Streams uses an underlying component, it's called RocksDB, which is very highly optimized for fast writes and has still relatively good read performance. And the techniques that this component uses, they are nowadays quite popular in the context of stream data management, or in general, if you have a lot of inserts to deal with. So we're going to discuss about that in a little bit more detail. The key idea is that in order to make writes efficient, you ideally want to write sequentially. And if you remember, for instance, the session on hardware, storage hardware, we have seen that those storage devices often have a preference for writing out data sequentially as opposed to having many random writes which are widely distributed, for instance, on the hard disk, because, for instance, the hard disk has to move mechanical components in order to get to certain locations on the hard disk, and doing that takes quite some time. So we want to try to write sequentially. And updates, yes, that means in general that we insert new tuples. In this case, yes, updates in general could also mean that I go back and update or delete some prior tuples, but in this case, the updates consists of adding new tuples. And for compacted topics, that indeed means that the newly added tuples might essentially, the semantics is that the new value overrides the old value. Yes. Okay. So in order to make writes efficient, I want to write sequentially. And there's an easy way of doing that. So if I want to purely optimize for insertions, and I have some pages on hard disk, and I have a buffer in main memory. So if we add the records to that buffer in main memory, I could just write out the entire buffer whenever it is full, and then I write the entire buffer to hard disk. And now I fill it up again, and once it is full, I again flush it to hard disk, and so on. So this process here is totally optimized for insertions. I'm sequentially writing data, so that is very efficient. On the other side, what happens if I ever want to look up values for one specific key, for instance? And if I just write out things in the order in which they arrive, it means that here, in order to find a specific key, in the worst case, I might have to read everything that I have written, and that is clearly very inefficient. So this system is entirely optimized for writing data, but it's not very good at reading data, because the data that I'm writing doesn't have any structure that makes it easier to find specific records that I'm looking for. On the other side, I could optimize for reads, and I'm not going to discuss that in too much detail because this is essentially what we have seen so far. You might remember the indexes that we have discussed about, for instance, the B+ tree, and those index structures, they are very helpful in order to find specific data quite efficiently. And typically, if I want to be efficient at reading data, then I can just maintain an index over the data. So whenever I insert new tuples to my data, I would also update that index. And that means that I'm very efficient at finding specific records via the index. But on the other side, whenever I insert a tuple, I also have to update that index. And since this index doesn't store the data in insertion order, it means that in order to update the index, I need to update at least one page, which essentially means that I'm getting quite inefficient at inserts, because each insert is associated with one random write. Does that make sense, the trade-off between the write optimized and the read optimized storage? Any questions on that? And perhaps one little clarification on the last question that I had about what it means if you say that the leader accepts updates. I should also say that in accepting those updates, depending on the configuration, it might also entail talking to the followers and making sure that they have received the updates, such that even in case of a failure, I have stored the data somewhere. So there's a couple of steps that accepting updates entails. And then after having done all of them, the leader tells the producer that now the update has been safely processed, so the producer doesn't need to resend it. All right. So now we have seen two possibilities of dealing with data insertions. If I want to optimize for write performance, I can just append data sequentially, but then it's pretty bad for reads. If I want to optimize for read performance, I might want to maintain an index data structure, but then insertions are pretty expensive. So in the following, I'm going to discuss about a compromise between those two, a data structure, which is very good at writing data and not too bad at reading data either. It's the log structured merge tree. And this is the data structure used by Kafka streams. Now, a log structured merge tree essentially divides the data into multiple levels. The uppermost levels are stored in main memory. The lower levels are stored on hard disk, and each level is associated with a size constraint. And the size of those levels increases from the uppermost level to the lower levels. And it doesn't increase arbitrarily, but the ratio of sizes between consecutive levels always remains the same. So for instance, we could say that the next level is always 2 times larger compared to the last level. The way in which we use those data structures is this. Whenever we insert data, we first insert it into the uppermost level. And then whenever one level exceeds its capacity, we take all the current content in that level and merge it into the next lower level. So those merging operations, they are relatively efficient because here I can write data sequentially, right? So I don't insert single tuples randomly, but I'm merging 2 large batches of tuples, and thereby I get a pretty efficient write throughput. Now, when I want to read data from one of those trees, I mentioned that the data at the same level is globally sorted, which means that it is relatively efficient to find the correct data for a given key at a level. I might also have additional data structures that help me to identify the data I'm looking for in one specific level quite efficiently. For instance, I can use Bloom filters, which often can allow me to skip levels at which the data I'm looking for is not located. And Bloom filters, it's also something that we have quickly seen in the context of distributed joint processing. It is essentially a hash table which contains bits for specific hash buckets that tell you whether corresponding entries are in your data set or not. So since multiple entries map to the same hash bucket, it means that if you have a 1 at one of those hash buckets, that may refer to the data you're looking for. It may also refer to different data, so you cannot be sure, and you need to check in order to see. If the bit is set to 0, it means that the data you're looking for is definitely not located there. So you can often skip looking at specific levels if you use a Bloom filters using the key that you're looking for as hash key. All right, so there's a couple of tricks that can play in order to avoid looking at specific levels or finding data at specific levels faster, but really just the fact that my data is sorted at the different levels, it makes it significantly more efficient to find data I'm looking for compared to having just one unordered sequence of data where I might have to read everything. So that was one component of a KSQL DB. The next time we're going to discuss the actual interface, and then we're also going to see a little demo. Have a nice day, and then I see you again on Wednesday. Okay, everyone, let's get started. So for the moment, we are still discussing about stream data management. We have seen two different systems for stream data management, an older system from Stanford and now a more recent system called KSQLDB. KSQLDB is based on Apache Kafka, and we have discussed about the specifics of Apache Kafka in the previous lecture. Now we're going to discuss more about KSQLDB. So KSQLDB is a high-level API that runs on top of our Kafka streams, and it translates SQL-like queries into those Kafka operators. I quickly mentioned that Kafka supports low-level operators like filtering, for instance, and here we are translating those SQL queries into a plan that involves those simple operators. KSQLDB processes so-called collections of events, which can either be streams or tables. And I'm going to say a little bit more about that on the following slides. It also supports two different types of queries, pull queries and push queries, where a pull query executes once on the current state of the data, while the push query essentially is a continuous query and continuously generate new results if the streams that it is based upon generate new results. I mentioned that KSQLDB has two types of collections, and those collections essentially both store so-called events, which you can imagine like a row where one of the columns is a timestamp column, basically. The difference between streams and tables is what happens if we insert a new events, new tuples into the corresponding collection. If it is a stream, then new entries are simply appended. They don't override anything else. They're just appended to the end of the stream. So streams would be suitable to represent, for instance, historical data like the development of stock prices, for instance. For tables, it's a bit different. For tables, we expect those events to have a primary key. And then if we append a new event, a new tuple to a table, it means that we are overriding prior values for the same key as the newly inserted tuple. So tables are rather meant to represent the current state. For instance, in the stock example, a table could represent the current price for each stock, but it wouldn't contain the information on historical price developments. We can create collections with those commands here, which are clearly close to the SQL commands that we have seen for creating tables in prior lectures. Here we have an example where we create a stream and one where we create a table. For the stream example, it's a price history stream. So here we are taking care of the stock market example. After the create stream command, you have the name of the stream, which here is price history. And afterwards, we are defining the columns that will appear in the stream. And here we have a symbol column which represents the name of the stock. And then we have a price column. And as in SQL, we are specifying the type for each of the columns. So here we have the symbol column, which is of type string, basically, and the price column of type integer. Now, the next part of that statement is more specific to KSQLDB. I mentioned that KSQLDB internally uses Kafka topics in order to store the data for streams and tables. And here we therefore specify a corresponding Kafka topic, the ticker topic in this case. So this topic must already exist before we create the stream essentially on top of it. We also specify the value format. We have a couple of different possibilities. Here we choose to represent values in a JSON format. And the second command on this page here is a create statement for a table. So this is the current stock price, because if we have a new row, it overrides values that were written previously and have the same key. And in order to make that happen, I first of all need to tell the system what the key is, which column is the key column. And here I say that the symbol column is the key column. And here you see the primary key command. Due to the semantics of tables in KSQLDB, generally, when specifying tables, you need to specify a primary key constraint. So here the key is the symbol column, and if we insert new events into the table, it will override the old prices for the same shares. The previous commands create collections that are initially empty. I would first have to insert data into them to make them interesting. Once I have some collections already, I can also use them to derive new collections from them with the syntax that you see here on this slide. For instance, I could say that I have the general stream with stock market updates, but maybe I'm specifically interested in one specific share, for instance, the Apple share with the symbol AAPL. Then I might want to create a stream that filters things down to updates that concern only this share. And this is what I'm doing with the first command here in the slide. So here we are creating a new stream called Apple Ticker that is more specific than the generic version. And after the stream name, I can immediately specify what the stream should look like. And here we are simply selecting from the price history stream created on the previous slide. But here we have a filter condition in the where clause. We are restricting the symbol to AAPL. And here another example, a little bit more complex and from a different domain. Here we are creating something called the advertisement stream. And we are specifying the associated query directly below. Here we have a join. We are joining a click stream with the advertiser table, which contains perhaps more information on the companies that have placed advertisements on our website. And as join condition, we simply require that the advertiser ID in the click stream is identical to the advertiser ID in the advertiser table. All right, so in general, if I want to derive new collections, I can create them with the syntax, create a stream, for instance, then the name, then as, and then the corresponding query specification. And as you see here, again, this is pretty close to SQL. So if you already know SQL, then it is relatively quick to get used to this notation. All right. Now, if I don't derive streams, then I might want to insert data into them explicitly. I can do that again with a syntax very close to SQL. I can simply write insert into, then the name of the stream, then the name of the columns that I want to insert data for. The other columns will be set to null values implicitly. And finally, the values that you want to insert. So here we have a temperature stream, which apparently has a location in the temperature column. It might have more columns. And then we are inserting the value Ithaca and 32 degrees. All right. So in terms of query types, we have two query types, push queries and pull queries. they work a little bit differently. The pull query essentially means that we only want to query the current state of the world. So the pull query executes once and returns a data to us, and then the query terminates. So it only returns one result. The push query is different because the push query keeps pushing updates to us. So it keeps running. It's a continuous query that keeps running until we terminate it explicitly. So the push query might refer to tables or streams, and it will continuously return to us the newest updates from those collections. The pull query only runs once. There's a couple of restrictions on it. For instance, you cannot just run select star from stream with a pull query. That might lead to large results, and the stream keeps generating new data. So the pull query is restricted to be applied to tables. It returns one result, and there's a couple of more restrictions about which functionality the pull query supports. I mean, all of this targeted at reducing the size of this one result that the pull query returns. You can query streams and tables, again, using something pretty close to SQL syntax. Here we have examples for the pull query and for one push query. For instance, here for the pull query, I might want to get the current number of page views by region from a corresponding table. Maybe I want to restrict my attention to the Ithaca region, and then this query would return to me the current state. For a push query, for instance, I could define it on a click event stream, and whenever there is an update with the region key Ithaca, then I want to emit the corresponding update. So here you recognize the push query by this final clause telling it what to do with the updates it receives. So here we are emitting all the changes, all the updates to the click event stream. Now, let's see a little bit how that looks like in practice with SQLDB. They recently released a cloud interface that I'm going to use now in the following. Let me share my screen. All right. And now you should be able to see the cloud interface here. I'm currently running a small cluster with Kafka on it. And now I'm using KSQLDB as an interface. Here we are in the editor, which allows me to write queries like the ones that we have seen before. And perhaps I can just start by writing a query that will create a stream. Here, let's create a stock ticker stream, for instance. So we have the create stream command, the name of the stream. And now let's just follow the example that we have seen in the slide. So here we want a column called symbol, which is of type varchar. So it's a string of varying length. And now perhaps we also have the price column of type integer. Now I still need to link that to the corresponding Kafka topic because everything is based on that as underlying infrastructure. So here we are setting the Kafka topic to this one here. That is a topic that I have previously created. And we also need to choose a value format. And for this one, let's just use JSON. All right. So now I can run the query over here. We are processing the query and it succeeds. Now here we should have a new stream appearing, and there it is. It is the stock checker of type stream. So I mentioned that KSQLDB has streams and tables, and here that I have previously created, you see the curstock is a table here recognizable by the associated symbol, and here below you see the new stock ticker collection, which is of type stream. All right, so now I have created this stream. Let's perhaps start inserting values into it. And now I'm gonna create a new window. I'm gonna share it in a second. So I want to enable you to follow the updates as they're being generated. All right. All right. And here you should be able to see two windows. So I have logged into the interface from two different windows, basically. So in one window, I'm now gonna insert data into the stock ticker stream, while in the other window, I'm gonna create a continuous query that gives me the updates to the stream. So first of all, let's see how we can insert data into the stream. So we have just created this stock ticker stream. So now I can, for instance, run the command insert into stock ticker, and here I can explicitly indicate the columns for which I want to specify values. That would be the symbol and the price column. And now I can specify the values I want to insert, and maybe now I want to insert the new price for Apple shares, for instance. All right, so I mean, this symbol and price column specification is optional. In this case, I'm specifying values for all of the columns in the stream, so I wouldn't need to put it, but you can put it, and you may use it in order to specify values only for a subset of columns. All right, so let's run this query over here. All right, so this query has now executed, no problems, but of course, in order to make it more interesting, we also want to see the effect on the stream somewhere. And in order to have that, I'm gonna create a query, a continuous query in the other window. So let's perhaps create a query which just listens for updates to the Apple share price. So I can add a specification, a restriction to the AAPL Apple stock. And whenever there's an update to it, I want to emit the corresponding changes. All right. So here we are selecting from stock ticker, we're restricting to the symbol AAPL, and we are emitting the corresponding changes. So now you see that this query is marked as running. So this doesn't seem to change either. So this will keep running until we explicitly terminate it. Let's see whether it does what it is supposed to and emits the updates to the stock ticker stream that refer to the AAPL symbol. So now let's say that the price slightly increases. So now we are submitting, we are inserting the corresponding data. And as you see here in the query result on the right-hand side, indeed the update appears. If you try a different symbol, for instance, IBM, in that case, nothing happens because here we are not satisfying the condition that is specified in the where clause of the query. Let's test again with AAPL. And shortly after, the corresponding update appears in the query result. I can keep doing that. You see the delay between inserting the data and receiving the data on the other side is pretty small. So this system seems well suited for real-time reactions. For instance, if I want to include anything which listens for specific price thresholds for specific shares, for instance, and then tries to automatically buy or sell the corresponding shares. Now, I believe we have a question in the chat. Okay, that is a very good question. The question is, why don't we see the original $120 price in the query result? And that is the specific property of those push queries. They only notify you in case of a fresh update. They don't retrieve the current data. They only react if there's any changes to the data. So we terminated the query with the command emit changes. So it will only emit if there is changes to the data since the query was created. So that is a great question. The initial content that I have inserted is indeed not shown in the query result. Very good question. All right. All right. So I wanted to show you a quick demo about what it is like to use systems for stream data management in practice, in this case, a KSQLDB, but there's also many other systems. Is there for the moment any more questions, for instance, about the KSQLDB demo or about streams in general? All right. So that was a little demo for a stream data management system. And now we have covered the stream data topic. We have seen various examples for when we want to use data streams, because we're dealing with things like sensors, for instance, or in the example stock market updates. Those are scenarios where we often want to react to changes in real time. And with stream data management systems, we can do that. One common topic in stream data management is efficiency. In particular, we want to somehow keep the amount of data we need to store manageable, which we have seen several techniques for in the Stanford Stream data management system. We also want to be efficient about insertions. In particular, we have seen how KSQLDB uses some specialized techniques in order to make insertions quite efficient. And of course, if you're dealing with large amounts of users or large amounts of updates, then often you want to go for a distributed stream management system, which we have seen with KSQLDB. So we are about to start with a new topic. Is there currently any more questions on stream data management? All right, I'm already gonna change the slides here. All right, so we're currently discussing about different types of data beyond relational data. And the last type of data that I want to look at, that is a spatial data. And here you actually have a corresponding chapter in our Ramakrishnan and Gerke book, which is a chapter 28 in my edition. And this one covers most of the material that we are gonna discuss in the following. So we have looked at graph data, we've looked at data streams. Now we're going to look at spatial data. And spatial data, that's something that we all use on a regular basis. If you think, for instance, of Google Maps, it stores two-dimensional spatial data. You can also have spatial data in more dimensions. For instance, if you think about CAD systems, then they will store information about a three-dimensional object. Now, on a high level, spatial data can be classified into two types. Either we want to store information about points somewhere in space, which are completely characterized by a location in your n-dimensional space, or we want to store information about regions, which could, for instance, be specified by lines, boundaries represented as lines in a two-dimensional space, or by surfaces in a three-dimensional space. They may still have a location which represents some kind of anchor point, for instance, the centroid, but ultimately here you have like a whole set of points making up the region. There's also a couple of query types that are commonly associated with spatial data. First of all, there's the spatial range query. And that could, for instance, be show me restaurants in Ithaca, where we are defining a spatial region, which is Ithaca, and we want to retrieve objects of a specific type within that range. We also have a nearest neighbor queries. That's also something that you might know from Google Maps. It has a functionality to search for nearby objects. And then here it might give you the nearest objects, for instance, the nearest gas station to your current location, ranked by closeness. Finally, there is the so-called spatial join. And that could be something like finding objects that are close to each other, like pairs of objects that are close to each other. For instance, you might want to find pairs of parking lots and hiking trails that are within a certain distance from each other. So those are the three most common types of spatial queries. And in the following, we're going to discuss about how we can support them efficiently. If there's a question in the chat. Okay, very good question. So the question is about how do we define the regions if you're dealing with a region data object. So it depends a little bit on the application or on the scenario, but typically you would define them by a boundary. So you would not explicitly represent the points within the region. There might be infinitely many of them, but you would just specify the boundaries of the region. We will also see a couple of efficient representations of regions within indexes, but generally you would not define them by the points inside of them, but rather by the boundaries that restrict the region. And often we are dealing with specific types of regions. For instance, things become easier as long as we're considering boxes, multidimensional boxes as regions, but which specific types of boundaries and regions we consider, that depends a little bit on the application. But that's a great question. Yeah, so we would not go for the points explicitly. All right. Now, in the following, in this part, we're going to mostly discuss about indexing. And there has been a lot of work on indexing explicitly for spatial data, because it happens that our standard indexes that we have seen in previous lectures, they don't work very well for spatial data. And in the following, we are going to first of all establish that fact by an example with B+ trees, which work well for many scenarios, but in this scenario for spatial data, they are maybe not such a good idea. Then we will discuss about a technique called space filling curves, where you're connecting the different points in your space by a curve that visits close by points close together. We are going to discuss about a region quad trees, which is an indexing structure that is specialized for storing large regions of your space efficiently. We're going to quickly discuss about grid files, and then we are going to discuss about R trees, which you can consider adaptation of B+ trees for spatial data. And this is one of the reasons why they are quite popular in practice. So let's first of all see whether we cannot simply use our good old B+ trees in order to index spatial data. So here we are dealing with a two-dimensional spatial data to keep things simple, but the insights that we are generating here, they generalize to higher dimensions. And here I simply have the X and the Y dimension. And perhaps I want to support range queries within this region, queries of the form specifying interval for X and specifying interval for Y, and then retrieving all the points within the corresponding box. So perhaps I could think of creating a B+ tree that indexes, that has a composite index key, which uses those two dimensions as components. And for a tree index, I always have to specify the order in which the columns are considered when composing the index search key. And in this case, I'm placing X before Y. So the composite index search key first contains X and then it contains values for Y. So if we try to graphically represent the order that the index generates for the data, because as you might remember, in the leaf nodes of those tree indexes, the data is always sorted. And according to this sort order, we would visit the points in the space in the order that you see here. So our index search key prioritizes X in the sort order. This is why X changes only slowly, and instead we will first visit all the values for y, for one fixed value of x, before we change the value for x. So this is the order in which the index groups the points in the space. And as you can imagine, retrieving data about points that appear close together in the index sort order is more efficient. So if you think about different queries in this two-dimensional space, for instance, the queries that you see here on the right-hand side of the slide, can you try to make a guess about which of those queries the index would support quite nicely, and which others the index would not support so well? Okay, there's the suggestion that we would support the third one quite well. Okay, so it might also depend a little bit on the data properties. So here the third one, I mean, it restricts the two attributes that the index uses as a composite key. Okay. Is there perhaps any scenarios where this might not work so well? And what about the other cases? Does anyone have a suggestion about the other queries as well? Okay, the suggestion is the first one would be supported well. Okay, does anyone have an opinion about the second one? If you think back many lectures ago when we discussed about the conditions under which indexes are applicable to queries. Yes, very good, very good. Here basically we would have to go through all the x coordinates just to find those few y coordinates that we're interested in. We have no restriction on x, so we had basically would have to iterate over all possible values of x. Yeah, exactly, yes. And frankly, in those cases, it's often more efficient to actually just scan the data. So we essentially said that in those cases, if we have a restriction on columns that are not a prefix of the composite index key, then we won't even consider using the index. Because of exactly this problem, we would have to try out different values, all the different values for x, basically, in order to retrieve the associated values for y, and that is not efficient. Okay, good, awesome. So yes, I think we pretty much covered it. So I think people are in agreement that for the first case, using the index is probably a pretty good idea. If you think about this curve that we are following in the two-dimensional space, then essentially we would need all of the points that we are visiting on this curve between two specific points on that curve here, right? So I mean, if we are interested in everything between two specific values of x, or here everything that is smaller than one value of x, then the order in which the index sorts the points in the space in is actually quite good, because we will retrieve all the points we're interested in and no points we are not interested in when following exactly this curve in the space, which represents the order in which the index sorts those points, right? So quickly moving the chat here. All right, so here in the first case, using the index is actually a great idea. So that works really well. Now, in the second case, according to our standards, we would not even consider using the index. So here, using the index doesn't make a lot of sense, because if you would follow that curve, then most of the points you encounter on that curve, probably you won't even use. So using the index is doesn't really make things more efficient. Now, the third case is somewhat, at least the index is applicable because we are restricting a prefix of the composite index search key columns. So that is something. On the other side, whether we want to use the index or not in this case, it depends a little bit on the data properties and on the query properties. For instance, if the restriction on X is quite restrictive, so we want actually retrieve many points from the index, then maybe we want to use it. On the other side, even if that is the case, here we still would retrieve some points that we are not really interested in. So whether we want to use the index or not in this case, it depends on a couple of factors, but it is not, it doesn't narrow down things enough to the points that we are interested in. Just making sure there's no new messages in the chat. Yeah, okay. So this is why using standard indexes for spatial data is typically not a good idea. And this is why people have spent a lot of time thinking about how to optimize index structures for spatial data. If you have to bring it, if you have to summarize what the problem is, we can say that points that are close in the two-dimensional space, they are not necessarily close in the index, and the retrieving close by points in the index is always more efficient than retrieving far apart points from the index. So answering at least some range queries using this index would be quite inefficient. One possibility that I could still consider, but which also comes with some drawbacks, I quickly want to mention it here anyway, is to essentially use multiple tree indexes for different dimensions. We could have a separate tree on X and a separate tree on Y. And if I have a range query that concerns both dimensions, I could retrieve the record IDs from the two indexes and then essentially intersect them. But that means, first of all, I need multiple indexes. Also, there's overheads for the intersections. And I might, even if the intersected result is small, I might actually retrieve a lot of data from the two indexes if the restriction on at least one dimension is not very selective. So this method also doesn't work great. So probably it makes sense to come up with some specialized indexing structures. Before we do that, is there any questions here on this motivation? All right, then we're gonna start with one first method, which is called set ordering, and that essentially numbers all the points in your space in a way that points that are close in the two-dimensional or n-dimensional space, they also have a close numbers. The method that we are about to see, set ordering, it is quite good, but not perfect in that respect. There's other methods which I won't discuss in detail, but I just want to mention the term at least once, such as Hilbert curves, which are even better according to this criterion, meaning that they keep close by points close together in this ordering. The principle of set ordering is described here. It first of all assumes that each coordinate is represented as a binary string. And then, for instance, for 2D, we would essentially have two binary strings, A and B, representing the two coordinates of an object. And the number that we assign to this coordinate via set ordering simply mixes the bits from both of those representations. First, we take the first bit from the first coordinate, then the first bit of the second coordinate. then the second bit of the first coordinate, then the second bit of the second coordinate, and so on and so forth. Now, let's see how that actually looks like in a two-dimensional space. So here we have a space, and we assume that coordinates, they are quite coarse-grained and are represented by only 2 bits. So now we're going to number those 2 coordinates via set ordering, and we are starting with the origin, which is 0, 0, 0, 0. Now, what would be the next point in a set ordering if you apply the principle that we have seen on the previous slide? So I can quickly show that again. Below on that slide, you find the principle about how the set ordering number is formed. And if you apply that to this little example with a 2-bit coordinates, what would be the next point in the plane that we are visiting? So we have started with 0, 0, 0, 0. What comes next? Okay, I'm collecting opinions here. Okay, all right, so we already have 3 votes, I believe, for 0, 0, 0, 1. Okay. Any other suggestions? Okay, good. So let's see what happens if we mix those bits. We are mixing the X bits before the Y bits. So in that case, if we want to get to a 1, we would have to get 0 from X, then 0 from Y, then 0 from X again, and then 1 from Y. Very good. So the next point would be indeed 0, 0, 0, 1. So that is the principle. Here in red, next to the coordinates, you have the corresponding set ordering number, which is formed according to the principle that we have discussed. And I see you have a sense for it now. You also might notice that here I have some points which are filled blue circles and some points which are empty circles. What I want to represent here is that the points that I'm connecting, they might not be occupied. So with this method, we are ordering the coordinates in the space independently of whether we have any objects at those coordinates or not. So in this case, the blue circle, for instance, could represent that there is some kind of object associated with that coordinate, while the empty circle represents the case that there is no object at that coordinate. We just have the coordinate, and with set ordering, we are essentially ordering the coordinates in the space independently of which objects we have stored in the space. So that is one specific of that method. There's other methods which are actually adapting the way in which they divide or sort the coordinates in the space to which data is present. But this method does not do that. All right, so let's continue filling it in. So the next one here, we are mixing coordinates again. We are getting the 0 from X, then the 0 from Y, then the 1 from X and the 0 from Y. So that would be a binary 2. This is why this is the set ordering number. And we continue in the same way. This is how it looks like. And I mentioned quickly that set ordering is not perfect in keeping close points close together in this ordering. As you see here, in most cases, we have close by points in the two-dimensional plane, which have pretty similar numbers according to set ordering. But in this case, from 7 to 8, we have a bit of a jump, actually. So in this case, the set ordering doesn't seem to be ideal. And if you're interested in this, then you will find methods that avoid those cases and are even better at keeping close by coordinates close in the corresponding ordering. So let's just fill this up until we have covered all the coordinates, which has happened now. And as you see here, in most cases, we keep close by points close together. We are essentially reducing a multi-dimensional space to a one dimension by ordering all of the coordinates. And because we are doing this now, the advantage is we can essentially use standard B+ tree indexes or other indexing structures in order to index objects in that space according to their set values, which represent the coordinates. And if I have something like a multidimensional range query, for instance, I could somehow look up the set coordinates of a region which contains the object, or I could, if I am looking for one specific point in particular, I could calculate the corresponding set value, and then I could query the index for that specific point. So we are at the end of the time slot. I'm going to stop here. The next time we're going to see more on spatial indexes, and we're also going to discuss about corresponding systems for processing spatial data. Have a nice day, and then I see you again on Friday. All right, let's get started. Today, we're going to continue discussing about spatial data, like what we have for maps or for 3D objects, for instance. And the last time, we have started discussing about how to index spatial data for efficient access. The first idea was that we just use our usual B+ trees and so on. But we have seen that this can be actually quite inefficient because those indexes don't necessarily store points close together that are close together in, for instance, the two-dimensional plane. So we need some specialized indexing structures, and we're going to discuss about a couple of them. Last time we have already started discussing about set ordering, which is essentially a way of mapping a multidimensional space to one-dimensional curve through it, such that coordinates that appear close together on that curve, they're also close together in the original space. This is how we would do it for 2D coordinates. If we represent those coordinates as a bit string, then we get the set ordering number by just mixing one bit from the first coordinate, then one bit from the second coordinate, then the second bit from the first coordinate, then the second bit from the second coordinate, and so on. So we keep mixing those bits from the two coordinates, and that gives us the set ordering number. We have also quickly illustrated this with the example here in the two-dimensional plane. Here, coordinates are represented by 2 bits only to keep it simple. And then the first point would be the origin, basically. And then the next point would be this one here, because we take the 0 from the x coordinate, then the 0 from the y coordinate, then the 0 from the x coordinate, the second one, and then the 1 from the y coordinate, and that in binary representation is the 1. And if we continue doing this, then we can traverse the entire range of coordinates here. And as you see, at least in most cases, points that are close together in the 2D space, they also have a close set ordering number. There's a few points where it works a little bit less good. For instance, here you have the jump between 0.7 and 0.8. There's a couple of refinements of that principle which avoid those little jumps. But in each case, that should work better than using a B+ tree on a composite key that includes the two coordinates. So with this, we can essentially use a standard index in order to store the set ordering number. So this is what we have already discussed the last time. Now in the following, we're gonna extend that further and see a couple of alternative indexing structures for spatial data. One thing about the set ordering is that it orders points in the space. Now, sometimes you don't want to represent single points, but you want to represent larger regions instead. And of course, in principle, as long as you have some finite precision coordinates, you could represent them by a set of points, but of course, that would be very inefficient. Here, there's some specialized indexing structures that can store those regions more efficiently. And the first one that we are going to see is the region quad tree, which enables you to store regions quite efficiently. And this region quad tree essentially recursively divides the space into smaller and smaller boxes. So in the following, we're going to see a 2D example. In 2D, we would essentially divide each part of the space into 4 subregions, and then those 4 subregions are associated with child nodes in a tree. So let's illustrate this with this a little example here again. So this is the entire space that I want to index. So if I create the region quad tree, then first it would contain a root node that essentially represents the entire space. And now I recursively decompose this into 4 quadrants, which become child nodes in the corresponding region quad tree. And now, for instance, if I want to represent one of those green regions precisely, then I could simply stop the decomposition, because here I want to represent maybe the upper left quadrant, for instance. Now I already have a corresponding node. Now that might still be a little bit coarse-grained, but you can just continue the decomposition perhaps for one of those quadrants, and now you can represent even more fine-grained regions. So here you can essentially stop the decomposition once you have achieved the resolution that you want, and once you can represent the region that you want to include in the tree. So that is the region quad tree. It divides the space in a way that is independent of the data that you actually want to represent. And then if you want to represent a region, it becomes one node in this tree. And if you want to know, for instance, whether one specific region is included, then you can traverse this tree from the root node to the corresponding leaf node. And then selecting a child node, you just see whether the region that you're looking for is contained within the part of the space that is represented by the corresponding child node. And also you see that when traversing the tree, you will finally end up with one single leaf node, because those child nodes, they are always non-overlapping. So it is clear which of those children you need to continue with when searching for one specific region. Okay, so that is the region quad tree. Any questions on this? All right. Okay, so one potential drawback of, for instance, this region quad tree is that it is independent of what the data actually looks like. That leads to so-called grid files, which try to adapt the indexing structure to the specific data that I want to store within it. So essentially, the decomposition becomes more fine-grained for those parts of the space where we have lots of points stored, and less fine-grained for the parts of the space where I have less points stored within them. And once I insert or delete points from one of those grid files, I keep dividing or merging a part of the space. And I do it in a way in order to represent the data with the minimum amount of space. So we're not going to go too much into detail with grid-wise, but you can find more details in the book. I want to discuss art trees in a little bit more detail because they're very common data structure that is often used in practice. And art trees are essentially an adaptation of B+ trees to handle spatial data because they have very common properties with B+ trees, the very common indexing structure in databases. And in the following, we're going to see in a little bit more detail how they work. Now, the search key for an art tree is generally a multi-dimensional bounding box. So essentially, you query one of those art trees by giving a bounding box, basically an interval for each dimension. And then from the tree, you can obtain all the objects that are contained within this bounding box. Similarly to the B+ tree, we are storing data in the leaf nodes, and we are distinguishing between data entries and indexed entries. If you think back of the B+ tree, it had those data entries in the leaf nodes, and it had those index entries in the inner node. The purpose of data entries was to capture the actual data or references to the data. The purpose of index entries was just to guide your search for objects from one level of the tree to the next level of the tree. And the purpose of those is similar for art trees, just that the search key is represented a bit differently. So for instance, in a case of data entries, what we're storing is a pair of the record ID, the record, and the associated bounding box for that record. And depending on what kind of object it is, if it is a box, then that's of course easy, but maybe it's a less regular object. So in those cases, we store whatever is the smallest box that still contains the object. For the index entries, we are storing pointers to child nodes, like in the case of the B+ tree, but here also we are storing a bounding box that is associated with the child node in order to direct our search to one or multiple child nodes. And finally, one property that connects the art tree to the B+ tree is that we also try to keep it balanced in order to reduce the number of lookups that we have when moving from the root node to one of the leaf nodes. And that means that also after insertions or possibly deletions, for instance, we might have to do some work in order to rebalance the tree. Now, this is a little illustration for how the art tree works. So you might still remember on the previous slides, we have seen the region quad tree, and it divided the space into equal-sized, equally distributed parts. So here that is not necessarily the case. The art tree is more flexible, and here you see how it divides the 2D space into finer and finer bounding boxes. And on the right-hand side of the slide, you see the corresponding tree representation. Now we are storing potentially multiple bounding boxes in each of those nodes. They are represented with their corresponding identifiers, and different colors are associated with different levels of the tree. So here in the root node of the tree, we are storing index entries with bounding boxes R1 and R2, and R3 is contained within R1. So here we are storing R3 in the child node that is associated with R1, and within R3 we have even R6. So here we are storing R6 as child node of R3, the node containing R3. And as you see, the bounding box of the child node is are always contained within the bounding boxes of the with the corresponding entry in the parent. think there might be a question. All right. Okay, so the question, why does R5 point to R7? Why not R4? So R5 doesn't actually point to R7. That would mean that R4 points to R7. So the representation on this slide neglects a couple of details because it becomes difficult to represent. So here in each of those nodes, I represented the bounding boxes of the index entries that are contained within it. But then when making those arrows, then I didn't specify precisely which index entry the corresponding arrow is attached to. So in order to be more precise, what we would have to say here, when considering the green node containing R4 and R5 and the yellow node containing R7, then R4 and R5 represent index entries in the green node. R4 has the bounding box that you see on the left, the same as R5. And R7 would be pointed to by the index entry with bounding box R4, actually. So you are absolutely right. It's a great question. So this representation doesn't make it explicit, but here R7 would be associated with R4 because it is contained within that. So yes, so in this representation, I'm essentially just connecting nodes. If I want to make it more detailed, then I would have to connect the single index entries to specific child nodes. But here I'm abstracting away from that. Okay, very good question. Now there's another question. Okay, what would we do if R4 contains the region we are looking for, but R7 doesn't? Do we stop our search? Okay, that's a great question. How do we use this for searching? I'm gonna explain that on the next slide. So if there's any questions after that, then please ask again. So for the moment, I wanted to mostly illustrate the structure of the index and what it stores. So here we are storing index entries in those inner nodes, and then here in the leaf nodes, we would store all the objects that are contained within a bounding box R7 or R6, depending on the leaf node. Okay, so that is how the index looks, but how do we actually use it for querying and how do we do insertions? Let's see how that works. So this is the way in which I use the index to obtain stored objects. So the search key is the bounding box for the query or for the query object that can, in principle, be the query object can be a single point, or it could be a region or some other geometric object. So in that respect, we are quite flexible. And in order to find the object that we're looking for, we start at the root node. And the way we select our child nodes is that we have to check all children that contain the query object. And now here, there's a difference to the B+ tree, because in the B+ tree, we always knew that we have to continue to one specific child in order to find the object we're looking for if it is contained in the tree. Now, in the case of the R tree, things are a little bit more complicated for us because potentially multiple child nodes can be containing the object that I'm looking for a priori. That is because we don't require the bounding boxes of our index entries in the same node to be non-overlapping. We have seen that in the previous example. If you look, for instance, at R4 and R5, those two nodes, those two bounding boxes, they overlap actually. So if I was searching for an object that is contained in the intersection of R4 and R5, then I might have to check two corresponding child nodes. All right. So that is the way in which I do lookups. It's a slight generalization of what we're doing for B+ trees. Here we might actually have to check out multiple child nodes if the bounding boxes overlap. Now, how do we do insertions? So if we want to insert a specific object into the tree, then the first thing we need to do is to calculate the corresponding bounding box, like the smallest box that contains the object that we want to insert. And then again, we start at the root node and we proceed to the leaf nodes. At each step, we here for the insertions only select one single child. And when selecting that child, you might have some choice because multiple bounding boxes contain the object that I now want to insert. In those cases, I typically use a heuristic in order to select the child where, for instance, I have the most overlap with the corresponding bounding box. So I essentially use the child where I have to have the most overlap with the bounding box that I want to insert. If I do this, then at some point I will reach one of the leaf nodes, and then I will insert the new object into that leaf node. Now, I might have to expand the bounding boxes on the path from the root node to the leaf into which I have inserted. If the newly inserted object was not completely contained in all of the bounding boxes that we have traversed, in that case, I might have to change to enlarge the corresponding bounding boxes. And that's also new compared to the B+ tree insertions. What reminds us of the B+ tree insertions is that in order to keep the tree balanced, if I have to split one of the leaf nodes, because the leaf node is full, in that case, I have to split the entries over 2 pages. In those cases, I might have to rebalance the tree. Similarly to what we have seen for B+ trees, there's a couple of different methods. One thing that I could do, for instance, is that I just take out a certain percentage of objects from the tree and then I reinsert them. But there's multiple methods. All right. So in the following, we're going to discuss a little bit about SQL extensions that allow you to query spatial data. And towards the end, I'm going to show you a little demo from a system by Google, which allows you to query spatial data with those query formalisms. If you want to read up more on how to query spatial data, if you want all details, you can find the complete specification of the SQL extensions described in this document over here. And in the following, I'm going to see a few important extensions to SQL in order to give you some impression for what those extensions look like. But of course, there's many more functions that you probably want to get to know in case you want to seriously work with spatial data. So for the moment, I'm only giving you a high-level overview and discuss some examples for those functions. So if we work with spatial data in SQL, then there's a couple of specialized data types, basically, that represent this as spatial data. There's a couple of functions that you can use in order to construct those objects. For instance, if you want to construct a point data object, then you can use this constructor on the top in order to construct a new point, and on the bottom you see a corresponding statement for creating a line. So those are essentially constructors in your SQL query that create objects of the corresponding type. If you have objects or a collection of objects, then often you might want to get the boundaries of those objects. So we have the st boundary function which essentially returns you the union of all the boundaries of the geography expression that is the argument of this function. And if you break it down into specific types of objects, for instance, points by definition don't have any boundaries. For lines, the boundaries are the two endpoints, and for polygons, you have lines that are bounding those polygons, and the ST boundary function returns the union of all of those boundaries. You might also want to calculate something like a centroid, for instance. In that case, we are essentially calculating a weighted average of the component centroids if your geography expression refers to multiple spatial objects. And again, if you break it down into specific types of objects, for points, the centroid of a collection of points, it's simply the arithmetic average of the coordinates. For line segments, it's simply the middle point, and for polygons, it's the mass center. So this centroid function calculates the corresponding centroid and might represent it visually if you have a map-like representation, for instance. There's a couple of functions that allow you to access specific parts of those specific properties of those spatial objects, like the longitude and the latitude, or the number of dimensions. Those functions are represented here. You can also formulate predicates. For instance, you can check whether one region or one object contains another one with the contains a function. You can check for objects within a certain distance of other objects using the d within function here. And if the two objects that you're comparing have a certain spatial extent, then here this predicate evaluates to true if there's at least 1 point from each of the two compared objects that are below the minimum below the distance expressed in meters by default. You can calculate things like the area of spatial objects. You can calculate the distance between objects and many more things. So all of those things that you would typically want to do with spatial data, there's a corresponding extension in SQL. And so in the following, I'm quickly show one demo of a system that allows you to query spatial data. It is a system by Google. Here you see the system. It's the BigQuery GeoWiz tool. So yeah, I think now you should see the editor window. So this allows you to query geographical spatial data. You see that on the right-hand side, we have this map representation, and on the left-hand side, we have the editor field for entering SQL queries. And so in the following, I'm gonna run a couple of queries on a data set that contains information about the boundaries of a zip code areas in the United States. That is one of several data sets containing spatial data that are publicly available here. So for instance, all right, so here the zip code geo is a geometrical object that is associated with a specific zip code. And maybe for the moment, we're interested in zip codes that are associated with a city called Ithaca. So let's see whether I got the column names right. I did not, but that is actually a great function here because it tells me, it gives me some hints about how I want to correct that. Unrecognized name, zip code geo, did you mean zip code Guillaume? All right, so here I have to insert an M And now it works much better. So the query executes, and actually here it's popping up some markers also for Michigan. Perhaps there's like a different cities with the same name. I was actually more interested in this city over here in New York. As you see here, it has marked the corresponding objects in the database in red. All right, so let's maybe zoom in a little bit more, or let me maybe refine things and restrict the state name to New York. All right, so run that again. It zooms in a lot. Okay, and here we have indeed Ithaca. All right, so now there's a couple of functions that I could run. For instance, here I have selected all of the points. Maybe I mostly want to find out about the extent of Ithaca, about the boundaries of those different zip code areas. So let's use the st boundary function, which I'm using essentially like one of those SQL aggregates. If you think back of the sum, minima, and maxima, and so on. So here I'm just using this in order to apply it to the zip code geom column, which contains those geographical objects. So let me run that again. Now it should narrow down to the corresponding boundaries. Here you see it was filled in before. Now I'm only getting the corresponding boundary. Or maybe I'm not interested in the boundaries, but I'm more interested in the centroids, for instance. Then I could also change my query accordingly. Okay, now here it has zoomed in a lot. This is why I only see red for the moment. But if I'm zooming out, then I am getting something which is located pretty much in the center of Ithaca. It seems to be somewhere on Cornell campus, actually. All right. And okay. So what else could I do here? I could, for instance, look for different locations, or maybe I'm not only interested in things directly within Ithaca, but I'm interested in things that are somewhat located close to Ithaca. I have prepared a corresponding query here. So here, what I potentially want to do is that I find information about zip code boundaries in New York within a certain distance of Ithaca. Here, I mostly want to demonstrate you that you can still use those SQL features like subqueries, for instance. What I'm doing here is I'm using the std distance within function, which is a predicate that evaluates to true for objects below or at a certain distance. And what I'm comparing here is essentially the zip code area with the result of a subquery, which selects everything from the database where the state name is New York and the city is Ithaca City. And here, this is the maximum distance in meters. So I'm searching for things around Ithaca within a distance of about 100 kilometers. And if I'm running this, then I'm getting a little bit more data. Okay, so here I'm getting data from New York about zip code boundaries that are somewhat close to Ithaca. So here, this is just a small subset of the features that you have when acquiring spatial data with SQL, but it can already be quite useful. Maybe we want to switch location a little bit and go somewhere a little bit warmer. So let's maybe, for instance, try this. That retrieves even a little bit more data than before. So this system is based on the Google BigQuery system, which can handle large amounts of data and process them in parallel. It might still take a little bit. All right, now here I'm getting first results. Hold a little bit. Getting more results. Takes a little bit to run that query. Okay. All right. Okay. So this is to give you a little bit of an impression for how it can look like to work with one of those systems that allow you to query spatial data. That's, of course, not the only system. There's multiple systems supporting this standard that extends SQL for spatial data. Also for Postgres, for instance, there's extensions that allow you to query spatial data in Postgres as well. All right. And with this little demo, we are essentially at the end of our chapter of on spatial data. So we have generally seen that there's quite a few use cases for working with spatial data. The first thing people would think about is probably map data, but also for storing three-dimensional or even higher-dimensional objects, there is corresponding applications. We have also seen that standard data structures in particular are a bad match for storing and querying spatial data, but there is specialized data structures such as the R tree, which can deal with spatial data much more efficiently. And from the user perspective, you might want to use extensions of SQL that have been extended with spatial operators. We have seen one of them in the BigQuery GeoVis tool, but there's other systems that support the same extensions, also Postgres as one of them. All right, so now we're going to discuss about a different class of systems which implement something called eventual consistency. The material that we will discuss here is not in the book, but you can read up in more detail in the papers that you see here, which is the papers in which the systems that we will discuss in the following have been initially described. Now in the following, we're going to talk a lot about consistency. And I want to start with a little terminology warning, because we have already heard about consistency, which was the C in the ACID transactions. And in that context, consistency generally means that your data is consistent with all constraints. Now, in this lecture, we will be discussing about systems and about insights that come from a little bit of a different community. Therefore, the terminology is slightly different. And if in the following I talk about consistency here, what I mean is that in a distributed system, the different replicas appear to be in sync. So meaning that if you have an update to an object and you read the object later, then you will always see the updated value, and guaranteeing that is actually very difficult if for each object you may have multiple copies distributed over different nodes in your system. So the consistency that we will discuss in the following is a little bit different from the consistency that we have been discussing before, which is a bit unfortunate, but here there's just terminologies from different communities that overlap a little bit. All right. So let's discuss a little bit about trade-offs in distributed data systems. So we have discussed about consistency in the sense that different copies of your data appear to be in sync. And in the following, we're going to see a little example that shows that consistency can sometimes conflict with availability, meaning the capability of a system to answer requests. So let's assume that we are considering an online shop which has multiple sites in order to serve customers in different regions, for instance. Here in the simple example, we only have 2 sites, and each of those sites has a copy of the inventory, meaning how many items you have left from each type. And of course, those sites need to communicate with each other. So if one of them receives a request, they can update the other one in order to make sure that those inventories are in sync. Now let's assume that there is a communication failure. So here the network gets partitioned, we say, meaning that the different parts of our system cannot communicate with each other anymore. And now let's assume that there comes a customer who wants to buy something. So here, let's say somebody wants to buy a specific DVD. Now we have a couple of possibilities to handle that. Now, the first possibility is that we accept the request, which means that in our site1 directory, we have to reduce the DVD stock by 1. But that means that our 2 copies of the inventory now become inconsistent, because at this point in time, we cannot communicate that change to the other side because communication is interrupted. Now, the other possibility is that we just say, we are not available, we cannot treat this request, because if we did, our inventory could become inconsistent. And at least in principle, that could cause problems. I mean, imagine, for instance, that both of those sites start accepting buy requests for DVDs independently, and then at some point you have sold more DVDs than you actually have. So there could be problems. But of course, here we would make the customer unhappy, and we would lose one sale. Now, this little example shows you that is a trade-off sometimes between being consistent between different data copies and it being available, meaning being able to answer requests. And this example essentially has been generalized into something called the CAP theorem, which abbreviates consistency, availability, and partition tolerance, and essentially claims that it is an intrinsic trade-off between those different things. I mean, all of those are things that you want. You want to be consistent, you want to be available, you also want to tolerate network failures where your system gets partitioned into different parts that cannot communicate with each other. But this theorem essentially says that you cannot always have all of those together. So with some little extension of the example that we have seen before, essentially authors make the case that you cannot have the intersection of all 3, which is what you ideally want. Now, among the remaining options, traditional database management systems, they would typically prioritize consistency above everything else. So this is where traditional database management systems are located, at the intersection between consistency and partition tolerance. On the other side, the type of systems that we will be discussing about today, those are called NoSQL systems, which favor availability over consistency and would rather decide to sell the DVD even if they cannot currently communicate with the other copies of the inventory in the example from before. So those are 2 different trade-offs, and it depends on the specific scenario which of them you want to make. Now, the class of systems that we will be discussing today provide something called eventual consistency. Eventual consistency essentially means that we don't absolutely require our data to be consistent at all times. But instead of that, what we try to achieve is that we at least become eventually consistent. So if there's no new updates to the system, then at some point, all the copies of our data will become consistent again. So this class of system is motivated by application scenarios such as online shopping, because here you absolutely want to make sure that you can serve your customers as much as possible, because if you don't, then you lose money. So in those scenarios, perhaps being always available for customers can be even more important than having your data consistent at all times. The paradigm is also called base, which differs from ACID already in terms of semantics. So base stands for basically available, soft state, and eventually consistent. So here basically available means that you prioritize being available above everything else. Soft state means that you don't necessarily require your data at different sites to be consistent at all times, and eventually consistent means that eventually you will converge back into a consistent state. So that is kind of a counter, that is kind of the complement of ACID transactions in a way. And this is what those NoSQL systems that we will be discussing are aiming for. NoSQL is actually a bit of a broader term. It has been used with multiple semantics. In general, it designates systems that make a little bit different design choices compared to traditional relational database management systems, which could, for instance, mean having reduced the consistency base. Could also mean that we support different languages than SQL. In many cases, simplifications of SQL, which makes it easier to support them efficiently. It also refers to systems that use different data models compared to relational database management systems. So the term has multiple different semantics, but here in the following, we're gonna particularly focus on the reduced consistency requirements compared to traditional distributed database management systems. Now in the following, we're going to discuss about a couple of representatives of that category of systems, starting with Apache Cassandra. Now, Apache Cassandra is a distributed system. All of the nodes in that system, they have the same role, which means in particular that there is no single point of failure. If one node goes down, then the other nodes, they can continue operating. It is a so-called wide column store, which essentially means it looks a bit like tables in the database, with the difference that different rows in those tables, they can have a different number of columns. So in a way, this is more flexible than the traditional relational data model, where each table needs to have rows that each have the same number of columns. It supports a language called SQL, or Cassandra Query Language, which in a way is a simplification of SQL, because, for instance, you cannot do things such as joins, which makes it also easier to support it efficiently. It is optimized for scaling up linearly when adding new nodes. So basically, if you add more nodes, then you always increase the number of requests that you can answer. And that is a very desirable property to have for a system. And it offers you various ways in order to tune trade-offs between consistency and availability. Perhaps one quick example about how eventual consistency manifests in practice. Here I'm gonna show a couple of experimental results of a paper that evaluated another eventually consistent system, which is Amazon's SimpleDB. And in this experiment that you see here, what they did was essentially they update an object and then they read it immediately afterwards. On the x-axis here, you see the amount of time that passes between the write and between the read operation. And on the y-axis, you see the probability to read the most recent value. And as you see here, after about 500 milliseconds, there is a jump from about probability 33% to probability 100%. Does anyone have a suggestion about how the underlying system could be set up? So this is a system where we don't necessarily have the details about how it is working internally, because this is not necessarily released by Amazon, but by doing those experiments, you can come to some assumptions about how the system is working internally. And if you see this, so after 500 milliseconds, our probability to read the most recent value jumps from 1/3 to 1. What do you make of that? What do you think what the system is looking like? Okay, very good. Yeah, so after half a second, the central coordinator looks for the most updated version and sends updates to all nodes. Okay. If possible, we might want to avoid the central coordinator. But okay, so in general, after half a second, it seems that updates are propagated. It could also be like different nodes talk to each other every half a second. Okay. If you would have to guess how many replicas there are in the system, do you have any suggestions? Okay, very good. Yes, it could be 3 replicas, right? So what this could mean is that there's 3 replicas in the system, and we have to update one of them only in order for write to succeed. And we also only have to read one of them for read to succeed. So in this case, we could assume that we have those 3 replicas. If we read them immediately after the write, then we have a chance of 1 to 3 to get the right replica, which already has the most up-to-date version. And then every half second or so, those different replicas synchronize, so your update is propagated to others. So that would be one reasonable assumption in line with those experimental results that we see here. And more generally, those experimental results give you some intuition for how quickly those things propagate in practice. So we have talked about the theoretical concept of eventual consistency, but this tells you something about how eventual that is in practice. And here it seems that changes propagate already fairly quickly. We also measured, for instance, the peak times between writing and until the write is received in following reads. And at least for the 99% quantile, that works pretty well. And we have a very stable times around 500 milliseconds. There's a couple of longer peaks, but they are fortunately quite rare, but they might still occur. So with eventual consistency, you can never be 100% sure. Every once in a while, it might actually take significantly longer to propagate your updates, up to a couple of seconds, basically. Now, the CAP theorem has been criticized. The points that you see here are actually by the original author of the CAP theorem. He wrote another paper later in which he critically discusses the CAP theorem. And among the points mentioned are, for instance, that the CAP theorem focuses on relatively extreme cases. If you really have a system where different parts cannot at all talk to each other anymore, that might be rare. And also, we consider consistency and availability as something binary in the CAP theorem, and that, of course, is a simplification. In practice, you have a lot more choices. For instance, you don't have to decide in general which of the two, availability or consistency, is more important. You could decide that for each single transaction or for each single user. So this is more flexible than what it sounds like in the CAP theorem. And also consistency, it's not really a binary property, but it's there's a whole range of different consistency levels, so to speak. So altogether, the point is that the CAP theorem simplifies a couple of things, and that the choices might not be as strict as it suggests. Now, this has led to a new wave of systems that are often called a NoSQL. And the NoSQL essentially means that we try to get back consistency guarantees, we try to get back ACID guarantees when processing transactions, while at the same time maintaining high performance by exploiting a couple of new ideas and new developments, for instance, when it comes to the hardware. Now, this is a little overview of the different categories of systems that we have been discussing in the past few lectures. Of course, there's the so-called traditional distributed database management systems, which aim to guarantee ACID transactions, even if it comes at the expense of performance. Then we have seen a NoSQL systems, which is a broad term, but often it entails that we are giving up ACID guarantees for higher performance. That was the case, for instance, for those systems that we have seen last time. Now, in this lecture, we're going to focus on a few more recent systems, dubbed the NoSQL, which try to get the guarantees of ACID transaction processing, while at the same time having high performance and availability. Now, HStore, the design of HStore is based on a couple of observations about modern transaction workloads and modern hardware. For instance, it used to be not uncommon that we had a relatively long-running transactions. In modern workload, those transactions are typically extremely short. And also those transactions, they execute automatically. So unlike prior transactions, they don't require any input from the user at any point, which will significantly slow down transaction processing. Furthermore, the transactions typically correspond to templates that are known in advance. I mean, one typical application scenario is, for instance, a database system that is accessed not by writing SQL queries and transactions, but rather over a web interface. If you as a customer do online shopping, for instance, then the web interface often triggers transactions in a database in the background, but the templates of those transactions are already known before runtime, because they have to be in sync with the web interface. So they only depend on the specific parameters that you enter in some of the fields in the web interface, but the structure of the transaction is already decided a priori. There's also a couple of changes on the hardware side. It used to be prohibitively expensive to put databases into main memory, because main memory used to be very expensive. Nowadays, main memory has become cheap enough that for most databases in practice, it is actually feasible to fit them entirely into main memory. And then, of course, on the other side, what has changed is that nowadays, typically, if we build a system, then in most cases, It's going to be a distributed system, and altogether those observations entail a couple of design decisions for the HStore database system. So if you look at those observations, is there perhaps anything that comes to mind for you about the design implications for database systems? So if you look at those properties of modern hardware and modern workloads, does it suggest changing the design of database systems in any way? The authors of HStore certainly thought this way, and we will see in the following how HStore exploits those properties here. But I already wanted to ask whether anything spontaneously comes to mind about how those observations influence the database design. Okay, that's a good point. Recovery might be more difficult. Okay, why might it be more difficult? All right, okay. So very good. Yes. So here, if we can fit the database into main memory, then we probably want to do that because it is faster. But if we do that, then recovery becomes much more difficult. Now, if you think, for instance, about concurrency control, we initially said that we want to interleave the operations of different transactions for multiple reasons. Can anyone remember what the reasons were that we want to interleave the steps of different transactions? Yes, very good. There's a first reason, because long-running transactions would delay shorter transactions that are blocked behind them. If one user in the system is running this big transaction that takes an hour to finish, and if we don't interleave steps from different transactions, then all the other users with very short running transactions would be blocked behind that 1 hour transaction. And that would make everyone unhappy, basically. So yes, if there's long running transactions, then we want to interleave operations from multiple transactions. Long-running transactions, yes. Specifically, we discussed about a situation in which transactions often remain idle because they have to wait. And in those situations, it makes sense to squeeze in a step from a different transaction. So what is it that transaction often need to wait for? Very good. Here the suggestion is that we have to wait in order to read data from hard disk. Very good. So that is the other big motivation for interleaving the steps of different transactions, because if one transaction is waiting to get data from hard disk, then another transaction whose data is already in main memory may as well proceed. Very good. Now looking at those changes here, what do you conclude for concurrency control? So okay, very good, yes, exactly. So I mean, initially we said we don't want to execute transactions serially because of long-running transactions, because of waiting for data from hard disk. But now we are in main memory, so we don't wait for data from hard disk anymore. And all of our transactions tend to be short running. So for those reasons, there's actually no real motivation anymore not to run transactions serially, because it simplifies a lot of things. We have seen that concurrency control can be complex and it can cause overheads. But if I can just execute transactions serially, then it is probably the simplest thing to do. Okay, very good. There's also the point about transactions corresponding to templates. Is there any way in which I can exploit having some knowledge about the transactions before runtime? If somebody told you which transactions, roughly, which transactions are executed at runtime, what could you do in preparation in order to make data processing faster? Okay, we could load data in advance. And I mean, here we assume that everything is, everything is generally in main memory, and we would load the data before runtime into main memory. Yes, that is correct. What other decisions could you make if you know in advance approximately which transactions will come in? You have a lot of data. It is distributed over different nodes in your network. Is there some decisions that could influence the performance, which you can optimize perhaps by knowing a little bit about which transactions come in at runtime? All right, very good. So maybe we can already do some operations, something expensive like a join, for instance, already in advance. Or perhaps if we don't completely do it in advance, but we do preparation in order to make it very efficient. What kind of preparation could that be? Very good. Hashing data, for instance, okay. Yes. And in general, I mean, hashing is one valid way of distributing data across different nodes. So you can calculate a hash value in order to decide where to put one specific row of a table. And if you partition two tables using the same hash function and using a column from both tables that will be often joined together, then you ensure that a table partitions from different tables that join together are already located on the same machine, and therefore doing the corresponding joins becomes much cheaper. Okay, very good. I think we covered the primary points here. So if we know in advance which transactions come in, we can exploit that, for instance, in order to partition our data well, or generally to decide where to locate which data and how often to copy things and so on. And that can make processing at runtime much more efficient. So I cover the different points. I think we have essentially covered all of them. So because main memory has become cheap, we want to exploit that and actually store the database in main memory. Here, we have already heard that recovery can be difficult, but what we can do is that we simply create multiple nodes, independent machines, which store the same data. And if one of them crashes and loses the main memory content, we can just use data on the remaining nodes that have the same data and remain online. We're going to see in more detail how precisely we are going to do that. We have short-running transactions without disk stores, so why not just execute them serially? And we don't need any concurrency control like the ones that we have seen anymore, and it simplifies things a lot. And because we know a little bit about which transactions will come in at runtime, we can exploit that in order to do pre-processing, which makes runtime processing much more efficient. All right, so this is a little overview of the design decisions that HStore makes. Here you see a high-level architecture outline of the HStore system. So here on the left-hand side, you see a couple of components that are invoked before runtime. On the right-hand side, you see components that are involved in runtime processing. So here, before runtime, we already assume that we have a lot of information given. We have, of course, the database schema. We have some information about the cluster on which we want to deploy our database. We have stored procedures, essentially meeting those transaction templates, and we have a sample workload given. And using that sample workload, we can, for instance, see which tables are often joined together. And then using this deployment framework, we try to optimize the whole setup. We try to decide the physical data layout, which means essentially deciding where to store which data on our cluster. We already compile the stored procedures, which also saves runtime overheads, and we can already make certain optimization decisions in query planning. Now, at runtime, we receive transactions as input. You see this acronym OLTP here, which stands for Online Transaction Processing. So this designates workloads that generally contain a lot of transactions. At runtime, we use those precompiled stored procedures in order to execute those transactions that correspond to the templates that we have seen before. And we might need to coordinate the execution with different nodes for transactions that touch data which is located on different nodes. Often we are lucky and can already find the data which is relevant for a transaction on one single node. We can increase the chances for that by choosing a good data partitioning at preprocessing time. And altogether, the system aims at providing asset guarantees while still being very highly available and having a very high transaction throughput. So for most of this course, we have been considering classical relational database management systems. In this last part of the course, we have expanded our scope and considered systems that target different types of data, such as graph data, spatial data, or stream data. And we have seen NoSQL and NewSQL systems which make different design decisions compared to more traditional systems in order to gain performance. I've given you a high-level overview of those different types of database management systems in this section. If you want more details, I recommend you to check out the reading list at the beginning of each lecture. This was the Introduction to Database Systems course given in fall 2020 remotely at Cornell University. My name is Immanuel. I hope you enjoyed this course, and I hope you learned something that will be useful to you.